So good afternoon to one and all. Good afternoon. So till yesterday we have done line to line fault analysis little bit, right? And we'll be taking up some problems in this area now. LL fault analysis, some problems we are going to take up. So I'm taking up the first problem in the line to line fault analysis. So it's a previous GATE examination question. I think asked in 2018 or 19, I think so. Right? So please go through this question once. See the positive, negative, and zero sequence impedances of a three-phase generator. Three-phase generator are Z1, Z2, and Z0 respectively. Z1, Z2, Z0 respectively. And for a line-to-line fault with a fault impedance of ZF, the fault current is IF1. IF1 equals to K into IF. IF1 is equals to K into IF. Okay, where IF is the fault current. IF is the fault current with zero fault impedance. Okay, the relationship between the ZF and K is what? The relationship between the ZF and K is what? Yeah, look here. So I'm moving with the next slide to take up solution for this one. See, first of all, in the data provided, we have an alternator, right? And positive, negative, and zero sequence impedance of this alternator are Z1, Z2, Z0. Done. Next one. According to the data given, with a fault impedance ZF, if you have line-to-line fault, then that fault current is IF1, he is saying. Okay. So with the fault impedance ZF, line-to-line fault current, what's the formula for that line-to-line fault current? Minus J root 3 times of pre-fault voltage by Z1 plus Z2 plus ZF. Z1 plus Z2 plus ZF. That's the thing. Okay. And this is the value what he's saying as IF1 actually. He's saying that as IF1. So without ZF, if we take without that fault impedance value or with zero fault impedance, you can call if you want, without ZF value or with zero fault impedance value, fault current line to line, that is minus J root 3 times of pre-fault voltage by Z1 plus Z2. Z1 plus Z2. And this is the value he is saying as IF in the problem. Okay. Now, he is giving that relationship between IF1 and IF2, right? Let us take this ratio, IF1 by IF from this mathematical equations. Okay. So, ratio between IF1 and IF. So, IF1 is minus J root 3 times pre-fault voltage value by Z1 plus Z2 plus ZF. Z1 plus Z2 plus ZF you have. Okay. Next thing. IF is minus J root 3 times of pre-fault voltage. Minus J root 3 times of pre-fault voltage by Z1 plus Z2. Okay. You do that minus J root 3 VPF cancellation. And in the numerator, you have Z1 plus Z2 now. And the denominator, you are going to get Z1 plus Z2 plus this fault impedance as ZF. Okay. What is it IF1 by IF value from the data given? From the data given, just observe here. What is IF1 by IF? IF1 equals to K into IF. Na? So, IF1 is equals to K into IF. Means, IF1 by IF this value is nothing but k. That's the number you have to, that's the value you have to substitute here. Means this is k you have, and you take Z1 plus Z2 plus ZF to the other side. So it will come k into Z1 plus Z2 plus ZF, which is nothing but Z1 plus Z2. Okay. What is asking in the problem exactly? Is asking what is the relationship between fault impedance and K. So simply you have to write the fault impedance equation. Means ZF equation we have to write from this one. Okay. Yeah. So let me proceed with this further. So I can say from this now K into Z1 plus Z2, Z1 plus Z2 plus ZF into K is equals to Z1 plus Z2 again. Z1 plus Z2 here. Then what you do is that K into Z1 plus Z2 you take to other side. So you can get that fault impedance into K, nothing but Z1 plus Z2 into 1 minus K you can get. If you move that K into Z1 plus Z2 to the other side, so minus K into Z1 plus Z2. So Z1 plus Z2 is common, is 1 minus K. And what is the value of fault impedance from this now? Nothing but Z1 plus Z2 into 1 minus K by the K factor. Okay. So this is the relationship between the fault impedance and factor K what we have. Relationship between the fault impedance and the factor K. Yeah. So all of you getting this one? So what's the proper answer from the options given? Obviously option A we can say. Correct option will be A. Correct option will be A. Okay. Listen. See, without doing this solution also, we can tell the answer. Without doing this solution also, we can tell the answer just by common sense. Just by common sense. Common sense in the sense simply, look here. With fault impedance of ZF, fault current is IF1. Without fault impedance, fault current is IF. Means, if you keep ZF value 0 in the first formula, that will be resulting into same as IF, right? Getting me? Please listen here. If you keep ZF value 0, then obviously whatever the IF1 we have, that IF1 and IF will be same. Means cross check will be like this. Cross check. For ZF equals to 0, fault impedance value equals 0. We should say IF1 value and IF values are exactly equal. Means what? That K value will be equals to 1. Na? K value will be equals to 1. Means whatever the options you have here, 4 options here, keep the value of K as 1. Keep the value of K as 1 and check whichever the equation is giving the ZF value as 0, that is a proper answer for us. All of you getting me? All of you getting this one? Keep the value of K equals to 1 in the options given. Check whichever the equation is giving ZF value as 0, that option is a correct one to be chosen. Yeah. So now you can go with the options what they have given. First option, I'll keep K value 1. 1 minus 1, 0. So Z1 plus Z2 by 1 and it is multiplied with 0. So it is 0. So option A is perfect. What about option B? K value 1 if you keep, you get ZF value some number. Z1 plus Z2 into 2 by 1, which is not equal 0 definitely. And what is the next one? And if you keep K equals to 1 here, 1 minus 1, 0, and some finite value by 0, it will be infinite. ZF equals to infinite, what is? Okay, next one. And if you keep K equals to 1 here, Z1 plus Z2 by 2, and ZF value is not coming as 0. Following. So in that way also we can have a cross check that correct answer will be A, obviously. Okay. So correct answer from the option C is A. Answer is A from the cross check also. Yeah. So next we'll take up one more problem in the double line fault. One more problem I'm going to take up in the double line fault quickly. Later on we'll move to double line ground fault. Take this. Next problem. So please go through this one once. This question. These are taken from your classroom objective questions provided by our institute. So let me read it. A three-phase generator is rated for 25 MVA, 13.2 kV, and XD double dash 0.2 per unit, X2 0.3 per unit, and X0 zero sequence reactance 0.1 per unit. The neutral is solidly grounded. Clear. Neutral is solidly grounded. A line-to-line fault occurs on the phases B and C. We have a line-to-line fault on B and C phases of the generator. The value of VB is value of VB is dash kilovolts. Kilovolts. Yeah. Tell me, in the solution, what you have to say first is we have a three-phase generator like this. Three-phase generator. And we have it is a star connected and a solidly grounded neutral. And ratings are given here. 25 MVA three-phase rating. And a 13.2 kV line-to-line voltage rating. Line-to-line voltage rating. And XD double dash value, he said 0.2 means XD double dash value is nothing but X1 only. X1 value is nothing but XD double dash number, that is 0.2 per unit. And negative sequence reactance, he said 0.3 per unit. Zero sequence reactance, he said as 0.1 per unit. All these values are in per unit. On what base values? Ratings. Okay, 13.2 kV, 25 MVA. These are the base values. With respect to those base values, these are the per unit reactances given in the data. So let me take up the same values as base now. Same values are going to be considered as base values. These values itself we are considered as base values. Okay, done. Next, for line-to-line fault on BC conductors, what will be the value of VAB? VAB means line-to-line voltage actually. VA minus VB he is asking. Na? VA minus VB. To calculate this value, first we should find out what are the positive, negative, and zero sequence voltages after the fault has been occurred. After the fault has been occurred. On what basis we have the fault? BC. BC. See, earlier, listen all of you. Please listen here. Yeah, listen here. Actually, in the earlier class, we discussed about line-to-line fault. That's on BC conductors only. BC conductors. After saying that fault is on BC conductors, we got symmetrical components in terms of phase A relation. We constructed the phase A positive sequence network, phase A negative sequence network, phase A zero sequence network. Then we have gone for connection between them. Yes or no? For example, in the exam, if they have given fault on AB conductors, then what you have to do? Right? ABC, na? ABC. For example, if you have LL fault on AB conductors, then whatever the symmetrical components networks you draw, that may come in terms of C, just by following a logic. In case of LG, you have fault on phase A. We have drawn the sequence networks in terms of phase A because equations are saying that to me. Equations are saying in that way. For example, if you have fault on BC conductors, line-to-line fault, we are getting in terms of A. Equations are saying that to me again. For example, in the same way, in similar way, if you have fault on AB and networks may come in terms of C, we have to draw. And if you have fault on AC, it is required to draw the networks in terms of phase B. That logic you have to follow while you are doing the analysis. Anyhow, it was a direct problem for us as we have fault on BC. For LL fault on BC, fault on BC conductors, the sequence networks connection will be of course, as we said, it will be coming in terms of phase A. Okay, so first you have to draw phase A positive sequence network like this, neutral, and phase B negative sequence network, phase A negative sequence network, and zero sequence network is not needed, but still if you want, you can draw that also, no issue. Neutral, and we have to keep 3 times of ZN, that is solidly grounded, already we said, which is equals to 0. 3 ZN value, that is equals to 0. And this is plus minus pre-fault voltage. I am calling as EA1. This is Z1. And this voltage we have VA1, and this current we have as IA1. And this is the voltage I am showing VA2. Impedance we say Z2. Current we have as IA. Okay, so now you can draw this connection. No fault impedance given in the problem. So just you can join these things in this manner. Okay, so now you calculate that VA1 and VA2 values. VA1 and VA2 values. What are the values of Z1 and Z2 given in the problem? Z1 value was J0.2. Okay, Z2 value was J0.3. How much is this pre-fault voltage? Pre-fault voltage, did you mention anything in the problem? Nothing mentioned, so you take it as 1 per unit, means 1 at an angle 0 degree, 1 at an angle 0. Now you calculate this VA1 and VA2. VA1 and VA2. If you want to use capital notation, no issue. Capital notation you can use here. Capital VA1, capital VA2, and here also in the currents also capital IA1, capital IA2. That's your wish. Okay, capital IA2. Now you can get that capital IA1 current easily from this network analysis, which is EA1 by Z1 plus Z2. So EA1 value was 1 at an angle 0 degree, and this summation J.2 plus J.3. So it will be minus J2 per unit. Positive sequence current is minus J2 per unit. Okay. Next one. You have to find capital VA2 value, capital VA1 and capital VA2 from this one. What is VA1 value? Capital VA1 is EA1 minus IA1 into Z1. EA1 minus IA1 into Z1. EA1 value 1. What is IA1? Minus J2. And what is Z1 number? J0.2 already we have chosen. And this value, if you do J square minus 1, and it will be 0.6 per unit. 0.6 per unit. And you calculate capital VA2 also. Of course, as these two networks are exactly in parallel, capital VA2 and capital VA1 are exactly equal. Capital VA2, capital VA1 are exactly equal. Else, if you want to write the formula also, minus IA2 into Z2. Okay, so minus IA2 is minus J2 and Z2 number is J0.3. This number will come to be 0.6 in per unit form. Capital VA2 value was 0.6 in per unit form. Okay, so after getting this capital VA1 and capital VA2, what is capital VA0 value? That is 0. Zero sequence voltage will be 0. You can observe from your network or from the previous class discussion what we have done, because the zero sequence current value was 0 and this impedance is finite. This overall zero sequence impedance is finite. Definitely zero sequence voltage value will be 0. Even though they have not mentioned it, still we can assume that as zero sequence voltage as 0 simply. And what voltage is asking in the problem actually? What voltage is asking? VAB in terms of kilovolts, what is asking? VAB in kilovolts. What do you mean by VAB in kilovolts? What do you mean by VAB value in terms of kilovolts? Nothing but VA kilovolts value minus VB kilovolt value. Okay, what do you mean by VA kilovolt here? VA per unit into V base per phase value in kilovolt minus VB per unit into V base per phase value in kilovolts. So that V base per phase, you can take it out common. So you can get here VA per unit value minus VB per unit value, okay, multiplied to voltage base per phase number. Multiplied with voltage base per phase number. And you just take up the equations of that VA and VB in terms of symmetrical components. Okay, so in terms of symmetrical components, you take up that VA and VB. What is that VA? VA0 plus VA1 plus VA2 in the per unit form minus what is VB? VA0 plus alpha square VA1 plus alpha into VA2. This whole multiplied with the voltage base per phase number. Voltage base per phase. VA0 will be cancelled out and you can take this VA1 common. You get 1 minus alpha square here. 1 minus alpha square. And you can say VA2 common, and you get here 1 minus alpha. This whole multiplied to V base per phase. Multiplied to V base per phase. Okay, already you know VA1, VA2 also equal. VA1, VA2 also equal. That also you can take it out. So capital VAB in kilovolts will be equal to, yeah, if anybody is still writing, please complete it quickly. If anybody is still writing, please complete it quickly. Anybody is still writing, please complete it quickly. Yeah, so I can say, I can take this VA1 common, and what you can get here, 1 minus alpha square plus 1 minus alpha. Just it's a simple mathematical calculation further. VA1 into, you observe here, 1 plus 1 is 2, minus you take common, you have alpha plus alpha square into V base per phase. What is that alpha plus alpha square value? Minus 1. Alpha plus alpha square number is minus 1. And minus minus was cancelled, so it will be 3. So VA1 value multiplied with 3 into V base per phase. That's it. Simple. What is VA1 number? 0.6 into 3 into what is voltage base per phase value? Voltage base per phase. Look at the base values what we have selected. V base per phase is 13.2 kV by root 3. Line to line voltage base is 13.2 kV. Per phase voltage base will be 13.2 kV by root 3 kilovolts. Okay, you please get this answer how much? 13.717 kilovolts. You may get this number as 13.717 kilovolts. That's the line to line voltage of AB. Line to line voltage of AB. But if you have a clear idea, it may not take this much amount of time also. It may not take this much amount of time also, because in the examination you don't need to write all these steps, right? You don't need to write all these steps. Just what you do is simply, I will draw these sequence networks and I will find out VA1 0.6 per unit, VA2 also 0.6 per unit only. Then what is phase A voltage? VA0 plus VA1 plus VA2. Phase A voltage is 1.2 per unit. And what is phase B voltage? VA0 plus alpha square VA1 plus alpha into VA2. That's common. So it will come minus 1. It will be minus VA1. So like that you can do it a bit in a quick manner whenever you familiar with these types of problems. Okay. Yeah, VA2 is 0.6 per unit only. Kindly check it. VA2 value was plus 0.6 per unit only. Kindly check that one again. Okay, so this ends the double line fault analysis. Let's move to double line to ground fault now. Double line to. You have to see once. I am saying you already. No, sir, see once means I have asked you to cross check, right? Please cross check once again. Next, double line to ground fault. Double line to ground fault I am going to take up. Yeah, okay. Here it is IA2 minus. Okay. IA2 is negative of IA1. Negative of IA1 means plus J2. IA2 current is negative of IA1 plus J2. Yeah. Next, we will be moving with the double line to ground fault. Double line to ground fault. We'll call it is LLG fault analysis now. Double line to ground fault, or you can say LLG fault analysis. Abjit, I corrected it. Please go with that. Actually, I don't need to calculate that VA2 also, as we know already VA2 and VA1 values are exactly equal. Okay. Double line fault in delta, it will be similar. Why you are bothering about that, Jadhav Pradeep? Double line fault in delta, it will be similar. You have to draw positive sequence network, negative sequence network, connect in parallel. That's it. Okay. See, again, as we are saying many times, in case of double line to ground fault also, first I will be starting the analysis with a alternator like this, right? So this is one alternator we have. So this was the alternator and neutral, and these are the outcoming terminals we have. Outcoming terminals. Yeah, so this neutral I am connecting to ground with an impedance of Zn, neutral impedance. And these are the terminals I am calling ABC, outcoming terminals. And these are internal EMFs we have, EA, EB, EC. EA, EB, EC internal voltages. Terminal voltages, let us say VA, VB, VC here. And outcoming currents are IA, IB, IC. Outcoming line currents are IA, IB, IC. Cross check that, Sri Divya. Please cross check it, Sri Divya, quickly. VA1 value, you are saying some mistake. Yeah, look here. Look here in this. Pre-fault condition will be as it is, no load operation only. All the three currents are zero. Terminal voltages will be equals to internal voltages. Okay, so I'll write quickly pre-fault conditions. Pre-fault conditions, no load. No load. All the three currents are exactly equals to zero. Not only that, terminal voltages are nothing but internal voltages here. Okay, terminal voltages are nothing but internal voltages, and these are balanced voltages. Okay, so EA1 will act as a pre-fault voltage, positive sequence, which is not equals to 0. EA1 value equals to EA, you can write. Pre-fault voltage is that. And EA2 number 0 and EA0 number is also 0. This we explained many times till now. This we have explained many times till now. Okay. Why we are doing fault analysis only in the no load operation? Why we are doing fault analysis only in the no load operation? Your practical system is a loaded system, right? Practical system is a loaded system. It's not in the no load. As we said in case of superposition principle. Superposition principle, first we'll calculate the load currents before occurrence of short circuit. In the next case, I will do the fault analysis under no load operation. Then whatever the fault component currents you have and pre-fault current, so-called load current you have, you add them together. That is the resultant current flow in the system whenever you have a short circuit fault. That's what the superposition principle which we discussed at the beginning itself. Before starting the LG fault itself, we have studied about loaded alternator, loaded system, short circuit fault. Where we have done pre-fault condition, we have a load current. Then we have take only fault without any load, means no load operation fault. And we have done the fault currents as well as line currents calculation. And if you have a fault on a loaded system, we have to add that load current with the fault component current. That will give you the resultant current. Okay, pre-fault current means that they will give in the data if they want to know. They will give in the data definitely. So now our interest is to find the fault component of current during the no load operation. That's what we are exercising here. That's why most of the times we used to do fault analysis in the no load operation. Yeah. Next, let's move. Double line to ground fault on BC conductors I am going to call. Solid double line to ground fault on the BC conductors like this. Double line to ground fault. Okay, so I will move with the next slide. LLG fault, solid LLG fault on BC conductors. On the BC conductors. Okay, look here. We have solid LLG fault on BC conductors. Immediately, B is connected to ground and C is also connected to ground. Na? B point is connected to ground. C point is also connected to ground. So obviously this VB and VC values will come to be 0. Phase B voltage will be 0 and phase C voltage also comes to be 0. This you can write. This you can write. What about the phase A voltage for you? What about the phase A voltage? It's not connected to any point. We don't know that. It's an open circuit. We don't know the value of VA, I can say. VA may not be equals to 0. So voltages are obviously unbalanced. Voltages are obviously unbalanced. Okay, now you think about currents. See, still line A was open, so IA equals to 0. Line A was open, so IA equals to 0. And you know here, IB non-zero, IC non-zero. Some of these two currents, IB and IC, will be flowing into the ground. So the ground current is nothing but B plus C currents. B plus C currents. Let me write here. Phase A current is equals to 0. Phase B current not equals to 0. Phase C current not equals to 0. But you know, summation of these two currents is a ground current. Ground current. See, listen here. Particularly in this case, in case of double line to ground fault, whatever the ground current we have, that we are going to treat as fault current. Ground current itself we are going to treat as fault current here. So fault current is nothing but summation of B and C currents. Okay. Now you simply make this comment that the system is unbalanced after the fault has been occurred. System is unbalanced after the fault has been occurred. Now you apply the symmetrical components here. You apply the symmetrical components for this one. First you take up the voltages in symmetrical components, then you think about the currents. Let me take up the next slide. Symmetrical components for voltages. Symmetrical components for voltages. Just you write that matrix VA0, VA1, VA2. Okay, so this is equals to 1 by 3, 1, 1, 1, 1 alpha, alpha square, 1 alpha square alpha multiplied with this matrix here, VA, VB, VC. Multiplied with that matrix, VA, VB, VC. VA value, we don't know. We have to keep as it is. What is VB? 0, because B conductor was shorted. What is VC? 0. C conductor was shorted. Now, what you will get the value of VA0 from this now? What you get the value of VA0 from this? 1 by 3, VA plus 0 plus 0. So, 0 sequence voltage value was VA by 3. What is positive sequence voltage? VA1. 1 by 3. VA plus 0 plus 0. So, it is again VA by 3. Negative sequence voltage VA2. 1 by 3. VA plus 0 plus 0. So, this value is also VA by 3. Means what's the comment you can make from this now? All the three sequence voltages are exactly equal. All the three sequence voltages are exactly equal. That is nothing but VA by 3 from this relation. VA by 3 from this relation. Okay, tell me all of you. If all the three sequence voltages are coming equal, how we have to connect the three sequence networks? How we have to connect the three sequence networks? Definitely, the three sequence networks should be connected in parallel to make sure that all the three sequence voltages are exactly equal. Okay, fine. Okay, let me think about the sequence components for currents also. Sequence components for currents. One single statement I will tell you with respect to currents here. IB is non-zero, IC also non-zero. But one thing, IA equals to 0, na? IA current equals 0. What's the meaning of that? IA equals to 0. IA0 plus IA1 plus IA2 is equals to 0. Sum of the three sequence currents of phase A is equals to 0. That you can treat as relationship. Okay, you no need to go for equations and all further. Okay, so I can write as IA value is equals to 0. As that current IA is equals to 0, you can write IA0 plus IA1 plus IA2. Summation of the three sequence currents will be equals to 0. summation of the three sequence currents will be equals to 0. Okay, done. Now you draw sequence networks, give the connection, and you can do the network analysis further. So moving with the next slide to take up the sequence networks and all. Sequence networks connection. Sequence networks connection. Okay, so this is a positive sequence network. To neutral. Default voltage is A1. Positive sequence impedance Z1. And this is a terminal positive sequence voltage as VA1. Current I am saying as IA1. Negative sequence network, we can show like this. Neutral. And this is Z2. And this terminal voltage I am saying as VA2 here. And this current is IA2. Negative sequence network. Zero sequence network. Up to neutral, we can keep Z0. Neutral to ground, we can keep 3 times of Zn. 3 times of Zn. Like this will have. And this is the zero sequence voltage VA0 and current we have as IA0. Clear? Now we have to connect these three in parallel as we are saying, because all the three sequence voltages are equal after the fault has been occurred. After the fault has been occurred. So by connecting these two in parallel, VA1, VA2 are exactly equal. And the value of VA0 and VA1, VA2 are exactly equal. Okay. So voltages condition we have satisfied. Now we should think about the currents condition also. This is the current IA1 entering, IA2 going in this way, IA0 going in this way. And if you stand at this node, all the three sequence currents are coming towards that node. All the three sequence currents are coming towards that node, and sum of the three sequence currents will be equals to 0. Okay, so I can call IA0 plus IA1 plus IA2, IA0 plus IA1 plus IA2. This summation is equals to 0. IA0 plus IA1 plus IA2, that summation is equals to 0. Already we have, we got that condition with respect to IA equals to 0. So if you want to write three sequence networks connected in parallel. Connected in parallel. In parallel. Three sequence networks connected in parallel. Next. Let's do network analysis of this. You can redraw this network in your flexible way and you try to find out IA1 correct. After that, you go for IA2 and IA0 currents, and then VA1, VA0 voltages. Okay. First, I will say sequence currents calculation. Sequence currents calculation. Okay, I am redrawing that network in the flexible way as I have mentioned. Like this is Z1, and this is your default voltage as EA1, and this is Z2, negative sequence impedance, and we have here Z0 and then 3Zn. Z0 and then 3Zn. Yeah. And this is the current IA1 you have. Current IA1. See, you know, this Z2 and Z0 plus 3Zn are in parallel. Z2, Z0 plus 3Zn are in parallel. That will come in series with Z1. So EA1 by that whole impedance value will give IA1 current. So positive sequence current IA1 is equals to voltage here EA1 by equivalent impedance seen by the voltage sources. Z2 in parallel with Z0 plus 3Zn, that's one number. That whole impedance will be in series with Z1. So you can have Z1 plus Z2 in parallel with Z0 plus 3 Zn. Like this, we are going to get the positive sequence current, IA1. Okay, this is a current IA1. Next, what is this current IA2? It's a negative sequence current coming out from Z2 impedance. Means coming out from the negative sequence network, you can say. Okay. See, by doing current division, we are capable to get it actually. So IA1 divided between these two branches will give the two branches currents. For example, if you want to get this Z2 branch current, IA1 into opposite impedance Z0 plus 3Zn by summation Z0 plus 3Zn plus Z2 we have to write. But from that current division technique, whatever the current you obtain, that's the current going down. That's the current going down. But we need the current coming up. So we have to keep minus sign. Okay. So I can say here from this IA2 current, if you write, which will be minus IA1 into Z0 plus 3Zn value by Z2 plus Z0 plus 3Zn, just from current division principle. IA1 into opposite impedance Z0 plus 3Zn by summation of two impedances. That's the current going down in the Z2, but we need current coming out. So I have to keep the minus sign for that. Okay. What is the zero sequence current IA0? In the similar way we should do by current division technique, you can say the zero sequence current IA0 as again IA1 current into opposite impedance is Z2 by the total impedance will be Z2 plus Z0 plus 3Zn. But again, this IA0 current is going down, but we need current coming out. So we have to keep minus sign for that current. You have to keep the minus sign. Yeah. So by this way, you are capable to get the currents as IA1, IA2, IA0, all the three currents. See, after getting these currents, these three currents, we will try to find out ABC currents here. What are the currents flowing in the outcoming terminals of alternator, A terminal, B terminal, and then C terminal. Later on, we think about what is the current flowing in the ground. We will make that comment on the fault current also. Okay. So ABC currents, if you think here, ABC currents, if you think. Okay. Yeah. Just look here. ABC currents. First, IA current, which is nothing but summation of IA0, IA1, IA2. This number will be 0. IA0, IA1, IA2, that number will be equals to 0. What is the phase B current here? What is phase B current? That is IA0 plus alpha square IA1 plus alpha into IA2. I can't extend this equation further. Only one suggestion what I will make is, if you have double line to ground fault analysis in the problem, you draw the three sequence networks in parallel, find out IA1, IA2, IA0 currents. After getting those currents, substitute in the B current equation, you will get IB. That's it. What is current in the phase C? Current in the phase C. IA0 plus alpha into IA1 plus alpha square into IA2. Again, I will make the same comment. Calculate the sequence currents from network analysis. Substitute those currents in the current IC equation. We will get that current value, IC value. Okay. Yeah, is it audible to all? Somebody is saying it's not audible. Is it audible to all? Please tell me. Yeah, audible. Good, good. It's audible. Sarath, please cross check your system. Yeah, let's continue. These are ABC currents. Okay, now let's make the comment on the fault current also here itself. Then we will think about the voltages. Fault current is nothing but ground current already we said, na? Fault current is nothing but ground current we said already in this type of fault. Fault current, IF, is nothing but ground current. What is that in your expectation? Anybody tell me please? What is that ground current in your expectation? What is the ground current in your expectation? 3 times of zero sequence current. Ground current is nothing but 3 times of the zero sequence current. That's it. Always, wherever you go, if they are asking what is ground current, what you should say? 3 times of the zero sequence current. Yes or no? Now we have to prove. But according to the analysis, what we have done, we got this current as summation of B and C currents. B and C currents. I'll try to extend this equation to prove that current has 3 into I and R. Okay. So IB plus IC if we take, means you should take summation of these two. Summation of these two. Kindly observe. I am writing directly. Kindly observe. Summation of these two. IANR plus IANR. 2 IANR. IA1 common. Alpha square plus alpha. IA2 common. Alpha plus alpha square. Next one. 2 IANR. In this, alpha plus alpha square is common. You will get IA1 plus IA2. IA1 plus IA2. What is alpha plus alpha square? Minus 1. So it will be 2 IA0 plus or minus 1. I'll say minus IA1 plus IA2. 2 IA0 minus of IA1 plus IA2. Getting? Already we know that IA1 plus IA2 plus IA0 is equals to 0. So IA1 plus IA2 you can replace with minus IA0. I'll write. Please you complete this one first. Please complete this one quickly. So once after completion, please raise your hands. Okay, yeah. So as we know, IA1 plus IA2 plus IA0 is equals to 0. Obviously, zero sequence current value will be minus IA1 minus of IA1 plus IA2. Else, in the reverse manner, IA1 plus IA2 is equals to minus IA0. That's a better one by which you can substitute this directly into the calculation of fault current. So therefore, fault current is nothing but 2 times of zero sequence current minus of IA1 plus IA2 is minus IA0. Minus was cancelled. It will be 3 times of the zero sequence current, which we said earlier. Said already. Okay. Yeah. So if you look into that diagram, 3-phase network with a double line to ground fault just once, just look here. See, whatever the current flowing in the ground, you have, that will be flowing in the ground and flowing into this neutral, flowing into this. Yeah, so flowing into this neutral. So of course, you know that neutral current is nothing but 3 times of zero sequence current only. Neutral current is nothing but 3 times of the zero sequence current. Ground current also in the similar manner what we have mentioned. Yeah, next. So next we'll think about voltages quickly. Sequence voltages from this circuit analysis. VA1 nothing but EA1 minus IA1 into Z1. VA2 minus IA2 into Z2. VA0 minus IA0 into Z0 plus 3Z. That's it. Those equations I will write quickly. Sequence voltages. Sequence voltages. Okay. So first VA1 value EA1 minus IA1 into Z1. VA2 value minus IA2 into Z. Next, VA0 value, which is minus IA naught into Z naught plus 3ZM. Z naught plus 3ZM. IA naught value minus IA naught into Z naught plus 3ZN. Sequence voltages. Now, if you want to get the ABC voltages, just if you follow the equations, what we have discussed till now, ABC voltages, you write ABC voltages. What is phase A voltage? VA0 plus VA1 plus VA2. Summation of zero sequence, positive sequence, and negative sequence. And this is nothing but all the three sequence voltages are equal. So you can write this as either 3 times of zero sequence voltage, or 3 times of positive sequence voltage, or 3 times of negative sequence voltage. Like that you can write. Either it is 3 VA0, or you can say 3 VA1, or you can say 3 VA2. What about the phase B voltage? We mentioned it is 0. Phase C voltage also equals to 0 because BC are directly connected to ground. So we can say phase B voltage is 0, phase C voltage is also 0. Both phase B and phase C voltages will be 0. Okay. So next we'll take up quickly double line to ground fault with fault impedance. Means with ZF not equals to 0. Double line to ground fault with fault impedance, or you can say ZF not equals to 0. How to find VA naught? That equation I am saying, right? Minus IA naught into Z naught plus 3ZN. Okay, what is the doubt you have again here, anonymous attendee? How to find VA naught? What is the doubt you have again? I'm going in a sequence. I'm not saying you anything direct, which I feel. If you are following class thoroughly, definitely you will also feel that I'm not saying anything directly. Yeah, so let's take up the next thing, that is double line to ground fault with ZF not equals to 0. LLG fault with the ZF fault impedance not equals to 0. ZF value not equals to 0. Yeah. Let's see here. Again, we'll take up the alternator. Again, we are going to take up the alternator in the similar way, right? Pre-fault conditions are as it is. Let me copy the diagram if possible. This alternator only we are taking up. Yes, let me draw better. Alternator with certain sequence impedances. Positive, negative, and zero sequence impedances. Neutral, and it is connected to ground with an impedance of Zn, we are saying. And these are outgoing terminals, ABC. And the terminal voltages are VA, VB, VC. And currents are IA, IB, IC. And internal voltages here, EA, EB, EC. The generator, internal voltage of the generator, EA, EB, EC. Like this. Pre-fault conditions are as it is. You no need to write them. If you want, I will copy those pre-fault conditions. You no need to repeat them. Okay, so these are the pre-fault conditions here. Now we have a double line to ground fault on BC. We are saying with fault impedance. Okay. See, anywhere in the examination or in the textbook, anywhere, if you find this type of statement, double line to ground fault with fault impedance not equals to 0 means Listen, all of you. Don't ask me again why you have connected ZF in this place only, not in the other place. Look here carefully. In the exam or anywhere, if they said that double line to ground fault with fault impedance not equals to 0 means you should short this BC together first. B and C have to short together first, and then whatever the fault impedance you said in the problem, that you should connect between this to ground lines. Between the short to ground, you have to connect the fault impedance. This is a way of keeping the fault impedance in the problem. Okay. And whatever the current this is carrying, that we are treating as fault current, of course, that is nothing but ground current only. That's nothing but ground current only. How much is that value? 3 into 0 sequence current in terms of symmetrical components. Now, we write the conditions, whatever we have after the fault has been occurred. We are going to take up the conditions, what we have. The faulted condition. LLG fault on BC conductors. BC conductors. Of course, you know that A is already open, means current IA equals to 0. B will carry some current, C also will carry some current. We don't know about them. Okay. So current in the phase A conductor is 0. It is open. B current, definitely it will exist. C current, definitely it will exist. Not only that, IB plus IC, that whole current is going into ground. That itself we are going to name it as fault current. That itself we are going to name it as fault current. Okay. Next thing. Voltages you think. VA. It's open. So A voltage is non-zero. A is open. So phase A voltage is non-zero. What about B and C? B and C. VB and VC are equal. Because both are shorted, right? VB and VC are exactly equal, but not equals to 0. Not equal 0. Equals to how much now? That is nothing but IF into ZF. Because BC, both voltages are equals to IF into ZF from this circuit analysis. So I can say B and C, both voltages are equal to fault current into fault impedance. So obviously the overall system is in the unbalanced state only. Yeah, that's what I am saying, anonymous certainty from many times, right? How we have to treat that ZF means we have to short BC together and we have to keep the fault impedance between that combination to ground. That's what I am explaining you many times. Yeah, kindly listen to me. Kindly listen to me. See, which equations looks to be similar with fault impedance and with zero fault impedance? With zero fault impedance and with non-zero fault impedance, which equations are looking same? Again, it will be current equations, right? Again, it will be current equations. So, if you convert these currents into symmetrical components, as you know already IA equals to 0, you can confirm that IA0 plus IA1 plus IA2 value equals to 0. Okay, as phase A current is equals to 0, you can confirm that IA0 plus IA1 plus IA2 value equals to 0. And what is fault current here? What is fault current? IB plus IC, which is 3 times of zero sequence current. Fault current is nothing but 3 times of zero sequence current. Now, we should put our effort. We should exercise about these voltages. Sequence voltages, we should exercise little bit more. Okay, let us take up. Symmetrical components for voltages. Symmetrical components for voltages I am going to take up. Symmetrical components for voltages. So you can write VA0, VA1, VA2 sequence voltages 1/3, 111, 1 alpha alpha square, 1 alpha square alpha multiplied with voltages. You have VA, VB, VC. VA, VB, VC. You keep that VA as it is, you don't change it. VB also you keep as it is only, but VC you can replace with VB. VC you can replace with VB. We said just now because VB and VC are equal here. So in place of VC, you can keep VB. And what is VA naught from this now? What's the zero sequence voltage? 1 by 3 VA plus 2 VB. VA plus 2 VB. What is positive sequence voltage? Observe here. 1 by 3 VA plus alpha VB plus alpha square VB. In the yesterday class for line-to-line fault also we have done similar things, I think. In the line-to-line fault also we have done the similar things, and this you can rewrite it as 1 by 3 VA. You take VB common, alpha plus alpha square, that is -1. So VA minus VB we are going to get. That's a positive sequence voltage VA1. What is the negative sequence voltage VA2? We can write 1 by 3 VA plus alpha square VB plus alpha into VB again. Okay, again you take that VB common, alpha plus alpha square you can get. So 1/3 VA minus VB we are going to get. Means ultimately what you can write from this will be positive and negative sequence voltages are exactly equal. Positive and negative sequence voltages are exactly equal. Means we have to connect the positive and negative sequence circuits exactly in parallel. Positive and negative sequence circuits exactly in parallel. Now we should get the relationship between zero sequence voltage and the positive sequence voltage value. We have to get the relation between zero sequence voltage and positive sequence voltage to have the connectivity, or to know the connectivity between the zero sequence network and the positive negative sequence networks. Okay, let's take. Already I said VB equals to VC, IF into ZF now. If VB equals to IF into ZF, we can take now. I will expand that one further. As we know already, phase B voltage is nothing but fault current into fault impedance. Fault current into fault impedance. Let's take that VB, VA naught, alpha square VA1, alpha VA2. What is fault current? 3 times of the zero sequence current. 3 times of the zero sequence current. Fault current is 3 times of zero sequence current. Next thing. Already you know just VA1, VA2 are equal. So in place of this VA2, you can keep VA1. And you take that VA1 common. So you have VA naught plus, if you take VA1 common, you get alpha square plus alpha 3 into IA naught into fault impedance. That alpha square plus alpha, this number is -1. And if you keep that, finally you can get zero sequence voltage minus positive sequence voltage as 3 times of zero sequence current into ZF. 3 times of the zero sequence current into ZF. Okay, so immediately in the next slide, we'll take up the 3 sequence networks and we'll try to give the connection between these 3 networks. Because we got the relationship between all the things. All symmetrical components, we got the relationship. Yeah. So I'm taking up in the next slide, sequence networks. Sequence networks connection. Networks connection. Simple. First, we should draw a positive sequence network, negative sequence network, zero sequence network. I will repeat it. This diagram only I will copy because I have all these available. All these things are available in this. That's why I'm copying this diagram. Sequence networks only I'm going to take without connections, right? These are the 3 sequence networks here. Positive, negative, and zero. Carrying currents of IA1, IA2, IA0. IA1, IA2, IA0. Next, first condition. Listen all of you. Look here. First condition. VA1, VA2 are equal. Means positive and negative sequence networks are exactly in parallel. VA1 equals to VA2 means positive and negative sequence networks shall be connected in parallel. Shall be connected in parallel. So I will connect these two in parallel. Connected in parallel. Okay, next. VA0 minus VA1 is equals to 3 into IA0 into ZA. See, means we have a relationship between zero sequence voltage and positive sequence voltage, but those two are not equal. We have a relation. We have a relation between VA0 and VA1, but these two are not equal. So, see, obviously, this point voltage what we have is nothing but either VA1 or VA2, and this point voltage is a VA0 value. You can join these two together, but not in a short term. You can join these two with some impedance. To follow that condition, or to satisfy that condition what we have obtained, I am keeping some impedance between these two. Keeping some impedance between these two. Okay, so this is the current flowing here, IA0. That's the current flowing IA0. And what is the relationship between VA0 and VA1? VA0 and VA1. So VA0 minus VA1 equals to IA0, 3 IA0 into ZF, na? 3 IA0 into ZF. That I will write as IA0 into 3 times of ZF. It will be same. So this impedance what we have here, I will be keeping as 3 times of the fault impedance. I will be keeping that impedance as 3 times of the fault impedance. Zn is there. I connected Zn. Why you are bothering about Zn, Abhinandan? I connected Zn, right? 3 Zn. Have I shown it in this diagram? Yes, I have shown it. 3 Zn. Yeah. So this is a way of connecting the sequence networks of a double line to ground fault with a fault impedance. With a fault impedance. Yeah. Tell me, please. Tell me, in this case, I don't write any equations. I don't write any equations. Just simply do network analysis from this one. Find out positive, negative, and zero sequence currents, and find out the required things, whatever he is asking in the problem. Whether he is asking fault current value, or sequence currents, or whether he is asking about sequence voltages, that you have to calculate. Okay? Yeah. So you can say if you want fault current is 3 times of zero sequence current. So you find out the zero sequence current from this network analysis, and 3 times of that will give the fault current. I don't extend this one further. I don't extend this one further. Okay. Next thing. So I'm going to take up 3 things as we have done in the earlier fault studies also. First one is a generalization. Generalization I'm going to do. Next one, I'll take up what we call circuit breaker rating calculation. Circuit breaker rating calculation. Then we will see fault level calculation. Fault level calculation. Simple. Generalization. Generalization. So generalization means we have some big power system network, something like this. So this is some system we have. This is a line and transformer connected, and this is another system we have. And here also we have another system, something like this we have. A big power system network consisting of number of transformers, transmission lines, and then generators. And this is the location of fault. That's the location of short circuit fault. Okay. So with a LLG fault with fault impedance. LLG fault with fault impedance. With fault impedance. See, you have to calculate first with respect to fault location. First, we have to calculate pre-fault voltage value with respect to fault location. First, we have to calculate pre-fault voltage value. Okay, pre-fault voltage, positive sequence, and we have to calculate positive sequence Thevenin impedance value, negative sequence Thevenin impedance value, zero sequence Thevenin impedance values. These three things we have to calculate: Z1 equivalent, Z2 equivalent, Z0 equivalent. So with respect to the fault location, whole network in the positive sequence form, can be redrawn simply like this. This is the pre-fault voltage, and this is a positive sequence Thevenin impedance. Like this, we can draw the whole network in the positive sequence network form. Again, with respect to the fault location, with respect to the fault location, the whole network you can redraw into negative sequence network form, Thevenin equivalent network, as Z2 equivalent like this, and this is a fault location. Again, the whole network what you have, zero sequence network what you have, that we can redraw into its Thevenin equivalent model in zero sequence like Z0 equivalent, and this is a fault location. This is a neutral off system. It's a neutral off system, but this is ground, or you can say zero potential terminal. Now, as you know already, as we have done this double line to ground fault analysis already, we have to connect positive and negative sequence circuits in parallel. Between this parallel combination and zero sequence network, we have to keep the 3 times of the fault impedance. And whatever the current flow you have in this zero sequence network, that is IA0, 3 times of that is a fault. Fault current is nothing but 3 times of zero sequence current. That's it. Simply do network analysis, find out zero sequence current, multiply that with 3, you will get the fault current number. Okay. Pre-fault voltage, generally they will give in the problem. You no need to bother about that value, pre-fault voltage value. Yes, why you are asking this type of doubt, anonymous certainly? Why is neutral of positive negative sequence network connected to ground? Already we are saying all are zero potentials. Neutral is zero potential in the positive sequence. Neutral is zero potential in the negative sequence. Ground is zero potential in zero sequence. I am shorting them. What is the doubt in that again? Yeah. So let's move ahead. Next I'm going to take up breaker rating, circuit breaker rating calculation based on what we call double line to ground. Circuit breaker rating selection. CB rating selection. Based on LLG fault we are doing. Earlier we have done this CB rating selection based on LG fault, CB rating selection based on LL fault. Now we are doing that based on double line to ground. That's simple, very simple. Just I am taking one simple network to explain you about this one. Star connected generator with 3 wires coming out like this. These are the phase conductors. You can call ABC here. ABC conductors. And I am showing one 3-phase circuit breaker here, something like this. 3-phase circuit breaker like this. Now you have a double line to ground fault on BC. Double line to ground fault on BC like this. B and C are shorted to ground. B and C are shorted to ground. Yeah, unloaded only, Siva. Okay, please tell me. Anonymous attendee means we have many anonymous attendees here, not you. Look here. This phase A current is 0 here, open. B is carrying some current as IB. C is carrying some current as IC. And the summation is going into ground, named as fault current. And this is your circuit breaker. This box, what I have shown is a circuit breaker. Tell me. CB rating formula, 3-phase rating of circuit breaker. 3-phase rating of circuit breaker formula, 3 into phase voltage rated value in kilovolts multiplied with what? 3 into phase voltage in terms of kilovolts multiplied with what? Yeah. Tell me please. 3 into phase voltage in kilovolts multiplied with what? Which current I should consider now? Which current I should consider? Is it fault current or IB and IC? You no need to consider the fault current. You no need to consider the fault current. What the current carried by the breaker here? IB and IC only, right? Fault current is going into the fault, not going into your breaker. That's why many times, maybe in the examination sometimes, listen please, listen all of you. Maybe in the examination, the people used to ask you what is fault current value, what is fault current value. But I can't do anything with the value of fault current, what you calculate, strictly speaking. Strictly speaking, I can't do anything with the fault current value what you have calculated. What I have to concentrate is, during a particular short circuit, what are the currents carried by the lines? What are the currents carried by the lines? That only we should think majorly, because whatever the current carried by the lines you have, that's the current what the breaker has to interrupt. Okay, so that's why I can say 3 into V phase in kilovolts multiplied with maximum of IB and IC currents in kiloamps. Maximum of IB and IC currents in terms of kiloamps. Okay. So if you want to write this in a different manner, maybe voltage in per unit, current, maximum of IB comma IC per unit multiplied with S base 3 phase. Already we removed the 3 na. So 3 into S base per phase you get, that will come to be S base 3 phase. Like this you can conclude. You no need to extend it, because I don't know exactly what is the equation. What is the equation for the IB? I've shown breaker already. I've shown this breaker already. This is the breaker symbol I've shown in the diagram. Okay, let's take up the fault level formula. Fault level formula, simple. Fault level or short circuit MVA formula. Fault level or short circuit MVA formula. 3 phase number we are going to give. Fault level, 3 phase number. You know, it is pre-fault voltage per unit number, fault current magnitude per unit number into S base 3 phase. Here you get a clear discrimination. What is that fault current in per unit? IB plus IC magnitude in per unit form. Okay, so where in this double line to ground fault particularly, IF per unit is nothing but 3 into 0 sequence current magnitude in the per unit form. 3 into 0 sequence current magnitude in the per unit form. Okay. Fault level is giving an indication only with respect to fault current value. Breaker rating calculation is a bit different. Breaker rating calculation will be a bit different. Okay, tell me now, tell me again. Based on what? Based on what? The severity of the fault is going to be decided in the system. Based on what? The severity of the fault is going to be decided in the system. Is it based on the line currents IB and IC or the fault current? Based on what current we have to decide the severity of the fault now? Is it based on IF value or IB and IC? IB and IC. IB and IC. Yes or no? IB and IC. Because those are the currents which are flowing into your alternator, causing a damage for the alternator, right? Fault current is not flowing into your alternator. After all, it may be flowing into your neutral of alternator, but that's not flowing into the windings of alternator. What will be current flowing in the windings of alternator? IB and IC. Because based on these currents, IB and IC only, we have to decide the severity of it. Okay? Yeah. Fine. This is the end of the double line to ground fault also. Let's take up 1 or 2 problems quickly on this one. And then we will move on to the 3 phase short circuit fault. Okay. So So let's take in the next slide problems on this. So I'm showing this problem, double line to ground fault. Yeah. So, small modifications I have to make. Yeah, read this question. A 50 Hz 13.2 kV 15 MVA alternator. Yeah. 13.2 kV 15 MVA alternator. X1 equals to X2 20%, means you can treat that as 0.2 per unit. Xg not 8% means 0.08 per unit. And its neutral is grounded through a reactance of 0.05 per unit. Sometimes these neutral reactance or neutral resistance, they may give in ohms. Neutral reactance or neutral resistance may give in ohms. We should be very clear in what units it is given here. It's in per unit here. Clear. Okay. Determine symmetrical RMS current. Symmetrical RMS current in the ground in kiloamperes for double line to ground fault occurring on phase A and B. Phase A and phase B. Till now, on what phases we have studied the double line to ground fault? B and C we studied, but now in the problem I am saying that the fault is on A and B conductors. Okay. The generator is operating at a terminal voltage of 13.9 kV before the fault taking place. Before the fault taking place. Okay. Yeah. So let's say in the next slide, solution. So this is the alternator. We have three-phase alternator like this. So these are the conductors ABC. ABC I am showing. Next thing. From the data given, it's a 50 Hz alternator. 13.2 kV line to line voltage. And what's the MVA rating of this one? 15 MVA. 15 MVA three-phase rating of this alternator given. And next reactances X1, X2, both numbers are exactly equal. That will be 0.2. Zero sequence reactance of this is 0.08. Alternator neutral is grounded with a reactance of Xn, and that Xn value was 0.05 per unit. Xn value was 0.05 per unit. Determine the symmetrical RMS current in the ground. See, you have double line to ground fault on AB. Double line to ground fault on AB, something like this. And you have to find out how much is this ground current in kiloamperes in terms of RMS. Of course, current in the sense we have to give in the form of RMS only, right? Right? We have to give this in the form of RMS only. And he said, what is the operating voltage before the fault occurrence? 13.9 kV. 13.9 kV is a pre-fault voltage line to line. Pre-fault voltage line to line is 13.9 kilovolts. 13.9 kV. Okay, how much is that per unit value? By choosing ratings itself as base values. We have to consider these ratings itself as base values. By choosing it, if you calculate the pre-fault voltage magnitude in per unit form, actual value 13.9 kV by base value 13.2 kV. See, if you want to write per phase, take in numerator 13.9 by root 3. Take in denominator 13.2 by root 3. Root 3 will be cancelled out. You will get some number. How much is this value? Value you are going to get 1.053 per unit. 1.053 per unit. That will be the pre-fault voltage. Now, we have fault on AB conductors, right? AB conductors. How to do this fault analysis? Just the same logic what I said you have to follow. Earlier, you have fault on BC. You got the symmetrical networks in terms of A. You got the sequence networks in terms of A in your analysis. Now, if the fault is on AB, you are going to get the sequence networks in terms of the phase C. Okay, so for this particular fault, I'm going to say sequence networks connection. This is a positive sequence network of phase C. Negative sequence network of phase C. And you see zero sequence network of phase C now. Impedances will be remain same. Positive sequence impedance in all the three phases is equal. Negative sequence impedance in all the three phases is equal. Zero sequence impedance in all the three phases is also equal. Z0. And here it is 3 times of Zn and this is a ground. 3 times of Zn and that is ground. Okay. Yeah. So you have to connect these three things in parallel because he didn't mention anything regarding fault impedance in the problem. So you can simply join these three in parallel like this. Okay. And this is a current IC1, you can say positive sequence current. And this is a negative sequence current IC2. And you call this a current IC0. IC0. Whatever the IC0 you have, 3 times of IC0 is nothing but ground current. 3 times of IC0 is a ground current. Yeah, did he mention anything regarding reference in the problem? Anything regarding reference? Nothing. So I will assume now, phase C pre-fault voltage as a reference. Phase C pre-fault voltage itself I will take as reference. So I don't have a confusion with 120 degree minus 120 degree and all. Okay. So this pre-fault voltage of phase C, what you have, this itself we will be taking as the reference. That itself I am taking as reference. Okay. Now you can keep these numbers quickly. What is x for x2 0.2? So this number is J0.2. This is also J0.2. X0 is J0.08 and 3 times of Zn is J0.15. And you redraw this network and try to find out the IC0 current. Okay, first IC1 current you try to calculate. IC1 current, if you want to write phase C pre-fault voltage is assumed as reference. Okay, so you can call the pre-fault voltage value in the phase C 1.053 at an angle of 0 degrees. Let's continue. IC1 pre-fault voltage 1 at an angle 0 degree by this equivalent impedance J0.2 Z1 plus Z2 in parallel with Z0 plus 3 Zn. Z0 plus 3 Zn value J0.23. That series combination J0.23. So J0.2 in parallel with J0.23. J0.2 into J0.23 by J0.2 plus J0.23. Yeah, you please calculate this current IA1. Sorry, IC1 current. Yeah, I am really sorry. Pre-fault voltage is 1.05. 1.053 is a pre-fault voltage. 0.5. Okay. You tell me this value. How much? How much is this value? Minus J. The J is very costly. Don't forget about J. Sai Pranit, don't forget about the J. If you are giving the answer, please give with the J symbol only. The final answer, what is asking? That you can give in magnitude at the end. But you don't keep the magnitudes in between your steps. Okay? You keep whatever the value you get along with J. Minus J 3.43. Minus J 3.43 per unit. This is IC1 current. IC1 current. Now, what current we need to have? IC not, because we need the ground current. IC not current, nothing but minus IC1 into current division. Minus IC1 into opposite impedance. J.2 by J0.2 plus J0.23. So minus IC1 in the sense it is plus J 3.43 you can get. Numerator you have 0.2, denominator it is 0.43. J will be cancelled in the numerator and denominator. And how much is this value? How much will be this value? Anybody tell me please? Plus J. Almost 1 point something. 1 point something. 2.982. I don't think so. By doing current division. 1.595 per unit. Now, fault current value in per unit form is 3 times of zero sequence current. So 3 into J 1.595. How much is this in per unit? 3 into that number. So get J 4.786 per unit. 4.786 per unit. Now he is asking that current value in terms of kiloamperes, because he didn't mention the base values in the problem, right? He didn't mention the base values in the problem. Of course, he said here in the problem directly in terms of kiloamperes, means this you multiply with the base current. This you have to multiply with the base current. Calculate the base current. Calculate the base current from the base values we have selected. I base equals to S base 3-phase value by √3 into V base line to line. √3 into voltage base line to line. How much is that S base 3-phase number? Look at this S base 3-phase. 15 mega means 15 into 10 power 6 by √3 into V base line to line is 13.2 kilo. 13.2 kilo. Yeah, please tell me this number how much. 3 IC naught, 3 IA naught, both will be same. 3 IC naught or 3 IA naught, both will be same. Okay, fine. So what is this value? 3.193 kilo. Is it kilo? 656.1 amperes. 656.1 amperes, else you write 0.656 kiloamperes. So now you can call fault current in terms of kiloamperes, ground current in terms of kiloamperes. Per unit number J 4.786. Base current is 0.656 kilo. So how much is this in kiloamperes? How much is this value in kiloamperes? Anybody, please tell me the answer. 3.14 kiloamperes. J 3.14 kiloamperes. If he is needed only magnitude of this current in kiloamperes, you keep this answer as 3.14 kiloamperes only. You keep that answer as 3.14 kiloamperes. That is a fault current value. Or ground current also you can say. Fault current or you can say ground current. See, for example, in this problem what we have discussed till now, we have taken fault on phase A and phase B. Phase A, phase B fault we have taken. We got the fault current value as 3.14 kilo. For example, if we take fault on BC conductors, how much will be the fault current magnitude? If you have fault on BC conductors, how much will be the fault current magnitude? Will it be remain same? If the fault is taken on BC conductors, can we say fault current magnitude remains same? Yes, same. Why? Because Z1, Z2, Z0 values will be remain same. Your network will be remain same. Pre-fault voltages remain same. The angles may change little bit. Angles may change little bit according to the reference what you are choosing. According to the reference what you are choosing, angles may change, but still magnitudes will be unaltered. Magnitudes will be unaltered. Okay. Similarly, if you have the same double line to ground fault on AC, A and C conductors, if you have double line to ground fault on A and C conductors, then again you are going to get the same answer as fault current 3.14 kiloamps. Okay. So this is about double line to ground fault. We'll take one more problem on this, and then we will move to three-phase fault. One more problem we are going to take up in the next slide. Yeah. At this problem. Go through this. So go through this problem. It is available in your PDF file. Look at this question. Consider the following single line diagram in which all the apparatus are given in per unit form. All the apparatus reactances. Okay. In which the reactance of all apparatus are given in per unit form on the common base. Done. For a double line to ground fault on phase B and phase C at bus 3. At bus 3, we have a double line to ground fault on B and C conductors. Find the following things. He said generator, transformer line, positive, negative, and zero sequence reactances. First one is find the currents in the faulted phases. What are the faulted phases here? I have taken 13.9 kV only. Sivagopi, just go through that answer once. I have taken 13.9 by that value, 1.053 only I have taken. Okay. Yeah, look here. Find currents in faulted phases. What are the faulted phases here? Phase B and phase C. So simply you have to find phase B current and phase C. Next, find healthy phases, means non-faulted phase. What are the non-faulted phase? A, phase A. What is phase A voltage at bus 3? At bus 3, what is the non-faulted phase voltage? These are the two things you have to calculate in this problem. Okay, first, see if you want to do double line to ground fault analysis at this bus 3, first we should be ready with positive sequence Thevenin network, negative sequence Thevenin network, zero sequence Thevenin network. After getting the 3, we have to connect them in parallel and you find out the sequence currents what you get. After getting those sequence currents, we can find out the faulted phase currents, so-called phase B and phase C. Okay, so I'll show you in the next slide. Solution. First, I'll take directly because all reactances are in per unit form common base. Positive sequence network I am taking directly for the single line diagram given. Okay, so this is a single line diagram given in the data. First, generator, it's a bus 1. Generator, we are going to represent as voltage source in series with impedance. Like this, it's a neutral. And we have bus 1 to bus 2 transformer, means it is represented as a series impedance only. Like this. And then bus 2 to bus 3, we have a line also represented as a series impedance. Bus 3. Okay, you keep all these positive sequence impedances, what you have. Directly numbers you can substitute. Generator positive sequence 0.2, transformer 0.2, line 0.2. So 0.2, 0.2, 0.2, J.2, J.2, J.2. So it's a internal voltage. And you have to find Z1 equivalent with respect to bus 3. Z1 equivalent with respect to bus 3 we have to calculate. So with respect to bus number 3, faulted bus, positive sequence Thevenin impedance value. Means you should kill this source, what you have, kill this source. After killing the source, how much will be that positive sequence impedance? You can look now. J.2 plus J.2 plus J.1. So it will be J0.5 per unit. J0.5 per unit. Clear? Next one. Again, we draw negative sequence network. We find out Z2 equivalent in the similar way. I'll show in the next slide, negative sequence network. Please complete it quickly. So moving to the next slide. Negative sequence network. Negative sequence network. You can draw the same single line diagram what is given in the problem. It's a bus number 1. Generator. We represent this in negative sequence network as a simple impedance only, negative sequence impedance. Bus 1 to bus 2, it will be represented as series impedance, transformer. Bus 2 to bus 3, we have a line also represented as a series impedance in the negative sequence network form. So we'll keep all these numbers. Generator negative sequence reactance 0.3, transformer 0.2, line 0.2. So these numbers are J.3, generator, transformer J.2, line it will be J0.1. So now with respect to bus 3, we should find out the Z2 equivalent value. With respect to bus number 3, we have to find out the Z2 equivalent value. And you know all the 3 are in series, so it will be coming as J0.6 per unit. J0.6 per unit. That was a negative sequence Thevenin impedance with respect to bus number. Okay. Yeah. So next we have to draw zero sequence network of this in order to get zero sequence Thevenin equivalent impedance. Zero sequence network we have to draw. I'll say zero sequence network. So let me show the single line diagram first. Like this we have. So bus 1. First generator up to neutral, we have to keep zero sequence impedance of generator. Neutral to ground should keep 3 times of Zn. The Zn value 0 as it is solidly grounded. Zn value 0. So you can call the 3 Zn value as 0. What is zero sequence impedance of generator given in the data? That is J0.05. Zero sequence impedance is J0.05. Okay. Next, bus 1 to bus 2 we have a transformer. First you draw open diagram of this transformer. Open diagram of this transformer. And what is a zero sequence impedance of transformer? What is the zero sequence impedance of transformer? J0.2. Primary what connection here? Delta. Delta means you have to close the shunt switch on the primary side. Secondary, star ungrounded means you should keep this series switch remains in open mode. 3 Zn is equals to infinite. 3 Zn equals to infinite. Bus 2 to bus 3 we have a line. Bus 2 to bus 3 we have a line. So it is represented simply as series impedance. What is zero sequence impedance of line given in the data? J0.3. J0. Now, with respect to bus 3, if you calculate Z0 equivalent value. With respect to bus 3, if you calculate that Z0 equivalent value, how much is that number? With respect to bus number 3, Z0 equivalent value if you do, it will be open here. So it will be obviously infinite. Zero sequence Thevenin impedance value will be equals to infinite. Infinite. Kushal, How you get 0.5, Kushal? Huh? Open circuit, so it will be infinite. Fine. Now, see whether it is required to consider this zero sequence network into analysis or not. That's a secondary issue. No need to bother about it. Just to follow the fault analysis rules, whatever we said there. Particularly for double line to ground fault, we are talking about. Double line to ground fault. See, of course, pre-fault voltage you can treat as rated voltage only. That means 1 per unit, because he didn't mention that in the problem. In the previous problem, they said 13.9 kV that we convert into per unit domain, we get 1.053. But here he didn't give that pre-fault voltage value. So you assume that as rated voltage as 1 per unit. You write it if you want. Let pre-fault voltage is equals to 1 per unit, as it is not given in the problem. Okay. Now, sequence networks connection for double line to ground fault. Sequence networks connection for LLG fault. Double line to ground fault. Okay, just you can draw first positive sequence network here. Positive sequence network. Like this, you can say neutral. And then negative sequence network here. Neutral. And then zero sequence network I am showing up to neutral. We should keep the zero sequence impedance. Sorry, I'm really sorry. We have drawn already. We have found Thevenin equivalent impedance already. So zero sequence Thevenin impedance is infinite. So it will be open. Z0 equivalent value we calculate already. That is equals to infinite. So it will be open. This is the Z2 equivalent value and this is Z1 equivalent value. Thevenin impedances, and this will be the pre-fault voltage VPF. And Z2 equivalent, Z1 equivalent numbers you know already. Now, how we have to connect these three circuits? How we have to connect these three circuits? Can we omit the zero sequence network? Can we omit the zero sequence network in the analysis? Tell me, I need your response here. I need your response. Can we omit the zero sequence network in the analysis? No. Why it is needed to omit? You consider it. You consider it. If it is omitted, means that mathematical calculation will take care of that. Why you are doing that intentionally? Don't do that. As it is LLG fault, you have to connect all the three sequence networks in parallel. That's it. That's the thing you do first. Okay. So irrespective of what's the value of Z0 equivalent, we have to connect these three sequence networks in parallel. Solid LLG fault we are discussing. Like this, we have to connect. And let me show the notations quickly. Phasor notations. These are A1, A2, and this current we have A2, and this is VA0 voltage, and this current is IA0. How much is the current IA0 here? How much is the current IA0? How much is the current IA0? 0, because it is open circuit. This is open circuit, so obviously IA0 current will come to be 0. What's your intention in the first part of the problem? Find the currents in faulted phases. Means IB and IC currents you have to calculate. For that purpose, you should be ready with the values of IA1, IA2, and IA0. That's it. Okay. So first IA1 current I have to calculate. IA1 current to solve the first part of the problem. Positive sequence current IA1. What you can say that IA1? As it is open, this you can omit completely in the analysis. And then Z1 and Z2 will come in series now. Z1 equivalent, Z2 equivalent will come in series. So VPF by Z1 equivalent plus Z2 equivalent will give IA1 current. So IA1 current is nothing but pre-fault voltage value by Z1 equivalent plus Z2 equivalent. Okay. What is pre-fault voltage value? 1 at an angle 0 degree, as they didn't mention it. What is Z1 equivalent and Z2 equivalent? Z1 equivalent J0.5, Z2 equivalent J0.6. J 0.5, J 0.6. So it will come like minus J 0.9091, I think so. Is it you are getting IA1? IA1 minus J, Thevenin voltage and pre-fault voltage both are same. Minus J 0.9091 per unit. Okay. What is IA2 current? From this model, you can observe that IA2 current is simply opposite to that of IA1. IA2 current is simply opposite to that of IA1 from the model. So IA2 current will come to be minus IA1 from circuit analysis. So it is J 0.9091 per unit. And as the zero sequence circuit was open, IA0 value was 0. As the zero sequence circuit was open, so you can say this IA0 current is 0. Now you find out that faulted phase B current. Faulted phase, that means phase B current you can do. Phase B current, IB is equals to IA0 plus alpha square into IA1 plus alpha into IA2. Like this you write first. Okay, IA0 value already we said 0. It is alpha square IA1 and IA2 is minus IA1. So you have minus alpha IA1. IA2 is nothing but minus IA1. So it will be alpha into minus IA1. Fine. So you can take this IA1 common, which is alpha square minus alpha. IA1 common, you get alpha square minus alpha. What is IA1 value? Minus J 0.9091. Minus J 0.9091. What is alpha square minus alpha? Alpha square minus alpha. So it is minus J root 3, I think so. Minus J root 3. Alpha square minus alpha, it will be minus J root 3. So J square, it's minus 1. So it will come as minus. How much is that value? Minus 1.574. Minus 1.574 per unit. Minus 1.574 per unit. That's a phase B current. Phase B current. And what about the phase C current? Phase C current you have to calculate. Yeah, you do that calculation. You do that calculation, phase C current, by using a similar equation. Yeah. So if you attempt to go with IC current now, which is IA0 plus alpha IA1 plus alpha square into IA2. So you take this current 0. In place of IA2, we keep minus IA1. So alpha IA1 minus alpha square again IA1. You take IA1 common. You'll have this as alpha minus alpha square. IA1 minus J 0.9091. Alpha minus alpha square means it is J root 3. you may get this current same magnitude 1.574 but positive. 1.574 only, but that is positive number. Getting? Simple. Okay, now you have to make certain comments on this analysis. Okay, we'll do that next one also. Second one also we'll do, then we will make certain comments. Second one also we'll do first. Second part. What is the second part of the problem? What is asking in the second part? Healthy phase voltage, right? Non-faulted phase means healthy phase. What is the healthy phase here? Phase A. Means we have to calculate phase A voltage. What is phase A voltage? Formula. VA0 plus VA1 plus VA2. So we have to calculate sequence voltages first. VA1, VA2 and VA0 values. Okay, second one. You can call healthy phase voltage. Healthy phase voltage. VA is equals to VA0 plus VA1 plus VA2. VA0 plus VA1 plus VA2. Okay. Check here. From circuit analysis. What is VA1 you can write? What is VA1? VPF minus IA1 into Z1 equivalent. Where VA1 is equals to pre-fault voltage minus IA1 into positive sequence Thevenin impedance. Pre-fault voltage is 1. IA1, how much is that current IA1? Anybody? Tell me please, IA1. Minus J 0.9091. Minus J 0.9091. What is Z1 equivalent value? Z1 equivalent value, I think it is J 0.5 in the data. J 0.5. Yeah, you please calculate this VA1. How much? Calculate positive sequence voltage. I will make that comment later. Vasishtha, I will make that comment later. So it is 0.5455. 0.5455 per unit is a positive sequence voltage VA1. What is VA2? Negative sequence voltage, how much? Anybody tell me please? What is negative sequence voltage? Minus IA2 into Z2 equivalent. Minus IA2 into Z2 equivalent. Minus of IA2 is minus J 0.9091. Z2 equivalent is J 0.6. You will get this number again same 0.5455 per unit. 0.5455 per unit. Same. What is zero sequence voltage? What is zero sequence voltage VA0? Anybody? Zero sequence voltage VA0 will be minus IA0 into Z0 equivalent. See, IA0 value 0, but Z0 equivalent is infinite. So we can't determine from this equation. Indeterminate. From the equation what we have written, we can't determine the value of VA0. But from circuit analysis, from circuit model what we have, from the connection of sequence networks, it is clearly visible that this VA0 value is equals to VA2 or VA0 value is equals to VA1. Clear? So I can say here from network connection or KVL connection, or you can say KVL, zero sequence voltage is nothing but the value of positive sequence voltage 0.5455 per unit. 0.5455 per unit. All of you getting this one? Yeah. So finally, after getting this VA1, VA2 and VA0, you can write VA value simply as 3 times of VA1. So 3 into 0.5455 per unit you are going to get. Okay. So I can say here phase A voltage, so-called healthy phase. Therefore, phase A voltage is equals to 3 into 0.5455. How much is that value? 1.6365 per unit. 6365 per unit. That's the healthy phase voltage. Healthy phase voltage. I think all of you getting this. VA2, how it is negative, Gajapati Raju? VA2 will be same as VA1. Let me cross check. It's minus of this. J square means minus. What is IA2? Sorry. This IA2 is plus J. IA2 is plus J 0.9091. J square is minus 1. Minus will be cancelled. It will come same as 0.5455. VA2 is positive. Yeah, good. Fine. Next thing. Tell me. If you look at these sequence networks here, if you look at these sequence networks, you observe. Listen, please. Listen, all of you. Listen, all of you. You can observe here. Zero sequence circuit is open. Zero sequence circuit is open, and you observe that only positive and negative sequence circuits are in parallel, carrying IA1 current and IA2 current, and you don't have the IA0 current at all. Can we feel that? Can we feel that this fault is similar to LL fault? Tell me, please. As a zero sequence circuit was open, I can draw simply positive and negative sequence circuits are connected in parallel as a zero sequence circuit is open here. So can we feel that this fault is similar to LL fault? Yes, but some conditions are there. I'll tell you, some conditions are there. Means, particularly for an ungrounded neutral system like this, as Z0 equivalent equals to infinite, right? The LLG fault and LL faults are looking as same. In what view means currents calculation I can see. Means in the calculation of IA1 and IA2 currents, as well as phase currents IB and IC, it will be same as LL fault. But if you go with the voltage calculations, in case of LL fault, zero sequence network is completely outside. In case of LL fault, zero sequence network is completely outside, and you don't have zero sequence voltage at all. That zero sequence voltage is zero. You get only positive and negative sequence voltages. But if it is a double line to ground fault, there is an existence of zero sequence voltage also in the calculations. Okay, in the view of currents calculation, LLG fault and LL faults are looking as same for an ungrounded neutral system. But in the view of voltages calculation, there is a definite difference between the two types of faults. I don't know whether you have understood this or not. I'm writing that statement here. In the view of currents calculation, double LG fault and double L faults are similar on an ungrounded neutral system. On an ungrounded neutral system. LLG fault and LG faults are same. Okay, but there is a difference in the voltage calculations. In bracket you write, but there is a difference in voltage calculations. Okay, this is another doubt what the people will have generally. Tell me, please. Tell me. For example, a problem is given simply like this. These are data I am providing. Just look. This is the data I am providing, same data. Else I'll copy it better. Same data as it is. No need to write. No need to write it. Just you can write it as same as previous problem. Same as previous problem. Find fault current value. Fault current value in per unit. What's your answer for this problem? Same problem, na? No change at all. Same problem, but I am asking you, what is the value of fault current value in the per unit form? What's your answer? Tell me, please. See, ground is not at all carrying any current, right? Ground is not at all carrying any current here. Then you should not say ground current as fault current in this case. Listen to my words, please. Listen to my words. If you have a double line to ground fault on an ungrounded neutral system, zero sequence current is zero. So ground current is zero. In that situation, we should not treat ground current as a fault current. We should treat any one of the phase current, maybe IB or IC, as a fault current. So this type of convention you have to follow. If it's a grounded system, and if he's asking fault current for LLG fault, I will say ground current as my answer. If it's an ungrounded system, LLG fault occurred, ground current is zero, I should say any one of the faulted phase current, as a fault current in the answer. Getting? Right? So I am saying that answer here, for LLG fault ungrounded neutral system, for LLG fault on ungrounded neutral system, ground current is equals to zero. Ground current is equals to zero. In this case, any one of the phase current, faulted phase current shall be considered as fault current. Okay. Therefore, for this problem specifically, fault current is nothing but phase B current magnitude. And what is that phase B current magnitude we have? Just check that number, how much? 1.574 per unit. 1.574 per unit, you can say as. Yeah, getting this convention, what I am saying? I need your response. I have written the thing on the board. I think most of you might be clear with this. There is say grounded. What is that? Yeah, good. Fine. Next. I'm taking up one simple calculation further with respect to this problem only. I'm taking up some simple calculation. Go through it. For example, look here. Yeah, look here. Look at this diagram. All of you look here. Ground current will be zero. Ground current will be 0. So please. This is a fault location. Bus 3 is a fault location. Fault location. So at bus 3, so-called at fault location, we have a LG fault. Pre-fault voltage is 1 per unit. Pre-fault voltage you treat it as 1 per unit. For LG fault at F, LG fault at F location, on phase A to ground fault. Better I'll say the LG fault at F rather than that, A to ground fault. A to ground fault at F location. At the fault location. What will be the healthy phase for you? What will be the healthy phase for you? B and C, right? What will be the healthy phases for you? B and C. What is the phase B voltage magnitude you can expect? What is the phase C voltage magnitude you can expect? Because those who are healthy phases, I am asking you about the phase B and the phase C voltage magnitudes. Anybody? Tell me please. Anybody? How much is phase B voltage magnitude and phase C voltage magnitude? It will be 1.732 times. That's what we discussed in the yesterday class. 1.732 phase B per unit, 1.732 phase C in per unit. Why it is so means? We have an ungrounded neutral system. Z0 equivalent equals to infinite and zero sequence voltage will be -1 per unit. Because of that, it is coming. Okay, one small change. All of you listen here. Don't ask me this doubt again in your doubt session. Don't ask me this doubt again in your doubt session. I'm saying this statement. Kindly listen to me carefully. Earlier, in case of LLG fault, you are getting this VA1 value something like 0.545 per unit, 5455 per unit, and VA2 also 0.5455 per unit, and so on. But listen. If Z1 equivalent and Z2 equivalents are equal, here Z1 equivalent is 0.5, Z2 equivalent is 0.6. Z1 equivalent number J0.5, Z2 equivalent is J0.6. But if Z1 and Z2 are equal, Z1 equivalent and Z2 equivalent values are equal, then what you can expect? What you can expect is VA2 will come 0.5 per unit, VA1 also comes to be 0.5 per unit. Anybody having a doubt? I am repeating the statement. Kindly understand to these words what I am saying. Kindly understand these words what I am saying you. If positive sequence Thevenin impedance and negative sequence Thevenin impedance, if these two values are exactly equal, if you calculate VA1 and VA2 values, you will get 0.5 per unit, both numbers. I don't know whether you have understood this or not. Okay. So I will write here if you want, with respect to fault location or bus 3, I am assuming that positive sequence Thevenin impedance and negative sequence Thevenin impedance is equal and zero sequence Thevenin impedance is equals to infinite. Assuming that all equipments are having positive and negative sequence reactances as equal. All equipments are having positive and negative sequence reactances equal. Okay. Yeah. Next thing. Tell me, A to ground fault you have taken. For example, we have B to C fault, line to line fault, BC fault at F location. Means LL fault, na? It's a LL fault. First one it's LG, next one is LL. Tell me please, for this fault, which is a healthy phase for you? Phase A. Which is a healthy phase? Phase A. Okay. So what is that healthy phase voltage magnitude? See, it is VA1 plus VA2 plus VA0. Look all of you. Again, you are saying the same answer, anonymous attendee. Look to my statement, what I am saying you. Line to line fault we have, and you have VA1 value 0.5, VA2 value 0.5 only. What is VA0 in case of LL fault? See, in case of LL fault, it is not at all connected to the network, right? This zero sequence network, what you have, it will be completely disconnected, right? Will be completely disconnected. It won't come into the network analysis at all. You have only VA1, VA2. Both values VA1, VA2 are 0.5 per unit. 0.5, 0.5 per unit, and this is 0. Assumed as 0. Yeah. Again, Pragati, why you are saying 2 into 0.545 after making the assumption? Huh? Again, 3 times of VA1. How come you get Shivaram Krishna, Prashant Reddy? Kindly listen to the words what I am saying you. This is completely disconnected. Why you have disconnected this? Because it's not LLG fault, it's only LL fault to me. If it's LL fault, we have to connect positive and negative sequence circuits in parallel. That's it. And if you calculate VA1, VA2, both the numbers comes equal 0.5 per unit. Yeah. IA1 and IA2 are equal, right, Sai Charan? IA1 and IA2 are equal, one and opposite. Yeah, fine. I think so. We have understood this. So this number will come as VA1 plus VA2 plus VA0 value, right? VA0 value, VA1 value 0.5, VA2 value 0.5 plus VA0 value 0 in case of LL fault. It will come to be 1.0 per unit. If you are getting any doubt, you draw sequence circuits for LL fault and check it. Next, you have BCG fault, BC to ground fault, LLG at F location. BC to ground fault at the F location. So it is LLG. LLG. What is the healthy phase for you? What is the healthy phase? What's the healthy phase? Phase A. How much is that voltage? VA1 plus VA2 plus VA0. But in this case, zero sequence network will come in parallel with that positive and the negative sequence networks. And this will come positive sequence voltage 0.5, negative sequence voltage 0.5, zero sequence voltage also 0.5. And this number will be 1.5 per unit to be taken. 1.5 per unit to be taken. Okay, next. LG fault yesterday, many times I explained Tulsi. Many times I explained for LG fault yesterday. Next, if you have three-phase fault, no healthy phase. All the three phases are faulted. Triple LG fault, all the three phases are faulted, no healthy phase. Forget about those two. Think about only these three. LG fault, LL fault, double line to ground. Tell me, is there any over voltage you are experiencing because of LG fault on the healthy phases? Is there any over voltage you are experiencing? Is there any? Without fault impedance only I am discussing. Why you are asking me again same doubt, even though you know the answer? Huh? Anonymous attendee, why you are asking me again same question, even though you know the answer? Which phases are experiencing over voltage? In case of LG, are you experiencing any over voltage? Yes. 1.732 on the LG phase B, 1.732 on the LG phase C. Are you experiencing any over voltage on the LG phase for LL fault? Are you experiencing any over voltage for LL fault? No, we are not experiencing it. Do you have any over voltage for LLG fault? Do you have any over voltage during LLG fault? Yes or no? Yes, that's the statement yesterday I said. Okay, if you have an ungrounded neutral system, and if you have grounded faults like LG and LLG, on the healthy phases, there may be a rise in the operating voltage. There may be a rise in the operating voltage, and healthy phases will experience the over voltage. Because of these over voltages, we said that there is a possibility of getting the arcing grounds phenomenon. But if you compare these voltages here, whatever the over voltage you get during LG fault, that is higher as compared to the double LG fault over voltage. In that perspective, LG fault is, if you have LG fault on the system, the probability of getting arcing grounds will be more as compared to the LLG fault. All of you getting this? Yeah. So I can say On ungrounded neutral system for LG fault, sorry, LLG. For LLG, fault on ungrounded neutral system, neutral system, there is a over voltage on healthy phase. There is a over voltage on healthy phase. Over voltage on healthy phase. Healthy phase. It may cause for the arcing grounds. Generally no, but still we can write that statement because of pre-fault voltage may be more than the rated value, or you have that Z1 equivalent, Z2 equivalent may be unequal. In that situation, that over voltage magnitude will be more. Okay, it may cause for arcing grounds. May cause for arcing grounds on healthy phase. Right? Yeah. Fine. Next thing. So this is with respect to double line to ground fault. Some conclusions we have discussed. Next, let us take up the three-phase short circuit fault. Three-phase short circuit fault. Ungrounded fault we are going to take up first. Three-phase short circuit fault. Already we discussed this three-phase fault on the alternator. We have done some problems also, right? We have done some problems also, but now we are going to do it by using what we call symmetrical components. We are going to do this by using symmetrical components. Yeah, first I will take no load operating alternator. We extend in the similar manner. I am taking no load operating alternator like this. Okay. So it's a neutral which may be connected to ground with an impedance of Zn. So these are the outcoming wires. ABC you can show. ABC you can show. And these are the terminal voltages. You have VA, VB, VC. And currents, you know, IA, IB, IC. Currents, you know, IA, IB, IC. In the similar manner. Internal voltages. EA, EB, EC. These are internal voltages we have. EA, EB, EC. Next, pre-fault condition as it is, no load operation only. If you want, copy those things, what we have written earlier. Yeah. So pre-fault conditions as it is. No load. Take it. Pre-fault conditions, no load. Yeah. So now we are going to consider fault here, three-phase fault. Look here. Three-phase fault we are going to take. Three-phase means simply this ABC will be shorted here. So I can say three-phase fault. Three-phase fault. At the terminals of the alternator, solid three-phase fault. I'm going to say solid three-phase fault means with the fault impedance value is equals to 0. I will be shorting these three. Okay, what happened after making these three short? Yeah, I know when to give break. Don't remind me. I know when to give break. Okay. Why you are saying the same thing again and again in the comment section? It may irritate some other people who is having a genuine doubts. Yeah, listen please, listen. Three-phase fault, we have a solid fault, something like this. What are the changes we are getting now just after having this fault? Just after having this fault, what are the changes we are going to get? Simple, all the three conductors are shorted, no? Shorted means definitely I can say A, B, C, all the three voltages will be exactly equal. All the three voltages will be exactly equal. That may or may not be 0, that we don't know. That value of voltage may or may not be 0. Okay, yeah. So I can say the next slide. After the fault has been occurred, phase A, phase B, phase C voltages are exactly equal. That may not be equal to 0. We don't know about it right now. For example, if that is connected to ground, then I can confirm that value is 0, but it is not connected to ground. Okay, next thing. What about currents here? Earlier, all the three currents are 0. IA, IB, IC currents are 0. But now there is a path for the current flow in the phase A, phase B, phase C. Means these three currents may not be equals to 0. These three currents may not be equals to 0. Phase A current not equals to 0. Phase B current not equals to 0. Phase C current also not equals to 0. Okay. Phase A, phase B, phase C currents may not be equal to 0. But one thing it is clear that some of the three currents will be equals to 0 because you don't have a return path. You don't have a return path. For example, if you stand at this node, apply KCL. IA current is coming down like this. IB current is going like this. IC current is going up. Then all the three currents are reaching to that node. There is no outgoing path. Some of the three currents will be equals to 0. Okay, but you can call IA plus IB plus IC. That summation will be equals to 0. See, we don't know exactly speaking the system is balanced or unbalanced. We don't know exactly whether the system is balanced or unbalanced. But you can apply symmetrical components for this, and we can construct the sequence networks. Based on sequence networks, we can confirm whether the system is balanced or unbalanced further. Okay, fine. First, symmetrical components for voltages I can say. Symmetrical components for voltages I can say. But you can ask me a doubt that, sir, earlier you said if you have a three-phase short circuit fault, you can treat the system as balanced. That statement is fine. If you want, you can go with that statement also directly. But I want to prove that statement with the help of symmetrical components. How we can say mathematically or perfectly the system is balanced during three-phase fault, that we are going to prove now. Okay, yeah. First, symmetrical components for voltages. Why EA1 0, Anusha? Why EA1 is 0? What is EA1? Default voltage, right? Symmetrical components for voltages. Simple. I'll write that matrix here. VA0, VA1, VA2 matrix. Okay, so it's equals to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. So it will be VA, VB, VC. Okay, all the three voltages are equal, we are saying. This VB you can replace with VA, VC also you can replace with VA. Okay, now what is the value of VA0 from this calculation? What's the value of VA0 from this calculation? 1/3 VA plus VA plus VA. So it will be 3 VA by 3. So it will be VA simply. VA0 value is equals to VA. VA0 value is equals to VA. Now, what is VA1 value? What is VA1? Tell me please, from this calculation. 1/3 VA plus alpha VA plus alpha square VA. 1/3 VA plus alpha VA plus alpha square VA. You can take that VA common and you can get this 1 plus alpha square. That 1 plus alpha square is 0. So VA1 value will be 0. VA1 value will be 0. Okay, fine. Next. What is VA2? What is VA2? VA2. 1 by T. You do that calculation again. VA plus alpha square VA plus alpha VA. Again, you take VA common, you will get same answer as 0. Same answer we are going to get as 0. Right? So positive and negative sequence voltages after the fault has been occurred are 0, and 0 sequence voltage is equals to VA what we get. These are results what we get from symmetrical components of voltages. What about from currents? From symmetrical, by applying symmetrical components for these currents, what results we are going to get? All the 3 currents are non-zero. I don't know about it. But one thing what I can confirm is sum of the 3 currents equals to 0. Na? If sum of the 3 currents equals to 0, 0 sequence current will be equals to 0. That we can confirm. Okay? Yeah, let me show. As IA plus IB plus IC equals to 0, IA plus IB plus IC, the summation is equal to 0. The summation IA plus IB plus IC is 3 times of 0 sequence current. So I can call 0 sequence current value 0. This is one relation what we can apply. Okay, now simply you take positive sequence network, negative sequence network, 0 sequence network, implement whatever the conditions we have into that sequence networks. Let's do sequence networks. Sequence networks. Generator only we are considering now. So it is a positive sequence network. Okay, so it's plus minus VA1, Z1 positive sequence impedance. Default voltage is EA1. Negative sequence network, neutral, and this impedance I call Z2, and this voltage VA. And 0 sequence network, up to neutral we should keep Z0, neutral to ground we should keep 3 times of Zn. Because we are discussing about an alternator alone, we should draw sequence networks of the alternator like this. And this voltage is VA0 I am showing, and this current flowing in this 0 sequence network is IA0. Current flowing in this network is IA0. And this current is IA2. And this current is IA1. These are the sequence currents I am showing: IA1, IA2, IA0. Yeah, next. Just don't think too much. Whatever the sequence voltages and currents relations you got, that you dump into the networks. Following all of you, don't think too much. Don't guess the thing. Don't say anything directly. Just follow the procedure. Look at the things. VA0 equals to VA. VA0 value equals to VA. You keep it here. VA0 value I should keep as VA. With a red color, whatever I am writing, all these things are during short circuit. Next one. VA1 how much? 0. Means after the fault has been occurred, this VA1 value 0. VA1 value 0 means we should make a short circuit here, obviously. We should make a short circuit here. Okay. What is VA2? Also 0. VA2 is also equals to 0. Means we can make a short circuit for this also. Why we are making short circuit? Because he is saying that voltage is equals to 0. Okay, let's move back. IA0 value 0. That's a current relation what here. IA0 value 0 in the sense we should make the circuit remains open. 0 sequence circuit we should keep remains open. Following all of you. Fine. These are the sequence networks correction. This you have to remember. I will repeat this one later. I will repeat this one later while you are comparing the triple LG fault and triple L faults. Okay, tell me now, what is the current IA1 you can get from this analysis? What's the IA1 current? Simply it is pre-fault voltage EA1 by Z1. That's it. What is IA2 current? I don't have any voltage source. I don't have any voltage source, but still you have a what we call a closed path. So even though you have a closed path, you don't have voltage source. IA2 current will be 0. And already we are saying IA0 current equals to 0. IA0 current equals 0. So you have only positive sequence current existing in the system. You have only positive sequence current existing in the system. Can we feel that the system is balanced now? Tell me anybody. Can we feel that the system is balanced now after the fault has been occurred? Yes, definitely. The reason is simply you have only IA1 current. Okay. So as only IA1 exists, IA1 exists, the system is balanced in post-fault condition. The system is balanced after the fault occurrence. After the fault occurrence. So in this triple L fault, yeah, look here. In this triple L fault, what is a fault current value means any one of the phase current can be treated as fault current. Fault current means any one of the phase current can be treated as fault current. You can call as phase A current. What is phase A current formula? It is IA0 plus IA1 plus IA2. What is IA0 value? 0. IA1 non-zero. IA2 0. So this is nothing but IA1 current itself, and this is pre-fault voltage by positive sequence impedance. Pre-fault voltage by positive sequence impedance. Okay, so have a break for 20 minutes. Have a break for 20 minutes. After break, we do some sort of generalization for this one, as well as with fault impedance, how to calculate the currents and all that we will write crisply. Later on, we will move on to triple line to ground. Okay, 20 minutes break. We will meet at 5 p.m. Class resumes at 5 p.m. So I have resumed the audio video on screen. Please kindly confirm. Yeah, good. So let's continue. Let's continue. Next, I will be taking up a triple L fault with some fault impedance ZF. So I'll say in the next slide, triple L fault with the fault impedance means ZF not equals to 0. Fault impedance means ZF not equals to 0. The same alternator I will be considering now. Same alternator we are considering. Same pre-fault conditions as it is. No need to repeat them now. Okay, so neutral, and neutral is connected to ground with Zn impedance. These are the outcoming terminals ABC. ABC outcoming terminals, and we have currents IA, IB, IC, IB, IC, and these terminal voltages are denoted as VA, VB, VC. Okay, I'll write simply pre-fault state of system. It is simply no load. Same conditions you can treat. Okay, I'm not repeating them. These are internal EMFs of the machines EA, EB, EC. Internal EMFs of the machines EA, EB, EC. Okay, now if you have a triple line fault with a fault impedance, particularly I am treating that fault impedance as a balanced fault impedance. Moreover, it's a balanced fault impedance in the star connection. I'm considering that fault impedance in the star connection. So I might have a fault impedance from A, something like this, from B, from C also, like this. Okay, so this is a balanced fault impedance section. Balanced fault impedance section. Balanced fault impedance section. Okay, I will be writing this one directly without discussing much about sequence networks. I will be writing this one directly. So as it is a what we call a balanced system now, as it is a balanced system, just you can draw per phase network. Just you can draw the per phase network. Based on that network, you are capable to get the positive sequence components, right? Or you can say directly phase A components we are going to get. Okay, so I'll say per phase network straightly. Per phase network directly. First phase A network of alternator, particularly positive sequence EA1, and positive sequence impedance is Z1. Okay, so this will be the positive sequence voltage VA1 and current I am showing as IA1. And whatever the fault impedance ZF we have, whatever the fault impedance ZF we have, that we will be connecting something like this. Fault impedance, we are connecting something like this, ZF. Fault impedance. Okay, so from this, if you want to find out fault current value, which is nothing but phase A current is nothing but again IA1 value, which is EA1 means pre-fault voltage VPF by Z1 plus ZF. Fault current value is equals to phase A current is equals to positive sequence current, which is nothing but pre-fault voltage VPF by positive sequence impedance plus that fault impedance ZF. Positive sequence impedance plus fault impedance ZF. Okay, fine. VPF by Z1 plus ZF. Now let's move with the generalization, breaker rating, as well as the short circuit MV. First, I'll say generalization. Generalization. Right. So we have some big power system network like this. Okay. So this is some system we have connected. For this bus bar, again you have some big system connected in this manner. And this is our fault location. I am showing three-phase fault location. So with respect to that fault location, first you find out the VPF value, so-called pre-fault voltage value, VPF value. Yeah, you can consider the fault impedance as a load. Calculate VPF, pre-fault voltage value, and then you calculate the Z1 equivalent, so-called positive sequence Thevenin impedance value. And as we said, it's a triple L fault with fault impedance. Triple L fault with some fault impedance. And what is that fault current we can write down? Fault current is nothing but pre-fault voltage value by positive sequence Thevenin impedance plus fault impedance. Pre-fault voltage value by positive sequence Thevenin impedance plus fault impedance, that we can say as fault current IF. Fault current IF in a generalization. Okay, next thing. Kindly complete it quickly. We'll move to next slide. Yeah, so I'm taking up in the next slide. Look here, for example, if this is some system, we have 1, and this is some system, I'll say 2. Between these two systems, we have a three-phase transmission line running. Three conductors running like this. It's a phase A conductor I'm showing, a phase B conductor here, and it was a phase C conductor like this. Okay, these are the phase conductors I'm showing as ABC. Now, if you have one three-phase fault like this on ABC conductor, what is fault current here? What is the value of fault current? If you look at this circuit, you feel there is some ambiguity. Why it is so means system 1 will supply some current in phase A. Similarly, system 2 also will supply some phase B current, supply some phase C current also. Both systems will supply some ABC currents to the fault element. Some of those currents are the currents flowing into fault element. Like that, you have to recreate it. Okay. So now, how in the sense, again, by means of tappings, we are going to redraw this. So this one system 1, and this is system number 2, and I will show three-phase lines here, line A and line B I am showing, and this is line C. Okay, now I am taking some tappings, something like this on the phase A conductor. I am taking some tapping, and it's a phase B conductor. I am taking some tapping, and phase C conductor again I am taking some tapping. Okay, these are ABC conductors. We are taking some tappings. Now, whatever the fault you say, that you apply at this place. Three-phase fault you can apply at this place, and whatever the current flowing in the phase A out, that is going to be called as fault current. I think all of you getting my point. What is it? This is the fault current IF, or you can say phase current. Phase A current itself is treated as fault current. Next, let's move with the breaker rating calculation with respect to three-phase short circuit. It's very important with respect to examination also. Breaker rating calculation. Moving to the next slide. CB rating calculation or selection, you can say. CB rating selection. Yeah, look here. See, for example, if you take only one alternator like this, and if you have 3 wires coming out, and you are keeping one circuit breaker at this place, means at the terminals of the alternator, we are keeping one 3-phase circuit breaker, and it's a star grounded alternator, we assume, and we had a 3-phase short circuit at the terminals. After this fault has been occurred, you have the phase A current as well as phase B current as well as the phase C current, and all the 3 currents will be equal in magnitude. All the three currents will be equal in magnitude. Then what is the circuit breaker rating three-phase value here? What is the circuit breaker rating in the three-phase manner? 3 into phase voltage magnitude in kilovolts multiplied with 3 into phase voltage magnitude in kilovolts multiplied with what current I should take now? Any one of the current. Either it may be a phase current, phase A current, or phase B current, or you can say phase C current. I'll say IA current because all the three currents are equal in magnitude in terms of kiloamperes, you can say. And if you write V phase in per unit, IA in per unit, you have to multiply that with S base 3 phase. You can write this phase voltage per unit value, phase A current per unit value multiplied with S base 3 phase. Like this also, you can write it. Like this also, you can write it. Yeah. Again, same rules what I said earlier. If you have current supply from both sides, not only in this case, in the previous fault studies also, like LG, LL, and LLG also, if you have current supply from both sides at the breaker location, we have to check which current is higher from side 1 or side 2. Based on that current, we have to design the breaker. Based on that current, we have to select the circuit breaker rating. Okay. Anyway, I will try to show that in a problem. Let's write with respect to fault level now. Fault level, or you can say short circuit MVA. For three-phase short circuit fault level or short circuit MVA or short circuit capacity. All these terms are short circuit capacity. Or fault level in MVA. So what's the formula we know? 3 into pre-fault voltage in terms of kilovolts multiplied with fault current in terms of kiloamperes. That's it. Else, you can write it as pre-fault voltage in per unit domain multiplied to fault current in per unit domain multiplied with S base 3 phase. Multiplied to S base 3 phase. Like this you can see. Pre-fault voltage in per unit form, fault current in per unit form multiplied with the S base 3 phase value. And already you know fault current per unit formula for the 3-phase short circuit that you can substitute now. So it's pre-fault voltage per unit into fault current per unit is pre-fault voltage by Z1 equivalent plus ZF, in per unit form multiplied with the S base 3 phase. Okay. Pre-fault voltage per unit, and here also pre-fault voltage per unit, you get pre-fault voltage per unit square. Okay, I'll show in the next slide. Please complete it quickly. This one. Please complete it quickly. Yeah. So once after completion, please kindly raise your hands. Once after completion, please kindly raise your hands. Okay, done. So I'll say fault level in terms of MVA. Fault level in terms of MVA is equals to, you can get here pre-fault voltage square in per unit form by you can have Z1 equivalent plus ZF in per unit form. Z1 equivalent plus ZF in per unit form into S base 3 phase. Okay, let's make the assumptions. Now. Let pre-fault voltage magnitude or pre-fault voltage value simply 1 per unit. So you can substitute here 1 square. Fault impedance is equals to 0. Fault impedance value is equals to 0. Then this equation, this above fault level equation, can be converted into S base 3 phase value by magnitude of Z1 equivalent per unit form. Magnitude of Z1 equivalent in per unit form. Okay, magnitude of Z1 equivalent in per unit form. And by assuming that network is lossless, let the network is assumed as lossless. Network is lossless. If that is the case, Z1 equivalent value will be turned into JX1 equivalent only. So if you take modulus of Z1 equivalent, it will be simply X1 equivalent that you can substitute there. Okay. So after making that assumption, fault level in terms of MVA will be S base 3-phase value in MVA, of course, S base 3-phase value in terms of MVA by simply X1 equivalent in per unit domain. X1 equivalent in per unit domain. Okay. Yeah, please complete the previous slide and then you can write simply in place of Z1 equivalent, X1 equivalent per unit. That's the expression for the fault level in terms of MVA. See, which formula we have to use means obviously according to data. Obviously according to data. Without having any confusion, without committing any mistake. What equation to be used means I will prefer to go for this one. Pre-fault voltage per unit into IF per unit into S base 3-phase is the best equation to calculate the fault level for any type of short circuit fault. For any type of short circuit fault. Okay. Yeah. Next, let's take up some problems on this one. Some problems. First problem I am taking up. First problem. Just look at this one. It's in the classroom objective questions PDF. Yeah, you take up this question. It was a question number 16. Question number 16. Try to answer that question, and in that question, I will try to show you that difference. I'll try to show you that difference. Between that fault level and what we call breaker rating. See this question? Assuming base rating equal to that of G1. Assuming base rating equal to that of G1 means whatever the G1 rating they have given 1000 MVA, that they have assumed as a base rating, base MVA, is MVA. Okay. The short circuit capacity of 3-phase fault taking place at the terminals of G1 is how much? Short circuit capacity for a 3-phase fault taking place at the terminals of G1 means this is a location of fault, and he is asking us to find out what is a short circuit MVA. Okay, first of all, 1000 MVA is a base. What is asking us to choose? X number for generator 0.2 only. Line X values will be remain same. 1000 MVA only base value. But generator 2 base value 800. Generator 2 base value was 800. Now we have to convert that means this X value 0.16 per unit given on 800 MVA base. We should convert it onto 1000 MVA base. You should convert it onto 1000 MVA base. Okay. Yeah. So let's move ahead to the next slide. As a solution, take this. Let us choose S base value as 1000 MVA. 1000 MVA. Okay, and we don't have any transformer here, so you no need to bother about voltage base values and all right now. You no need to bother about the voltage base values and all. Okay. Yeah. Listen here. Listen. Generator reactance same. Line reactance are same. Generator 2 we have to modify. Generator 2 X value was given Xg2. It is 0.16 per unit on how much base? 800 MVA base. 800 MVA base. It was a old base. It's a old base. And what's the new base here? S base new is how much? You have to consider 1000 MVA. 1000 MVA. So you no need to bother about the voltage basis, I said, by assuming that old voltage base value and new voltage base values are equal. By assuming that old voltage base value, new voltage base values is equal, I can say Xg2 per unit new number is equals to Xg2 per unit old value into S base new by S base old. That's it. S base new by S base old. Okay. By doing this calculation, I think you get this number as 0.2 per unit. 0.2 per unit. Okay. Next thing. You have to find out short circuit capacity. Short circuit capacity formula, you know already. I'll write it. Short circuit capacity is equals to pre-fault voltage magnitude in per unit form into fault current magnitude in per unit form into S base three phase. S base three phase. Okay, now anything mentioned about pre-fault voltage in the problem? Did he mention anything about pre-fault voltage? No. We have to assume that pre-fault voltage as 1 per unit. Pre-fault voltage value as 1 per unit. Okay, anything mentioned with respect to fault impedance in the problem? No. Fault impedance value equals to 0. Any resistance is given in the data? No. Resistance is also 0. By making all these assumptions, short circuit MVA or short circuit capacity or fault level, that formula will turn into S base three phase by positive sequence Thevenin equivalent reactance in per unit form. Positive sequence Thevenin equivalent reactance in per unit form. X equivalent in per unit. So simply with respect to this fault location, what they have mentioned, you find out that X equivalent value, dump that value in the what we call equation. Yeah. So calculating X equivalent means first you draw per phase network, so-called positive sequence network. Positive sequence per phase network you can draw. Generator represented like this up to neutral. After generator, you see we have two lines there. Line 1, line 2. Two lines are there. Okay. So after these lines, you have one more generator. That generator is represented in this manner, in a closed way. Now you can keep all these reactances or you say impedances. J0.2, I think a line J0.1 only. Is it? Yeah. J0.1 impedance, and this is J0.1 impedance, and this is J0.2. Right now we calculated. And this is the location of short circuit. This is the location of short circuit with respect to which you have to find out X equivalent or Z equivalent value. Okay, you kill the sources. By killing these sources, you know, 0.1 in parallel, it will come 0.05, and this is J0.2 in series. So J0.25 you may get. That will be in parallel with J point. So this you can redraw. Left side you will have J0.2. Okay, and the right side you will get this as J0.25. J0.25. So with respect to fault location, Z1 equivalent value will be J.2 in parallel with J.25. Anybody please tell me what is this number? Z1 equivalent. Tell me this number. Is J, you can say 0.2 into 0.25. By 0.2 plus 0.25. 0.45. How much? That number is J0.111 per unit. J0.111 per unit. So X1 equivalent is 0.111 per unit only. So you can call short circuit MVA here. Short circuit MVA or capacity. S base. It is 1000. He is asking us to consider by. You have 0.1111 in terms of MVA. How much is that value? How much is that number? Anybody? Tell this number how much? Short circuit MVA 9000. It will be 9 9,000 MVA. 9,000 MVA is a short circuit capacity at the fault location mentioned. The fault location mentioned. Okay. 9,000 MVA. That's the short circuit capacity. Yeah. Okay. Now tell me, what is the circuit breaker rating? In the same problem I am asking you, what will be the circuit breaker rating? Look here. Same as a previous problem, I can say. Same, or else better, I will show that diagram and all, and I will ask that question to you. Look here. So I'll copy this slide. I don't show this fault location to you. I don't show that fault location to you. This is a question. Assuming base rating equal to that of G1, the short circuit capacity the symmetrical breaking capacity, the symmetrical breaking capacity required for the CB kept in the system. Symmetrical breaking capacity required for the CB kept in the system. Will be dash MVA. Dash. Yeah. Try to attempt this problem. Attempt this problem once. Symmetrical breaking capacity required for the circuit breaker kept in the system will be dash MVA. See, if he is asking this type of question, where you have to look at the fault. In the previous problem, we located fault here according to the question given. Now, if he is asking breaking capacity of the breaker, with what we have to design actually? With how much breaking capacity we have to design the breaker? That's the question. Okay. So, where we have to look at the fault? Definitely nearby the breaker. Definitely we should take the fault nearby the breaker. After taking the fault nearby the breaker, we have some current supplied by the generator 1. We have some current supplied by the generator 2. And some of the two currents is flowing into fault. But only one current among these two will flow into the breaker. That current, the breaker has to interrupt here. Okay. Yeah. So first of all, I will draw that per phase impedance diagram. Per phase network. Okay. So this is the alternator equivalent circuit. And this is a location of breaker that you have to highlight now. And you have two lines in parallel like this. And then one more generator is at the end. Something like this. Okay. Now to design or to select the CB rating, what the procedure means? Take the fault at the CB location. CB location. Okay. After taking fault at CB location, what you should do? Find currents from both sides of system. Find currents from both sides of system or both sides of CB. Both sides. Okay. After calculating currents from both sides, next statement what I should say is select the CB rating based on highest current among the two. Third statement is select CB rating based on highest current among two. Highest current among the two. Current among the two currents. This is a general procedure which we discussed at the beginning stage of breaker rating also, right? So now simply you take fault at this location. First I will keep these impedances. This is J0.2 per unit and this is J0.1 per unit and this is J0.1 per unit and this is J0.2 per unit. Okay, what are the internal EMFs of machines you should assume? 1 at an angle 0 degree you assume as a voltage of both generators. Okay, now at the CB location you take the short circuit in this manner. The CB location you take the short circuit in that manner. Then you find out the current supplied by first generator as IF1 and find out the current supplied by the second generator as IF2. Summation of the two currents is flowing into fault element, which we are not at all bothering now. After the fault has been occurred, this voltage is 0. Okay, now what is IF1 value? 1 at an angle 0 by J0.2 means minus J5 is a IF1 value. What is IF2? You know, these two are in parallel, J0.05 and this is J0.2 and 1 by J0.25. 1 by J0.25. So that fault current will come to be minus J4 per unit. Clear? So which current is high for you? Is it IF1 or IF2? Which current is looking as high? IF1 is looking as high. So based on IF1 value, we should select the breaker rate. Okay? Yeah. So now I can say from circuit analysis, IF1 current, nothing but 1 at an angle 0 degree by J0.2, this will be minus J5 per unit. And IF2 current is 1 at an angle 0 degree by J0.25 and this will come to be minus J4 per unit. Okay, that implies CB has to be designed based on IF1 current magnitude. CB has to be designed based on IF1 current magnitude. Why you are thinking about negative sign? You should think about only magnitude. Should think about only magnitude here. Why you are thinking about negative sign? Right? Fine. So I can say circuit breaker rating here in terms of three phase as phase voltage in per unit form, rated voltage multiplied with IF1 current magnitude in per unit form multiplied with S base 3 phase. S base 3 phase. What is the V phase value per unit? 1. What is IF1? 5. And S base 3 phase, it is 1000 MVA. So this value we are going to get as 5000 MVA. 5000 MVA. We are guessing that this type of question may appear in the further gate examinations. We are expecting this type of question in the examination. Till now, they used to ask about short circuit MVA or short circuit capacity calculation. They didn't ask about the circuit breaker rating in this manner. Okay. Sometimes, if you keep the breaker at the end, and if you don't have current from other side of the breaker, whatever the fault current you have, that will flow in the breaker also, and that fault current itself, the breaker has to interrupt in that situation. That type of problem is there. In the previous examination, but this type of problem we don't have. But one more thing, what you have to observe carefully here is they don't mention where you have to take the fault. If they are asking about the breaker rating selection, they don't mention that where you have to take the fault. You have to take that fault at the breaker location and find out currents from both sides, and you check which current is high. Based on that, you should select the breaker rating. And moreover, whatever the breaking capacity we have given here, it's a symmetrical breaking capacity because IF1 current 5 per unit, what here? 5 per unit. It's a symmetrical component of the fault current. Symmetrical component of breaker interrupting current. Symmetrical component of breaker interrupting current. Okay, because we have not added any DC component here. We have not taken care of any DC component multiplication factor and all. So this is symmetrical breaking capacity. Symmetrical breaking capacity of circuit breaker. Capacity of circuit breaker. For example, if he is asking asymmetrical breaking capacity or momentary rating of circuit breaker. Momentary rating of circuit breaker, if he is asking, this is nothing but 1.6 into symmetrical breaking capacity we have to write. Symmetrical breaking capacity we have to write. So it will be 1.6 into 5000 MVA. 1.6 into 5000 MVA. So how much is this number? I think it is 8000 MVA. 8000 MVA is a asymmetrical breaking capacity, or you can say momentary. Yeah. So next we'll take up some more problems with respect to three-phase fault quickly. Let's take next problem. Look at this problem. Attempt to solve this question. This question is there already in the PDF file what I have uploaded. Yeah. So in a power system network, the positive sequence Thevenin impedance with respect to a 400 kV bus. We have a 400 kV bus in the system. With respect to that 400 kV bus, positive sequence Thevenin impedance value was measured. That number is 0.1 plus J 0.3 per unit on 400 MVA base. Means this Z Thevenin, what they said, 0.1 plus J 0.3 is on the base of 400 kV, 400 MVA. 400 kV, 400 MVA. Okay. The bus bar is operating at 420 kV at the instant of three-phase short circuit on the bus. At the instant of short circuit, it is operating at how much voltage? 420 kV. Okay. Find the short circuit capacity of the bus in terms of MVA. Find the short circuit capacity of the bus in terms of MVA. Just look here. So this is one bus bar we are selecting at which we are going to consider the fault. Bus bar. With respect to the bus bar, Z Thevenin or Z1 equivalent value 0.1 plus J 0.3 per unit on what base values? On 400 kV line to line voltage base and 400 MVA three phase base. 400 MVA three phase base values. Okay. Now the present operating voltage is said as 420 kV, means that is your pre-fault voltage. Pre-fault voltage is 420 kV that you convert into per unit form by dividing that with 400 kV base. Okay. Yeah. So let's take. So in the next slide, I'm taking pre-fault voltage. He mentioned 420 kV line to line. It's a line to line value. Then how much is this value in per unit form? Means actual value 420 kV line to line. Base value 400 kV line to line. Okay, kV will be cancelled out. 420 by 400. How much is that number? How much will be that number? Tell me please. How much is that value? 420 by 400. Somebody is saying 1.05 per unit. 1.05 per unit. That's the pre-fault voltage you have to consider. Okay, what is asking now? If you have a three-phase short circuit at this bus bar, what is the short circuit capacity of bus in MVA? What is the formula for short circuit capacity at that bus? Short circuit capacity, or you can say short circuit MVA is nothing but, again, you have to go with the original formula always. Pre-fault voltage per unit. multiplied to fault current per unit multiplied to S base 3 phase. S base 3 phase. Okay. So you keep this pre-fault voltage per unit. What is the fault current in per unit? You have to write pre-fault voltage value by Z1 equivalent, this magnitude in per unit form into S base 3 phase. S base 3 phase. This you can rewrite now. So pre-fault voltage square in per unit form by Z1 equivalent magnitude whole multiplied with S base 3 phase you have to take. Yeah, so I'm moving with the next slide to take up this calculation. Kindly observe it. Short circuit MVA is equals to pre-fault voltage per unit square by modulus of Z1 equivalent multiplied to S base 3 phase. S base 3 phase. Okay. Pre-fault voltage is 1.05 whole square. Pre-fault voltage square means 1.05 whole square. What is Z1 equivalent number? 0.1 plus J 0.3. Na? From that, what's the magnitude of Z1 equivalent? Root of 0.1 square plus 0.3 square. So this denominator Z1 equivalent in per unit is 0.1 square plus 0.3 square under root. Multiplied with what is S base 3 phase number? What's the value of S base 3 phase? Given in the data 400 MVA. This is a short circuit capacity. So all the varieties I have shown in this problem. Pre-fault voltage is not equals to 1 per unit. As well as we have some resistance in the network. We have some resistance also in the network. Yeah. Anybody calculated this number? Tell me your answer. 1394.56 MVA. 1394.56. Short circuit MVA value 1394 or 1395 MVA. Short circuit MVA. Okay. Next. Please check what you are doing here, anonymous attendee. Are you doing the breaker calculation here? What calculation you are doing in this problem? Are you doing breaker calculation or shunted capacity? Yes. Yeah. Next problem I am taking. Next one on triple L fault only. See this? Look at this. The three-phase short circuit capacity of a bus. Three-phase short circuit capacity of a bus. Not calculated Z new. What you are asking me exactly? Huh? Sir, in triple line fault, why you took IA only CB rating? Go through that. Why you have taken only IA? Because all the three currents are equal. Sir, why we not calculate Z new? Why? What's the necessity of calculating here? Tell me. What is the necessity of calculating Z new? Look here. The three-phase short circuit capacity of a bus in a power system network is 1000 MVA. Short circuit capacity is given 1000 MVA. Okay. What will be the short circuit capacity at that bus if pre-fault voltage is increased by 10%? If the pre-fault voltage value was increased by 10%, how much is the new short circuit capacity? See, actually, we know the formula for short circuit MVA something like this. Right? Maybe this one you see. Short circuit MVA equals to pre-fault voltage square by Z1 equivalent into S base 3. Means, you know, short circuit capacity is proportional to pre-fault voltage square. Short circuit capacity proportional to pre-fault voltage square. Okay. In the case 1, short circuit capacity or pre-fault voltage for VPF1, short circuit capacity value 1000 MVA, 1000 MVA. And for pre-fault voltage value of 1.1 times of VPF1, how much is the value of short circuit capacity? Okay, you know already that relation, right? So you can write short circuit capacity 2 by short circuit capacity 1 equals to pre-fault voltage 2 square by pre-fault voltage 1 square. So you can write from this short circuit capacity 2 equals to short circuit capacity 1 is 1000 into pre-fault voltage 2, 1.1 times of pre-fault voltage 1, 1.1 times of pre-fault voltage 1 whole square by pre-fault voltage 1 square. So that pre-fault voltage square is cancelled. So it is 1.1 square into 1000. So this number is 1210 MVA. 1210 MVA. Simple, very, very simple one. 1210 MVA. Yeah. Next, let's discuss little about the triple line to ground fault quickly. Triple line to ground fault we'll discuss quickly. Triple LG fault. Moving to next slide. Three phase to ground fault. Three phase to ground fault. Or you can say triple LG. Three phase to ground fault, or you can say triple LG fault. Yeah. Check this. Again, we will take alternator operating under no load condition. Alternator operating under no load condition. So this neutral is connected to ground with an impedance of ZL. And these are outcoming terminals ABC. ABC. Okay, so these are voltages. You have VA, VB, VC. Outgoing currents, already we said IA, IB, IC. And these are the internal voltages of your machine. EA, EB, EC are the internal voltages of the machine. EA, EB, EC. Yeah. So pre-fault is as it is, we said. Pre-fault, it will be as it is, no load only. No need to write all the conditions that we know already. No load. No need to write all the conditions. It will be no load. So I'm showing previous slide. So anybody still writing, please complete it. Previous slide I have shown. Okay. Yeah, you have three phase to ground fault now. Let me take up that. Ground fault. Like this. Okay, let's write in the next slide. Triple LG fault during triple LG fault. Triple LG fault. During triple LG fault. Tell me what happened after the fault has been occurred? What will happen to the voltages VA, VB, VC? All the three are connected to ground, right? All the three are connected to ground. Then what we should say? All the three voltages are equal to 0. VA value 0, VB value 0, VC value also 0. During triple LG fault, phase A voltage 0, phase B voltage 0, phase C voltage also equals to 0. Okay. What about the currents IA, IB, IC? All the three will exist. All the three currents will exist, which may not be equals to 0. Phase A current, I don't know, but it is non-zero. Phase B current, we don't know, non-zero. Phase C current, also I don't know, non-zero. All the three phases currents are non-zeros. IA, IB, IC currents are non-zero. Now I am asking in a simple terms. If all the three phases voltages are zero, if you convert them into symmetrical components, we convert these voltages into symmetrical components, what you get? What you get that VA1 value, VA2 value, VA0 value. After converting these voltages into symmetrical components, what you get that VA1, VA2, VA0, zeros only, right? All the three values will be zeros. If you have any doubt, you go with matrix. Go with matrix and calculate it and confirm. All the three sequence voltages are zeros. All the three sequence voltages are zeros. Any comment can you get from currents here? Any comment can you get from currents? I don't know. I don't have any comment actually with the currents because all the three currents are non-zero, but I can't say whether the sum of the three currents is zero or non-zero here because you have a path for the current. You have a path for the summation of the current flow. So I can't say whether the summation of the three currents is zero or non-zero in this particular case. But in the earlier case of triple line, in the earlier case of simple triple line fault, what we said is this is not grounded. So we are sure that IA plus IB plus IC equals to 0. Okay. But as it is grounded, we can't say it. Fine. Simply you draw sequence networks, positive, negative, and zero sequence networks. Okay. Give the connections by following these voltages relation what we have obtained. Yeah. Let's move. The next slide. I'm showing three sequence networks now. Let's show here itself. Positive sequence network I am showing first. This is the positive sequence network. Positive sequence network, neutral. And this voltage VA1 you have, current IA1 here, Z1. It was a pre-fault voltage. I am showing EA1. Negative sequence network. I am showing negative sequence network like this. Only negative sequence impedance Z2. And this voltage I am showing the VA2. And current here is IA2. Zero sequence network I am showing. Zero sequence network. Up to neutral should keep Z0. Okay, neutral to ground, we should keep 3 times of ZL. And this is the zero sequence voltage. We will call VA0. Current here is IA0. Current will be IA0. Just listen to my words. I didn't said that Pranjali Jamotkar. I didn't say it. Why you are saying that statement? Why you are saying that statement? I didn't say right. Listen, please. Listen. What's the value of VA1? 0. VA1 is 0 means you should make a short circuit here. VA1 value 0, we should make a short circuit. What is VA2? 0. We should make a short circuit here. What is VA0? Also 0. VA0 value also 0. And here also you can make a short circuit. This is the difference what you have to observe. This is the difference what you have to observe here. Getting me? Difference. See, in case of triple line fault, just if you observe here, triple line fault, we have drawn the 3 sequence networks like this. Positive sequence network, you know, VA1 value 0, I shorted it. VA2 value 0, I shorted it. But I don't know the value of VA0. Initially, you know, VA0 equals to VA, and I don't have any current flow in this loop because zero sequence current is 0. That's why I should keep this one open. I maintained this in open mode. But at present, VA0 value was 0. So you have to make a short circuit for this. Okay. In the previous case, listen please. Listen all of you. In the previous case, we have drawn sequence networks and all. We have drawn the sequence networks and all. After drawing sequence networks, what will be the value of VA naught? Anybody tell me, please? In the triple fault, ungrounded, ungrounded fault, what is VA naught here? Tell me, please. Is it 0 or non-zero? You said already VA, that's okay. Is it 0 or non-zero from circuit calculation? From circuit calculation, it will be minus IA naught into Z naught plus 3ZL. Z naught plus 3ZL. 0 into some finite number, right? 0 into finite number, that is equals to 0. I'm asking you very, very simple question. Why it is indeterminate? It's very clearly known here. Don't say that type of answers. Just look here, all of you. When you are saying that the zero sequence voltage is 0, is it before drawing networks or after drawing networks? In case of ungrounded triple fault, in case of ungrounded three-phase fault, you are saying that zero sequence voltage is equals to 0. When? Before drawing networks or after drawing networks? After drawing the networks. After drawing the networks, you are saying this one. But in case of triple line to ground fault, without drawing these networks itself, I am confirming that zero sequence voltage is equals to 0. I am confirming that zero sequence voltage is equals to 0 because all the three phase voltages are 0. See, when we are saying that zero sequence voltage equals 0 or phase voltage equals 0 in the three phase fault means after doing network analysis we are saying that. But here, without doing network analysis itself, as all the three phases are shorted to ground, we confirm that all the three voltages will be equals to 0. VA equals 0, VB equals 0, and VC equals to 0. So I think all of you getting this. Okay, now you tell me what is IA1 current? EA1 by Z1. What is IA2 current? 0. IA2 current is 0 because I don't have any voltage source, right? I don't have any voltage source. What is IA0 current? 0. I don't have any voltage source here also. Clear? Yeah. So in case of triple line to ground fault, we are writing IA1 value is EA1 by Z1. IA2 value was 0. IA0 value also equals to 0. Now, fault current in this case of triple line to ground fault is any one of the phase current only because ground current equals to 0. As a ground current is equals to 0, fault current is nothing but any one of the phase current. IA is taken as fault current, which is IA1 value only, nothing but EA1 by Z1. EA1 by Z1. Don't say that ground current as a fault current in this case. Ground current is equals to 0 in this case. So we have to consider that any one of the phase current as a fault current. Any one of the phase current as fault current. Okay, done. Next thing, listen please. So can we assume that now triple L and triple G faults are identical? Both are giving same value of fault current, na? Of course, voltage is also 0. In case of triple line fault also, after doing network analysis, I am confirming that all the three voltages are 0. VA, VB, VC, all the three voltages are 0. Here also, already all the three phases are grounded. All the three voltages are equals to 0. Yes, can we say that triple L and triple G are similar to each other? Yeah. So I can say. So triple L and triple G faults are similar with respect to fault current calculation. So in the examination, whether he mentioned the fault as a triple L fault or triple line to ground fault, you don't need to bother about it. Just you draw per phase network. Just to draw the per phase network and find out the phase current. That itself we treat as fault current for triple L fault as well as triple LG fault. Provided that, listen please, provided that the pre-fault system is balanced. Is before occurrence of fault, whatever the system exists, you have system is existing, that is a balanced system. In that situation only, this statement will be valid. Okay, so I will show that for you. Triple LG is identical to triple L, provided that the pre-fault system is balanced. Provided that the pre-fault system is balanced. Pre-fault system is balanced. Provided that the pre-fault system is balanced. Okay, done. Next, I will try to discuss about triple L and triple LG faults. Triple L and triple LG faults on an unbalanced pre-fault system. Means already existing system is unbalanced. Already existing system is unbalanced. And we have a triple L fault. How will be the currents and all? And we have triple LG fault. How will be the currents and all? What the difference you are going to get between the two faults? That we are going to discuss further by assuming that the pre-fault system is unbalanced. Okay? Yeah. So let's take up this one. Pre-fault system unbalanced. Pre-fault system unbalanced. Pre-fault system is unbalanced. I'll consider first triple L fault. Triple L fault. See, already you know, just listen all of you. Don't commit any mistake. Don't commit any mistake. Please listen here what I'm saying. Listen here what I'm saying. Triple L fault. What are the conclusions you are going to obtain here? What are the conclusions you are going to obtain for a three-phase fault? Three-phase ungrounded fault, balance, it's unbalanced system, you leave it further. See, whether the pre-fault system is balanced or unbalanced one, all the three conductors are shorted. Na? All the three conductors are shorted means VA equals to VB equals to VC, definitely. VA equals to VB equals to VC, definitely. Once after saying that VA equals to VB equals to VC, from symmetrical components of voltages, you will get VA naught value VA. VA naught value VA. What is VA1 value? 0. What is VA2 value? Also 0. That I will write you. That's it. So I can say here VA1 value I got 0. VA2 value also 0 I can say. But 0 sequence voltage is equals to VA. I don't confirm this value as 0. I don't confirm right now because equation C is not saying anything to me. Equation C is not saying anything to me with respect to 0 sequence voltage. So I have written that 0 sequence voltage value simply equals to phase A voltage. Now we draw three sequence networks, positive, negative, and 0 sequence networks for this pre-fault unbalanced system. For this pre-fault unbalanced system. Yeah, kindly observe. First, positive sequence network. Positive sequence network. We have some pre-fault voltage existing here in the positive sequence network. Okay, it's a pre-fault voltage positive sequence, and this is Z1, and this is the value VA1 here, and current here is IA1. Pre-fault negative sequence network. Pre-fault negative sequence network Z2. And you have voltage source here also, yes or no? VPF2 voltage source is existing here. Why it is so means before occurrence of fault, the voltages at the fault location are unbalanced. Voltages at the fault location are unbalanced. Yeah. Next, I will show zero sequence network here. So this is Z0 means Z0 equivalent. If there is any Zn value, that is added to that. Okay, Z1 equivalent you write, Z2 equivalent you write, Z0 equivalent you take. Okay, so this is a pre-fault voltage zero sequence, VPF 0, with respect to ground, of course. With respect to ground. And this voltage is zero sequence voltage VA0, and this current I am showing as IA0. The current I am showing as IA0. How many times I have to say anonymous attendee? IF equals 0 because IA plus IB plus IC equals 0. Have I said that? What is it you? Ground current equals 0. So we should not treat that as a fault current. What is a fault current? I said any one of the phase current we have to treat as a fault current. Why you are asking me again and again without listening properly to my statements? Yeah, please listen properly. Please listen properly. This is a doubt many people will get. That's why I stressed that statement many times earlier itself. Yeah, please look here. Please look here. See, I'll copy these circuits because these circuits I should draw even for triple LG fault also. I should draw for triple LG fault also, right? Listen. So as we said just now, we selected some fault location, but the system is unbalanced before occurrence of fault itself. Whatever the voltages we have there, so-called phase A, phase B, phase C voltages, that we are converting into symmetrical components, so that we get pre-fault positive sequence voltage, pre-fault negative sequence voltage, pre-fault zero sequence voltage. So we get voltage source in all the three sequence networks like this. If it's an unbalanced system, pre-fault system is unbalanced. Okay, now let me take second case. It was of a triple G fault. Same triple G fault. I will show same circuits because we are doing the fault analysis at the same location. We are doing fault analysis at the same location. Okay, tell me please. In this particular case of triple L fault, VA1 value 0. We got it from equations. We discussed already. VA1 value 0. So you have to make this one short circuit. Oh. VA2 value also 0. So you have to make a short circuit for this also. What is VA0? Equals to VA. Not only that, for triple L fault, we got some current relation as zero sequence current equals to 0. So this zero sequence current equals to 0 in the sense, this circuit must be in the open mode. And the zero sequence voltage equals to phase A voltage. After the fault has been occurred. Okay, yeah. Let's move with the same circuits, triple LG fault. So second case I have shown, triple LG. See, triple LG fault equations here, right? Triple LG fault equations. All the three conductors are shorted to ground. VA equals to 0, VB equals to 0, VC equals to 0. If all the three phase voltages are equals to 0, positive sequence voltage 0, negative sequence voltage 0, zero sequence voltage also equals to 0. Positive sequence voltage value 0, negative sequence voltage value 0, zero sequence voltage value is also equals to 0. That we have to show in the circuit. Okay. So whenever VA1 is equals to 0, I should short this one. To maintain that VA1 value 0, I should close this. Okay, short. VA2 value 0 means I should short this one. VA0 value how much? Also 0. So I should short this one also. I should short that point also. Yeah, have you understood this one? Please tell me. Have you understood this? Tell me, I need your response. Have you understood this or not? Yes. VPF2 will exist, Rohit. How many times I said again and again? Pre-fault system is unbalanced one. We have positive sequence pre-fault voltage, negative sequence pre-fault voltage, zero sequence pre-fault voltage also. Till now, whatever the analysis we have done, that is on a balanced system. Okay? In previous, you considered IA naught equals to 0. IA naught equals 0, it is saying from triple fault, right? IA naught value 0, we are getting it from triple fault. Just go back to the triple fault what we have written. All the three conductors are shorted, but not connected to ground. All the three conductors shorted, not connected to ground. What's the meaning of that? IA plus IB plus IC is 0. Zero sequence current is 0. So this zero sequence circuit must be in an open mode. Must be in an open mode. Yeah. I have not used any balanced relations here, anonymous attendee. Have I talked about current here? Have I talked about current? Simply, whether the system is balanced or unbalanced, all the three conductors are shorted. All the three conductors are shorted means what? VA equals to VB equals to VC. That's it. That statement only I am using here. Why you are thinking about in that way? And if you have a triple line to ground fault, all the three conductors are shorted to ground. All the three voltages are 0. Only voltage conditions I am using. I am not using current conditions here. Yeah. Anything more? Or you say IG is 0. Where I have written IG here? Tell me, Dinesh. Where you have written IG? Okay, fine. Let's think here first. Let's think here in this analysis now. I've used only voltage conditions. I am repeating this statement again and again for you. To give the connections for the sequence network, I am using only voltage conditions because after the fault has been occurred, I was clearly know about my voltages. What is phase A voltage? What is phase B voltage? What is phase C voltage? What is the relation between these three? That I know clearly. Following all of you, I don't know about currents. As the three conductors are shorted, I'll say simply VA equals to VB equals to VC. I don't know about currents. As the three conductors are shorted to ground, I will say all the three voltages are 0. I don't know about currents. How the currents will be means, those currents you should calculate from this circuit now. What is IA1 current here? Will it exist or not? IA1 current, will it exist or not? Yes? Will it exist or not? This is pre-fault voltage VPF1 by Z1 equivalent. That is IA1 current. What is IA2 current? Will it exist or not? Yes. What is that? Pre-fault voltage 2 by Z2 equivalent. Okay. What is IA0 current? That is 0. Because it is open already. IA0 value 0. Means you have positive and negative sequence current existing if you have a triple fault. Negative sequence current also existing in this pre-fault unbalanced state. Next one, you see here. What is IA1? Pre-fault voltage VPF1 by Z1 equivalent. You get same number as previous now. You get this number same as previous. Same as previous. What is IA2 current? Pre-fault voltage 2 by Z2 equivalent. You will get same current as previous now. Same negative sequence current. What you get in triple L fault, you will be getting for triple LG also. What is zero sequence current here? Will it exist or not? Zero sequence current. Will it exist or not? Tell me your answer. Yes, it will exist. How much is that? That is 0 pre-fault voltage VPF 0 by Z0 equivalent. Z0 equivalent. Can you please tell me what is phase A current in the previous case? After the fault has been occurred, it is IA1 plus IA2 plus 0. IA1 plus IA2 plus 0. That is a phase A current. What is phase A current in this case? It is IA1 plus IA2 plus one more current is added here as IA0. One more current is added here, that is IA0. Okay. Now you tell me please, in your view, phase current in the triple LG fault, IA1 plus IA2 plus IA0, phase current in triple L fault is simply IA1 plus IA2. Which phase current is more now? During which fault phase A current is more? During which fault phase A current is more? Generally, it is a triple LG. Generally, it is triple LG. Now, you tell me which fault is more severe to you? Which fault is more severe to you? Is it triple L or triple LG? Which is more severe? Triple LG fault is more severe than triple L fault. When? If the pre-fault system is unbalanced. If the pre-fault system is a balanced one, both will give same value of phase A current. Both fault analysis will give same value of phase A current. Okay? I think all of you getting this point what I have discussed till now. So therefore, the final conclusion is that triple LG fault is more severe than triple L fault. If the pre-fault system is unbalanced. If the pre-fault system is unbalanced. This is also one of the untapped area in the examination. It is also one of the untapped area in the examination. Okay. How, Dinesh? You tell me the answer. Sir, you say fault current IA in the triple LG fault. How? Huh? Ground current is 0, I am saying. Ground current is 0 in case of balanced case. If ground current is 0, will you give 0 as your answer for the fault current? We have to consider one of the phase current as a fault current in that situation. I repeated this one many times, but still you are asking me same question again and again. How you have considered? Huh? If ground current is equals to 0, we should consider any one of the phase current as fault current here. Okay. Yeah, done. Let's say one small problem here based on this voltages. Very small problem we are going to consider here. Let's look at this one. Go through this problem. It's a very simple problem. Very, very simple problem. It is a test for you whether you have understood the previous discussion or not. It will test you. Test your understanding exactly of the previous discussion. Check this one. Yeah, it's okay. Is in a power system network, the pre-fault voltages at a bus bar are given as VA 1 at an angle 0, VB 1 at an angle minus 90 degree, VC 1 at an angle 90 degree in the per unit form. Find phase A voltage at that bus bar for first one, 3-phase ungrounded fault at the bus bar. 2, 3-phase to ground fault at the bus bar. 3-phase to ground fault at the bus bar. Look here. See, first of all, in the problem, what they said is pre-fault voltages of the bus bar are VA, VB, VC. Generally, pre-fault voltage means we used to take the notation as PF in the what we call as a suffix, else E. Okay, okay, whatever. First, I'll write pre-fault voltages. Pre-fault voltages. Give your answer for the first one. Give your answer for the first one. Pre-fault voltages. Pre-fault voltage of phase A, 180 angle 0 degree. Pre-fault voltage of phase B, 180 angle minus 90 degree. Pre-fault voltage of phase C, 180 angle plus 90 degree in per unit form. Okay. If you have a three-phase ungrounded fault, just look back to the three-phase ungrounded fault circuits. Whether the voltages are balanced or unbalanced here. Whether these voltages are balanced or unbalanced. Any of you, please tell me first. Whether these voltages are balanced or unbalanced. Unbalanced voltages. Unbalanced voltages means, let us think about these circuits. Triple fault, ungrounded fault. What is phase A voltage here? That is nothing but VA naught, right? VA value, phase A voltage, is nothing but VA naught. What is VA naught value here? That VA naught value is nothing but zero sequence pre-fault voltage. Zero sequence pre-fault voltage from the network analysis. All of you getting the statement? Zero sequence voltage is equals to phase A voltage. From network analysis, as this is carrying zero current, we have a zero voltage drop here. Whatever the source voltage you have, VPF 0, that itself is a value of VA naught. Okay? Yeah. So I can say from this first one, for three-phase ungrounded fault, post-fault phase A voltage, is equals to what? Is equals to pre-fault zero sequence voltage of the phase A. Pre-fault zero sequence voltage of the phase A. Just from this network analysis only, I am saying that one. VPF 0 is nothing but the VA value. Okay. So what is that pre-fault zero sequence voltage? See, from these things, if you attempt to calculate that pre-fault zero sequence voltage value, that is 1/3 pre-fault phase A voltage, pre-fault phase B voltage plus pre-fault phase C voltage. Okay, so this you are going to get like 1/3, 1, and 1 at an angle minus 90 degree means minus J1, 1 at an angle plus 90 degree means plus J1. J1 minus J1 will be cancelled out. You get this number simply 0.3333 per unit. So this value is nothing but 0.333 per unit. That's it. Which phase voltage is that? Which phase voltage is that? Is it phase A, phase B, phase C? All the three are only phase A. All the three are equal. In case of triple fault, all the three phase voltages are equal. That is nothing but 0.3333 per unit. That's it. Okay. What is second one? If it is a three-phase grounded fault, tell me please. Three-phase grounded fault, what will happen to phase A voltage? 0. Because already phase A is grounded, right? Already phase A is grounded. You don't need to bother what is the zero sequence pre-fault voltage and all. It will be simply 0. Okay. So for second one, I can say for three-phase grounded fault, three-phase grounded fault. Okay. So post-fault phase A voltage. Post-fault phase A voltage. Phase A voltage that is equals to 0. Post-fault phase A voltage is equals to 0. Okay. Next. So let's have a small comparison between all types of faults what we have discussed with some conditions. With some conditions, I'm going to take up that. Right? Some conditions. Let's move to the next slide. So comparison between different types of faults I'm going to take. Comparison between faults, different faults with some conditions. Conditions means first condition, I am assuming that pre-fault system is balanced. Okay. Pre-fault system balanced. System is balanced. And fault impedance is equals to 0. Means fault what we are considering here is solid fault. Fault what we are going to consider here is solid fault. Okay, for those things only we are going to take up these comparisons. Yeah, just have a look at this one. So I'm showing type of fault here. What will be the relation between sequence currents? What will be the relation between sequence voltages? What is fault current formula? Or what's the fault current in terms of symmetrical components? Sequence networks required to find out fault current. Sequence networks required to find out the fault current. Yeah, first one. Type of fault I am saying LG. Type of fault I am saying LG. How about the relation between sequence currents? How about the relation between sequence currents here? All the three sequence currents are equal. IA0, IA1, IA2. All the three sequence currents are equal. Just recall the things what we have studied about the LG fault. Nobody is answering. Yes. All the three sequence currents will be equal. So IA1 equal to IA2 equal to IA0. What will be the relation between sequence voltages? What will be the relationship between sequence voltages? Sum of the three sequence voltages will be equals to 0. Sum of the three sequence voltages will be equals to 0. VA1 plus VA2 plus VA0 value equals to 0. Write it. Okay. What is fault current in case of LG fault? 3 times of the zero sequence current. 3 times of zero sequence current as a fault current. Yeah. 3 times of zero sequence current is a fault current. What are the sequence networks required to find out fault current? What are the sequence networks required to find out the fault current? All the three. Positive, negative, and zero. All the three sequence networks we have to use to find out the fault currents, right? I'll write simply positive sequence network, negative sequence network, as well as I should take the zero sequence network also. Zero sequence network also. Next thing, double line fault here. Double line fault. What's the relation between sequence currents in case of double line fault? Just think back, look back to the yesterday class of double line fault and tell me what will be the relation here? What will be the relation? In case of double line fault, zero sequence current will not exist. It will be zero only. Whereas summation of positive and negative sequence currents will be equals to 0. Summation of positive and negative sequence currents is 0. Zero sequence current will be equals to 0. That's the relation. Else you can write IA2 equals to minus IA1. IA2 equals to minus IA1. Like that also you can write. I'll show here. In bracket, IA2 value equals to minus IA1. IA2 value is equals to minus IA1. Like that you can see. Next thing. How will be the voltages here? Sequence voltages. Relation between sequence voltages. Zero sequence voltage value was 0. And positive and negative sequence voltages are equal. Positive and negative sequence voltages are equal. What is fault current? Minus J root 3 times of IA1. Fault current is minus J root 3 times of IA1. Tell me your answer. Which sequence networks are required to find out the fault current? Which sequence networks are required to find out the fault current? We need to go with only positive and the negative sequence networks. That's it. We no need to take up the zero sequence network at all in case of LL fault analysis. Okay. So positive and negative sequence networks are sufficient. Next one. Double line to ground fault if you have. Double line to ground fault if you have. What is the relation between sequence currents in case of double line to ground fault? Sum of the three sequence currents equals to 0. Phase A sequence currents are equals to 0. Assuming that fault is on BC conductors. Assuming that fault is on BC conductors, IA0 plus IA1 plus IA2, that summation is equals to 0. IA0 plus IA1 plus IA2, that summation is equal to 0. How are the sequence voltages relation? All the three sequence voltages are equal. VA0 equals to VA1 equal to VA2. VA0, VA1, VA2. All the three sequence voltages will be equal. What is fault current in case of double line to ground fault? Ground current we are treating, provided that if it is existing. If you don't have the ground current, means if the ground current value was 0, we should select any one of the phase current as fault current. Okay, but generally in case of double line to ground fault, ground current itself we are treating as fault current. 3 types of the zero sequence current. Which sequence networks are required to find out fault current? All the three. All the three sequence networks are required to find out the fault current. Fine. Next one. Already we said the conditions here. One is pre-fault system is balanced, I said. Fault impedance equals to 0. If the pre-fault system is balanced there, definitely I can say triple L and triple G faults are identical to each other. Triple L and triple G faults are identical to each other. So I can say either it is triple L fault or you can say triple G. Triple L fault or triple G. Both will be same. Both will be identical. Both will be identical. Next, tell me. How will be the sequence currents here? In case of triple L and triple G faults, sequence currents. IA1 existing, it is non-zero number. IA2 current 0. IA0 current also 0. IA1 current is non-zero. IA2 current will be 0. IA0 current will be 0. How will be the sequence voltage here? VA1 value 0. VA2 0. What is VA0? That is also 0. VA0 value is also equals to 0. All the three sequence voltages are 0. What is fault current in case of this fault? Positive sequence phase A current is a fault. Positive sequence phase A current is a fault. Which sequence networks are required to find out the fault current? Only positive sequence network is sufficient. Only positive sequence network is sufficient to find out the fault current. Getting all of you? Yes. Yeah, all of you getting this table? Please tell me. So I'll say now. Very, very simple theoretical questions I will ask you. Okay. Which sequence network will exist in all types of faults? All types of faults. Tell me your answer. Which sequence network will exist in all types of faults? Positive. Okay. Fault synthesis, fault analysis. Fault analysis. So answer will be obviously positive sequence network will exist in all types of fault analysis. Okay, next one. During which fault analysis? During which type of fault analysis? Which type of fault analysis? Fault analysis. During which type of fault analysis? Zero sequence network will exist. Zero sequence network will exist. Tell me please, in which type of fault analysis zero sequence network will exist? LG and LLG. You say grounded faults. Grounded faults except what we call triple LG. Except triple LG, for remaining faults we can have it. Okay. So answer will be grounded faults are grounded unsymmetrical faults. Grounded unsymmetrical faults. Grounded unsymmetrical faults. That is, grounded unsymmetrical faults are LG and LLG. LG and LLG. Means if the fault is associating with ground, zero sequence network will come into what we call zero sequence network may come into the network analysis. That's it. Okay, next one. In which types of fault analysis negative sequence network will exist? Next one. In which type of fault analysis negative sequence network will exist? Which type of fault analysis negative sequence network will exist? Yeah, tell me please. All unsymmetrical faults. All unsymmetrical faults. Unsymmetrical faults means LG, LL, LLG. For these types of faults, we will have the what we call negative sequence network existence. So answer will be all unsymmetrical faults or unbalanced faults. Unsymmetrical all unsymmetrical faults. That is LG, LL, LLG. For these types of faults, we have the negative sequence network existence. Done. Next. Next, I will take one more simple problem here. Just look here. Yeah, so I'm taking up in the next slide. Next question, you can say. Observe here this problem. A fault on a system gives the following conditions during the fault. Okay, IA1 Z1 0.2, IA2 Z2 0.2, IA0 Z0 0.6. What type of fault is that? Yeah. What type of fault is that? Anybody? IA1 Z1 value is at 0.2. IA2 Z2 value was 0.2. IA0 Z0 value was 0.6. What type of fault it may be? It may be. Yeah. First listen. How to analyze this? See, you have IA1 Z1, IA2 Z2, IA0 Z0. By using these things, we are capable to get the values of VA1, VA2, VA0, right? VA1, VA2, VA0. These are prescribed equations. For any type of fault, I can say VA1 is nothing but pre-fault voltage minus IA1 into Z1. For any type of fault, VA2 is equals to minus IA2 into Z2. For any type of fault, VA0 is equals to minus IA0 into Z0. Like this, you can write. Values may be different from one fault analysis to other fault analysis. That's okay. But equations will be as it is for any type of fault. Is it a LG fault, LL fault, LLG fault, or anything? VA1 is EA1 minus IA1 Z1. Means, according to the data given, VA1 will come to be EA1 minus IA1 Z1 is 0.2. EA1 minus IA1 Z1 is 0.2. What is VA2? Minus IA2 Z2 means it will be minus 0.2. What is VA0? Minus IA0 Z0, so it will be minus 0.6. 0.6. First of all, if it is triple LG fault, all the three sequence voltages must be 0. As it is not the case, triple LG is not the answer. Okay, next. In case of double LG fault, positive sequence and negative sequence voltages must be equal. Or all the three sequence voltages must be equal. But it's not the case, right? It's not the case. So LLG is also wrong answer. What you should say for LL fault? LL fault, you should not get any zero sequence voltage. You should not have any zero sequence voltage. That's also wrong. And only one option left here is LG fault. Is there any possibility of saying this fault is LG? In case of LG fault, sum of the three sequence voltages equals to 0. Three sequence voltages will exist and sum of these three will be 0. If you sum up these three, what you get now? EA1 minus 0.2, minus 0.2, minus 0.6. So it will come to be EA1 minus 1. EA1 minus 1. So there is a possibility to say that that value will be equals to 0 by assuming that pre-fault voltage is equals to 1. In that way, I can say that this fault may be of LG type. So your correct answer from the options given will be A. Yeah. Good. Clear all of you? Even though that EA1 is not equals to 1 per unit. But still you have some voltage existing. Maybe it is a fault with fault impedance. That situation you can read. I think all of you understanding this? Tell me please. Yeah, next. One more small problem I will consider. Yeah, I need your response. Have you understood this? Please raise your hands. I will move to next one. These are simple problems only. Sir, if VA0 equals to 0.2, we can say it as LLG. It may not be. To have that fault as LLG, VA1 and VA2 must be equal. VA1, VA2 must be equal. Okay. That chance you may not get. One minute. Yeah. So I'm taking one more problem here. That's what we have done just now. Yeah. Please tell me this answer. It's also a very simple one. This problem is also very simple one. Sir, can EA1 be negative? It may not be. Anonymous certainty, EA1 value will not be negative. Look here, a fault takes place on an unbalanced system given the post-fault voltage as VA 1 per unit. After the fault occurrence, phase A voltage 1, phase B voltage minus 0.5, phase C voltage minus 0.5. What might be the type of fault? What might be the type of fault? Anybody tell me? Look here, Ajay, look here. Post-fault voltages are VA 1 per unit, VB minus 0.5, VC also minus 0.5. First one, triple L. See, in case of triple L fault, all the three voltages are zero. After the fault has been occurred, in case of triple L fault, all the three voltages are zero. So triple L is not our answer. Okay. In case of double line to ground fault, definitely two voltages will be zero, right? Two voltages will be zero, definitely, if you have a double line to ground fault. So double line to ground fault may not be a proper option. Okay. So in case of double line fault, you expect that all the three voltages will be existing because no phase is connected to ground, right? A is not connected to ground, B is not connected to ground, C also not connected to ground. In that situation, all the three voltages may exist. Not only that, as it is LL fault, two voltages will be equal. Two conductor voltages will be equal. Other one will not be equal to the remaining two. Here it is satisfied that VB equals to VC. VB equals to VC. VA is not equals to that VB and VC. So there is a good chance to say that this fault is LL. Okay. And what about this LG? What about this LG? See, in this LG fault, any one of the phase voltage is zero. One phase voltage must be equals to zero. So I can say this is not a proper one to be chosen. Yeah, Yogashri, VB equals to VC, LG option A. What does that mean? If you have a LG fault on phase A voltage must be zero, right? But it is given 1 per unit. Or else you say, if you have a LG fault on the system, any one of the phase conductor voltage must be equals to zero, which is a faulted phase. Faulted phase voltage is zero. But he is saying all the three voltages are non-zero. So 0.5 means approximately zero, na? Who said 0.5 is close to zero? Who said it is 0.5 is approximately zero? 50%. It's okay. Yeah, fine. Next, let's take some more what we call final questions with respect to fault analysis. As a conclusion of all the types of faults which we have discussed, we are going to take up some problems. Yeah. So let's move with the next slide. See this one? Now there is one diagram. This is in your PDF actually. Shown this diagram in the next slide. Yeah, first you read this question. Read this question. Venkatesh, even though LN fault is ungrounded neutral, it will be zero sequence voltage will be zero only, right? Zero sequence voltage will be zero. Yeah, read this question. Two power stations, Cap A and Cap B. Two power stations, Cap A and Cap B has short circuit capacities with respect to their 400 kV buses. With respect to their 400 kV buses are 4000 MVA and 2500 MVA respectively. Two systems are there, AB separate, at their 400 kV buses. First system, short circuit capacity 4000 MVA. Second system, short circuit capacity 2500 MVA. Next, these two 400 kV buses are interconnected by a series reactor of 16 ohms reactance. These are interconnected by a reactor of reactance value 16 ohms. Okay. Find the highest value of short circuit capacity at any 400 kV bus. At any 400 kV bus, you have to find out the highest value of the short circuit capacity, or at any station terminal after doing the interconnection. Both statements are same, at any bus or at any station terminal. Look at this diagram. This is station A with short circuit MVA as 4000 MVA. Station B, short circuit MVA 2500. These are the 400 kV buses. These are interconnected by interconnecting reactor XR 16 ohms. 16 ohms. Okay. Yeah. Now, after doing that interconnection, we have to find short circuit capacity at the station A terminal, then short circuit capacity at station B terminal. After calculating these two numbers, whichever comes as high, that we should give as our answer. I think you are clear about this. I think you are clear. Okay. See, we know generally the formula for short circuit MVA, generally short circuit MVA equals to S base or base MVA, anything you can write. S base or base MVA by X equivalent per unit form. By X equivalent in per unit form. Base MVA by X equivalent value in per unit form by making all the assumptions what we said earlier. Pre-fault voltage assumed as 1 because he didn't give that in the problem. He didn't mention about resistances in the network. We are going to assume that resistances are 0. Okay, after making all those assumptions, we use it to say short circuit MVA equals to base MVA by X equivalent in per unit. See, obviously, after doing interconnection, to find out short circuit MVA with respect to this bus, we have to find out X equivalent with respect to this bus. X equivalent with respect to this bus, and that you substitute there, you will get the short circuit MVA. To find out X equivalent with respect to this bus, definitely we should know what is the internal reactance of station A. What is internal reactance of station B? Yes or no? So to know the internal reactance of station A, they mentioned the short circuit MVA at the bus A. Means station A short circuit MVA they have mentioned. To know the internal reactance of B, they mentioned the short circuit MVA of the station. We have to utilize these two to find out the equivalent circuit of station A in the Thevenin model, equivalent circuit of station B in the Thevenin model. That we should do first. After that, we should go for the whole network. Okay? Yeah. So let us say station A here. Station A. So this is represented simply in this manner in your single line diagram. But in your per phase model, it is going to be represented with a voltage source and the internal impedance. and this is a neutral terminal. Zero potential, zero potential. This voltage generally we treat as 1 per unit. This voltage generally we treat as 1 per unit. And this reactance you assume as XA. XA. Please give some flexibility to me. I am not using J symbol here. I'm not using J symbol. I'm going with only reactances as whole network is pure reactive in nature. Okay, fine. What is it XA? XA. See, already you know short circuit MVA at the station A 4000 MVA. Then this XA value in the per unit form is nothing but base MVA by short circuit MVA at the station B. Base MVA by short circuit MVA at the station A. All of you getting my words? Tell me please. Base MVA by short circuit MVA at station A. At station A. What is base MVA? Did he mention anything regarding base MVA in the question? Nothing. Did he mention anything regarding base MVA? You can choose your own number. Let us choose 4000 MVA itself as a base MVA. Let us choose 4000 MVA itself as a base MVA. Based on that, you do calculation of station A reactance, station B reactance, as well as the interconnecting reactance. All. Okay, I'll write. Let base MVA value is equals to 4000. 4000 MVA. Now you can get that XA value in per unit domain. XA in per unit form. Therefore, XA per unit is equals to what you can say base MVA 4000 and short circuit MVA is also 4000, and this ratio will come to be 1 per unit. 1 per unit. That's the equivalent circuit representation of the station. Similar calculation we should do for station B also. Station B. In the single line diagram, it was represented simply like this. Station B. And you can draw this in the per phase model. Per phase model like this. Voltage source in series with reactance XB. Voltage source in series with the reactance XB. Okay, now you know short circuit MVA at station B is 2500. 2500. Now you can find out this XB in per unit form in the similar manner. Base MVA by short circuit MVA. Base MVA value by short circuit MVA at the station B. Short circuit MVA at the station B. So base MVA number 4000 we have chosen in the previous calculation. Short circuit MVA 2500. Anybody tell me what is XB value in per unit form? XB in per unit form. 1.6 per unit. This number is 1.6 per unit. We got both. Now, next I'll take reactor. Reactor reactance in ohms they have given 16 ohms. That we should divide with the Z base to calculate per unit value of it. Yeah. So I'll say reactor. XR is equals to 16 ohms. And already you know S base three phase number. S base three phase number already is selected. Selected this one 4000 MVA. What is V base you should say? 400 kV line to line. Because the operating the rated voltage whatever you have, that itself is a base voltage you have to choose. Okay, because the remaining reactances what you have calculated earlier are on this base only. Are on this base only. Okay, now you can get the Z base value from this. Z base per phase. V base line to line square by S base three phase. Else you write V base per phase square by S base per phase. You give same value. Okay, so this will be 400k whole square by S base is 4000 mega. 4000 mega. So kilo square mega will be cancelled out. Kilo square mega will be cancelled out. I think you may get this number 40 ohms. Is it so? Z base. Is it 40? Yes, 40 ohms. Now the value of XR in per unit form is actual value 16, base value 40. So how much is this value? 16 by 40. 0.4 per unit. This number will be 0.4 per unit. Now we came almost to the end. Almost to the end. Just we will redraw the per phase model with reactor, and we will try to calculate the short circuit MVA with respect to station A as well as with respect to B. Okay. Let's take the next slide. Per phase network. Per phase network. So first station A. The station A bus. Station B. Station B bus. We have one reactor XR, XA, XB. This is a neutral operating at zero potential. Neutral operating at zero potential. Zero. Okay. Next. These internal EMFs will be 1 per unit. Internal voltage will be 1 per unit. Means Thevenin voltage. Now, if you want to find out short circuit capacity with respect to station A terminals, you have to find out that X equivalent value with respect to station A. X equivalent value with respect to station A, we have to calculate. See, just as a network analysis only, by killing the sources of this. By killing the sources, you should do this. By killing the sources. So if you kill the source, simply you observe XB and XR are in series, right? XB, XR will become in series. That series combination will be in parallel with XA. By that way, we will get the X equivalent with respect to station A terminals after doing interconnection. I will write in the next slide. I'll see here, no issue. After doing interconnection, X equivalent with respect to station A terminals, nothing but XA in parallel with XB plus XR. XA in parallel with XB plus XR. What is XA value? We calculate, I think, 1. 1 in parallel with XB plus XR. XR 0.4, XB 1.6. So this number is 2. So 1 in parallel with 2. So 1 into 2 by 1 plus 2. So it will be 2 by 3 per unit. X equivalent with respect to A is 2 by 3 per unit. Now you can find out short circuit MVA with respect to A. New short circuit MVA. Short circuit MVA with respect to station A. New number is base MVA value by X equivalent with respect to station A. What is base MVA number? 4000. X equivalent value 2 by 3. 2 by 3. So how much is this value now? How much will be that value? Anybody? 1200 by 2. I think 6000. You may get this number as 6000 MVA. 6000 MVA is a short circuit MVA with respect to station A terminal. Now, with respect to B, if you do, with respect to B, after doing interconnection, with respect to B, this is with respect to A. Now, with respect to B, if you are talking B, You have to remove this x equivalent A calculation what you have done. So with respect to B, if you talk x equivalent B, simple. XA, XR will be coming in series. XA, XR values will come in series. That series combination will be in parallel with XB. Will be in parallel with XB. Okay? Yeah, let's say. With respect to station B, equivalent reactance is nothing but XB value in parallel with the XR plus XA. Okay, how much is XB number? How much is the value of XB? I think 1.6. In parallel with XR plus XA, I think 1.4. Okay, XA value 1, XR is 0.4. So this number is 1.6 into 1.4 by 1.6 plus 1.4. Calculate this well. X equivalent B, how much? Tell me this number, please. 0.7467 for you. Now you can find out the short circuit MVA with respect to B, new value. Short circuit MVA with respect to B, new value. Same, base MVA selected 4000 by X equivalent calculated with respect to B. So it is 4000 by 0.7467. 7467. How much is this number? 5357 MVA, approximately 5357 MVA. 5357 MVA. So what should be our answer now? What should be our answer? 6000 MVA is our answer. That is happening at the station A terminals. Okay. So answer for this problem is 6000 MVA. The highest value occurring at A terminals. Station A terminals. Occurring at station A terminals. Okay. Interconnection means it is not killing the sources. Vaishnavi. Interconnection is not meaning to say killing the sources. To calculate X equivalent value, we are killing the sources. Yeah, fine. See, for example, without this reactor, if you do this connection directly, means by keeping this XR value 0, what will happen to short circuit capacity at station A as well as at station B? Tell me please. So, for example, I am asking you the same question, same as previous question. Same as previous question. If XR equals to 0, if XR is equals to 0, what is short circuit MVA at A, at station A terminals after interconnection? After interconnection. Anybody? After that interconnection. Simple. Choose the same thing. Base MVA, what we call 4000 MVA, you have to consider. Base MVA, we have to consider 4000 MVA, and we have to draw same diagram. I will show it. Just listen. This diagram I have to put. Okay. So this is a diagram here. Just have a look here. XR value we are keeping 0 because he is asking me to take 0 number. XA value already we said 1. XB value we said 1.6. With respect to station A terminals, you want to find out that short circuit MVA. So you find out X equivalent with respect to A here. X equivalent with respect to A. What you are going to get this one? By killing the sources, you have to calculate X equivalent we said. By killing the sources, we should calculate the X equivalent value. By killing the sources, XB, XR are in series. So XR is 0, XB. XB, XA will be in parallel, that's it. So the equivalent Thevenin reactance with respect to station A, equivalent Thevenin reactance with respect to station A is nothing but station A reactance in parallel with the station B reactance. So 1 in parallel with 1.6, 1 into 1.6 by 1 plus 1.6. Okay, how much is this value? Anybody? Anybody, please tell me this number, how much? It will be 0.615 per unit. 0.615 per unit. Now, what is it? The new short circuit MVA at the station A means 4,000 by this number. 4,000 by this number. So, short circuit MVA new at station A is base MVA value by X equivalent with respect to A. So base MVA 4000 MVA, X equivalent A much is this 615. It will be in terms of MVA. How much is this number? You may get this number 6,500. You may get this number as 6,500. That is nothing but summation of the two short circuit MVAs. That is nothing but the summation of the two short circuit MVAs. What is the short circuit MVA of station A? 4,000. What is for station B? 2,500. Sum of the two, 6,500. See, this is with respect to A as well as with respect to B also. This is with respect to A as well as with respect to B also. Now, the simple conclusion, what you have to understand here is, whenever you are going for interconnection of number of systems together, if you go for direct interconnection without any reactor, the resultant short circuit MVA is higher in number. But if you interconnect the systems with a reactor of some non-zero reactance value, as we have done earlier, the short circuit capacity value is going to be decreased. Whenever the short circuit capacity value was decreasing, obviously we can say the chances of getting the breaker rating will be less. Fault level on the system is decreasing, and breaker rating also, required breaker rating also going to be reduced. That's why whenever you go for interconnection of number of systems together, it is better to interconnect the systems through interconnecting reactors. Okay, any name the people will say. Sometimes the people will say busbar reactors, sometimes generator reactors, sometimes feeder reactors. The purpose of all these reactors will be same, in order to reduce the fault level or in order to reduce the required breaking capacity of the circuitry. Okay, so I will say here, by using interconnecting reactors, in bracket of non-zero reactance value, the fault level in the system decreases, or you can say short circuit capacity of system reduces, or the circuit breaker rating required will be less. Circuit breaker rating required will be less. I think all of you getting my point. Yeah, you can call this as current limiting reactor also. Yeah, S-base is remains same for all the system, right? If you select S-base at one place, that S-base is common for all places. Circuit breaker rating required will be less. Okay, done. Next. Let me tell you. With XR value only we are proceeding. Okay, I'll show here. With XR is equals to 16 ohms. What they said. With XR is equals to 16 ohms. else I'll take that diagram only. If you don't confuse, I will give it. Yeah. 1 minute, please. Original diagram. This one only I am considering. So, let me clean this. It's not needed now because these are old values. Without interconnection, you have those numbers. It's a 4N kV bus already. It's also a 4N kV bus already. Okay. And this is a XR value which we have considered as how much? 16 ohms means in per unit it is 0.4. You may confuse again. You will ask me again and again, it's the same question. 0.4 per unit. See, this XA of this station is 1.0 per unit. Station B is 1.6 per unit. Actually, at these 400 kV buses, what I have shown, definitely some 400 kV lines are running out, feeders. 400 kV feeders are running out, supplying power to some area. Maybe I can say this is one 400 kV feeder running, right? And this is another 400 kV feeder running lines. But we will be assuming that now these feeders are at no load condition. That's the assumption. That is the assumption. Just listen to my words. Earlier, without this interconnecting reactor, look this one. Without this interconnection, whatever the feeder 1 demand you have, it has to be met by station A only. Whatever the feeder 2 demand we have, that should be met by the station B only. That's it. But sometimes the power generation by the station A may be less. Sometimes during operation, if the power generation by station A is less, this feeder may not be satisfied at its full extent. In that situation, there should be some other supply also, second supply also to meet the load demand on this one. That's the purpose of doing the interconnection generally. Okay, why we do interconnection between the systems means to have good reliability, to meet the load demand all the time, right? To meet these requirements only, we are going for the interconnection. But problem after doing interconnection is short circuit capacities of system is increasing. Problem after doing interconnection is short circuit capacity of system is increasing. And in order to reduce that short circuit capacity, you don't go for a just interconnection, you go with the impedance interconnection. Maybe reactor interconnection we are suggesting. I think all of you getting my words. Are you clear about this? Please tell me. Yes? Yeah, okay. Now, tell me please. I am keeping one circuit breaker at this place. I am keeping one more circuit breaker at this place. These feeders are at no load. Now, what is the rating of this circuit breaker to be designed? With how much rating I should design this circuit breaker? With how much rating this circuit breaker has to be designed? That's the question. All of you getting me? Tell me please. See, you have some methods to calculate the breaker ratings already, right? If you want, you follow those methods. Else you can take up the values what you have done earlier also. But I will follow the methods. Circuit breaker 1 is this symbol. Circuit breaker 2 is this symbol. Now, to find out the breaker 1 rating, take the fault nearby the breaker 1. After taking fault nearby the breaker 1, something like this. This A will supply some current. B will also supply some current. And you see the thing, both currents, whatever the current supplied by station A, whatever the current supplied by station B, both are going into breaker and then going into fault. Both currents are going into breaker and then going into the fault. What is current supplied by A? 1 per unit voltage by 1. 1 per unit is the current supplied by A. What is current supplied by B? 1 by XB plus XR, that will be 1 by 2, that is 0.5 per unit. I think all of you getting what I am saying here. Is it clear? Is it clear? Both currents are going into breaker 1. Both A current is going into breaker 1. B current also going into breaker 1. Some of the two currents you have to consider to design the breaker 1 rating. So, CB1 interrupting current. Interrupting current. Nothing but 1 by 1, it's a current by A. 1 by 2, it's a current by B. So 1.5 per unit. Now, what is the CB1 rating? Formula for CB1 rating. Per phase voltage in per unit form, current interruption multiplied with base MVA. Multiplied with base MVA. This number will be 6000 MVA. So we have to design the circuit breaker 1 with a capacity of 6000 MVA. Capacity of 6000 MVA. All of you getting my words? That's your wish. How you do the analysis? How you do the analysis? Is it KVL, KCL, whatever it is? Doesn't matter. Okay, done. Next, how to find out the breaker 2 rating? How to find out the breaker 2 rating? Now, what you have to do is, you take the fault very close to breaker 2 now. You take the fault very close to breaker 2. Now, how much current this station B will supply? 1 by 1.6. 1 by 1.6. And how much current this A will supply? 1 by 1.4. Actually, to this fault location, I am getting current from only one side. That's a breaker 2 current only. That's a breaker 2 current only. Whatever the B current supply, that is flowing into breaker. Whatever the current A current supply, that's also flowing into the breaker. Means how much current the breaker 2 has to interrupt? How much current the breaker 2 has to interrupt? CB2 interrupting current. CB2 interrupting current. Yeah. How much? By station A, 1 by 1.4. By station B, 1 by 1.6. You will get some value. And circuit breaker 2 rating, if you calculate phase voltage per unit number into 1 by 1.4 plus 1 by 1.6 is a breaker 2 interrupting current into 4000. I think you will get this number 5357 MVA. 5357 MVA. Yeah, dear anonymous attendee, you have to consider what is the current flowing in the breaker. Whether both currents are flowing in the breaker or not. Whether both currents are flowing in the breaker or not. Tell me, I need your response, Mr. Anonymous attendee. Whether both currents are flowing in the breaker or not. Yeah. Then it will be, means this breaker has to interrupt both currents. Both currents it has to interrupt. Means some of the two is a current flowing in the breaker, which has to be interrupted by the breaker. Following all of you? Right, fine. So circuit breaker 2 rating, what you have selected? Circuit breaker 2 rating. Yeah, dear Pramod, what's the doubt you have? Could you please express what's the doubt you have, Pramod? You have asked me something. What's your doubt exactly? Please tell me. Pramod, are you there, Pramod? Yeah. Pramod, I need your response. Please tell me what's the doubt you have. If you don't want all these things, you can leave, no? If you are feeling that what subject we are studying, you can leave. I am discussing about breaker here, circuit breaker. Why you are why you are unable to catch up this one? Yeah, fine. Next, look here. For example, if we keep one breaker at this place also we'll keep one breaker. At this place also we'll keep one breaker. See, while you are calculating this breaker rating, this circuit breaker 3 you take, and this is circuit breaker number 4 you take. Okay, the circuit breaker 3 and 4 ratings if you take, it's not Pramodra, it's not Pramod Raj. There is another Pramod. Yeah. See, circuit breaker 3 rating, circuit breaker 4 rating, if it is required to calculate. How to calculate means at that time you see, take faulted breaker 3, you get current supply from A as well as you get the current supply from B also. At that time, any one of these two currents will be interrupted by the breaker, not both. KCL application. Simple KCL application. At that time, you should show your discrimination. Which current is high, which current is low, based on what we have to design the breaker. Similarly, circuit breaker number 4 also. Okay, fine. For example, same thing with XR is equals to 0 if you are the value of XR is equals to 0. Means zero internal reactance. Zero internal reactance. So zero interconnecting reactance. Let me clean all these things again. It's not needed for me. Okay. It's a 400 kV bus. We know already. Yeah. And this XR value we are considering as 0. XR value we are considering it as 0. I'll show this fader, this manner, fader. And again, you say this fader is operating under no load condition. Fader is operating under no load condition. We know reactance of station A 1 per unit. Reactance of station B already we calculated 1.6 per unit. 1.6 per unit. Yeah. Tell me please. Tell me. Now in this particular situation, if you are attempting to keep one breaker at this place, with how much rating we have to design it? Again, what you have to do is you take a fault at this place. Okay, find out this A is supplying some current, B is also supplying some current. Both currents are going into the breaker and then into the fault. Means breaker requires to interrupt both current at a time. Both currents at a time. So I can say here, breaker 1, circuit breaker 1, in this case, interruption current, CB1 interruption current supplied by A 1 by 1 per unit. Current supplied by B is 1 by 1.6. 1 by 1.6. You will get some number in per unit form. And what is the CB1 rating required here? CB1 rating required. Phase voltage per unit value into 1 plus 1 by 1.6 is a current to be interrupted into 4000 MVA is a base. How much is this number? Tell me please. How much is this number? This will come to be 6,500. 6,500. See, in the similar way, you calculate the other breaker also. This will come 6,500. You do that calculation. So this will come 6,500 MVA capacity required. And this breaker I will keep here. Circuit breaker number 2. This breaker also required to have a capacity of 6,500 MVA. So this is what I am asking you to compare, exactly speaking. With zero interconnecting reactance, both breakers requires to have 6,500 MVA capacity with some XR is equals to 0.4 per unit. Circuit breaker 1, 6,000 MVA. Circuit breaker 2, 5,357. Yeah, 357 MVA. By that way, the required breaker breaking capacities will be less. Okay, by using this interconnecting reactors. I think all of you getting this one? Yeah, definitely. Voltage at the bus bar will decrease after the fault has been occurred. Yeah. So this is end of this what we call reactors and all. After break, we take some more problems as a conclusion in the fault analysis, and we will wind up this. Okay. So have a break for 15 minutes. 15 minutes break. Okay. I have resumed the audio, video and screen. So please kindly confirm. Fine. So let's continue with the next problem in this fault analysis. See this one. A 100 MVA 20 kV three-phase synchronous generator was subjected to different faults. The fault current for LG and LL faults are 4,200 amperes and 2,600 amperes respectively. What is the per unit zero sequence reactance? What is the per unit zero sequence reactance? Okay, see this. See, this is a 100 MVA, 100 MVA three-phase rating. Three-phase rating and 20 kV, it's a line-to-line voltage value. Subjected to different faults. LG fault current at the terminal of the alternator, it is given as 4,200 amperes. And LL fault current at the terminals of the alternator is 2,600 amperes. What is the per unit zero sequence reactance of the generator? How much is the per unit zero sequence reactance of generator? Yeah, look here. See, the way of solving this problem will be in this manner. If you think about line to ground fault current formula, 3 into pre-fault voltage by Z1 plus Z2 plus Z0. If you think about line to line fault current formula, minus J root 3 times of VA1 VPF by Z1 plus Z2. The idea is calculate the value of Z1 plus Z2 from LL fault current. Calculate Z1 plus Z2 from LL fault current. That you substitute in LG, you will get the value of Z0. That's the idea. But in this problem, we have to take many assumptions. Right? Many assumptions we have to consider. First assumption is this alternator is lossless. Okay, we don't have any resistance for the alternator. That is the first assumption you have to take. He didn't mention anything regarding grounding of neutral. So we have to assume that this neutral is solidly grounded. Didn't mention anything about pre-fault voltage. We have to assume that pre-fault voltage is rated value. These are some assumptions you have to take for this question specially. Okay, so I can say first, let us assume alternator is of solidly grounded neutral. Solidly grounded neutral, and pre-fault voltage is rated voltage. Pre-fault voltage is equals to rated voltage, I can say, and lossless. Alternator is lossless. Okay, yeah, fine. Next. He is asking per unit zero sequence reactance. So whether we do this problem in the absolute domain or per unit domain, that we have to decide. First. Let's do in per unit only. Means this 4,200 what you have, that we convert into per unit current. Line to line fault current also we convert into per unit, and we continue with the per unit analysis only. So you get X0 value in terms of per unit by choosing this 100 MVA 20 kV as base. Clear? Right. First, you calculate the base current by using these two. By that way, we can get the LG fault current magnitude in the per unit form, LL fault current magnitude in the per unit form. Okay? Yeah. So I'll say first, base current from the base values what we have selected is, it is 100 MVA three-phase MVA base by root 3 into 20 kilo. So you please calculate this base current. How much? Please calculate this base current. How much? It is 2886 amperes, I think. 2,886 amperes. 2,886 amperes. Yeah, fine. Now, what is that LG fault current value we have? LG fault current. Only magnitude of LG fault current in per unit form. If you are interested to know, the actual value 4200 by base current is 2886. 4200 by 2886. Yeah. How much is this one? How much is this value in per unit form? Anybody? Tell me this number in per unit form. Yeah. Please tell me. So it will be 1.455. You say 1.455 per unit. That's the LG fault current in per unit form. And what is LL fault current in per unit form? LL fault current in per unit form. IFLL magnitude. The actual value, you know, it is 2600 actual value. By base current is 2886. How much is this value in per unit form? Calculate LL fault current in per unit form. 0.90 or 9, close to 0.9. 0.9 per unit is a LL fault current. So immediately what I'll do is that LL fault current formula by making all the assumptions. Will be like this. So it is minus J root 3 times of pre-fault voltage by Z1 plus Z2 magnitude. Z1 plus Z2 magnitude. So numerator you have root 3, pre-fault voltage 1, and Z1 plus Z2 you can replace with X1 plus X2 simply. Z1 plus Z2 you can replace with X1 plus X2. So X1 plus X2 will be root 3 by line to line fault current. So means it is root 3 by 0.9 we have to write. I think all of you follow this one. Based on these assumptions, pre-fault voltage rated value is 1 per unit. And only magnitude we are considering. Z1, Z2 replaced with X1, X2 because alternate is lossless. JX1, JX2 magnitude is X1 plus X2 we can write. Let's move. So we can say here X1 plus X2 value will be equals to root 3 by 0.9 in per unit. How much is this X1 plus X2 number? X1 plus X2. So 1.9245 you get. 1.9245 per unit is a value of X1 plus X2. Next, LG fault current we take. LG fault current. IFLG magnitude as it is 3 into pre-fault voltage by Z1 plus Z2 plus Z0. Z1 plus Z2 plus Z0 magnitude. Okay. And you take this one, 3 into pre-fault voltage is 1, you write. And magnitude of the Z1 plus Z2 plus Z0 is nothing but X1 plus X2 plus X0 in the per unit form. And what is this LG fault current you have in per unit form? LG fault current in per unit form 1.455. 1.455 per unit. 1.455 per unit. So from this you can write X1 plus X2 plus X0 number. X1 plus X2 plus X0 number. It is 3 by 1.455. 3 by 1.455. You please tell me this number. You get 2.062 per unit this number. 2.062 per unit. Already we know X1 plus X2, right? That is 1.9245 plus 0 sequence reactance X0, 2.062. And if you calculate X0 value, 2.062 minus 1.9245. How much is this value? How much is 0 sequence reactance? 0.138 per unit. 0.138 per unit on the base values of 20 kV, 100 MVA. 20 kV, 100 MVA. So this is a type of model in the exam. They will give different types of fault currents, and they used to ask you what is a positive sequence reactance or negative sequence reactance or 0 sequence reactance. But this is one model in the various examinations. Okay, let's take one more problem. So I'm moving with the next slide. Yes. So I'm giving this one. Go through it. This is a type of confusion problem again. To tell you some more thing, to tell you some more point in the fault analysis, I was interested to do this problem. I was interested to do this problem to tell some more thing in the fault analysis. Okay, take up this. A synchronous generator has sequence impedances Z1 J0.2 per unit, Z2 J0.14 per unit, and Z0 J0.07 per unit. Z1, Z2, Z0 values are given for the synchronous generator. Next thing, find LG, LL, LLG, triple L fault current magnitudes at the terminals of the alternator. Assume that the generator neutral is solidly grounded. Assume that generator neutral is solidly grounded. Okay, very simple. I am asking you to calculate all the types of fault currents in this particular case. Let's do quickly. First one, LG fault. LG fault we are considering. So this is alternator. Alternator neutral is connected to ground solidly like this. And these are the three terminals I am showing. Sequence impedances of the alternator already given Z1, Z2, Z0. You will take up those numbers according to the requirement. For example, if you have phase A to ground fault here. Phase A to ground fault. Okay. And whatever the fault current you say and phase A current both are exactly equal in this case. Fault current, phase A current both are exactly equal. Whatever. What is fault current formula? In case of LG, what is fault current formula? 3 times of pre-fault voltage value by Z1 plus Z2 plus Z0 plus 3 Zn. Zn is 0. Zn is 0. And you don't have any fault impedance at all. Okay. You calculate this number. Calculate this number by substituting the values. 3 into pre-fault voltage 1. And what is Z1 plus Z2 plus Z0? J.2, J.14, J0.07. Okay, you calculate this value how much? LG fault current magnitude. LG fault current you calculate magnitude and all we will consider later. Yeah, what is this now? 3 times 3 by J0.2 plus J0.14 plus J0.07. You'll get like minus J7.317 minus J7.317 per unit. That's the LG fault current. Second, LL fault will be line to line fault. Okay, so it was alternator and 3 conductors I am showing like this. Okay, and it's a star with solidly grounded, and we are having a fault on DC conductors like this, LL fault, and this is a fault current which we feel, and phase B current and phase C currents of same magnitude as fault current here. Both phase conductors B and C will have same magnitude as of the fault current. Okay, whatever. What is fault current formula for LL fault here? Minus J√3 times of pre-fault voltage by Z1 plus Z2. That's it. We don't have any fault impedance in any case. So it is minus J√3 times pre-fault voltage value 1. What is the value of Z1 and Z2? What are the values of Z1 and Z2? J.2, one number, and another number is J0.14. How much is this value? How much will be this number? So this number is minus 5.094 per unit. Minus 5.094 per unit. That is a LL fault current. LL fault current. Next, similarly, you take LLG fault and try to find out the LLG fault current also. Next thing I am taking up. Next thing. Third one, double line to ground fault. Double line to ground fault. Observe. So it's an alternator. Okay, so it is a star grounded one, star solidly grounded one. And BC conductors are shorted here. BC conductors are shorted. And that is connected to ground. Connected to ground. See, some current is flowing in the phase B conductor, some current is flowing in the phase C conductor, but we are treating the fault current as summation of the two in the calculations. We are treating fault current as summation of the conductor B current and conductor C current here. And what is it fault current generally we write? In case of LLG fault, it is 3 times of zero sequence current. How to get the zero sequence current now? We don't have a direct formula. So we have to go for network analysis. 3 sequence networks connected in parallel. By doing network analysis, we should find out IA0 value. Then we can get the double line to ground fault. So in this case, there is no other choice for you. You have to draw the sequence networks definitely. Okay. So let's say positive sequence network. Positive sequence network like this we have. Negative sequence network. Zero sequence network. Up to neutral, we should keep zero sequence impedance. Neutral to ground, we should keep 0 because it is solidly grounded neutral. Okay. And this is a pre-fault voltage which we consider as 1 at an angle 0 degree in the per unit domain. And positive sequence impedance J.2. Negative sequence impedance J.12. Zero sequence impedance is J0.087. J0.07. And our interest is to find this, this current, IA0. Our interest is to find that current, IA0. So before calculating that IA0 current, first we should be ready with IA1 current calculation. Then by doing current division, we will get IA0. Okay. What is IA1 here? What's IA1? IA1 is equals to simple. Pre-fault voltage 1 at an angle 0 degree by what you can write? By J0.2 plus J.14 in parallel with J0.07. J.14 in parallel with J0.07. Yeah, please calculate this number. 1 at an angle 0 degree by J0.2 plus the parallel combination J.14 into J.07 by J.14 plus J0.07. Yeah, you please tell me this number how much? Tell me this number. IA1. IA1. Anybody? Including J, you should answer this. Minus J 4.054. Minus J 4.054 per unit. Minus J 4.054 per unit is a IA1 current. Then IA0 current you can get by current division rule. IA0 current you can get by current division rule, which is nothing but minus IA1 into opposite impedance to the zero sequence branch J0.14 by J0.14 plus J0.07. Minus of IA1 means it will turn to plus J. It will turn to plus J. Okay. You please complete it quickly. I will move to next slide to write that resultant equation. LLG fault, right? In case of double line to ground fault, we have to connect the 3 sequence networks in parallel. In case of LL fault, we should connect positive and negative sequence circuits in parallel. In case of LG fault, all the 3 sequence networks are in series. After all, we have 3 types of faults here, excluding triple L. After all, we have only 3. LG, all the 3 sequence circuits in series. Across that, you have a short. LL, positive, negative sequence circuits in parallel. LLG, positive, negative, zero sequence circuits in parallel. That's it. Okay, let's move ahead with the IA0 current here. So minus IA1 in the sense plus J4.054 plus J4.054 multiplied with this value 0.14 by 0.21. J and J will be cancelled in the numerator and denominator. You please tell me what is this value? J 2.703. J 2.703 per unit. Then fault current for double line to ground fault will be 3 times of IA naught. 3 times of IA naught. How much is this current? Fault current? J 8.108. J 8.108 per unit. J 8.108 per unit. Next one, triple fault current. That's a fourth one what you asked in the problem. Triple fault. Triple fault. Just we have this alternator and you have 3 conductors like this. Okay, and it's a star grounded alternator, and you take that 3-phase fault like this simply, and whatever the fault current you say, that fault current and phase A current both are exactly equal here also. Fault current and phase A current both are exactly equal. And what is the triple fault current formula? Simply it is pre-fault voltage value by positive sequence impedance. Pre-fault voltage 1, positive sequence impedance is J0.2. This number will be minus J5 per unit. Minus J5 per unit. All of you getting this one? Minus J5 per unit. Yeah, please kindly check that Srinaya. It will be positive J only, I think so. IA naught value, it will be positive J. Yeah, all of you getting the currents what we have seen till now? LG fault current we have calculated, LL, LLG, and then triple. By comparing these calculations, what we have done? By comparing these calculations, which is most severe one? Which is most severe fault at the alternator terminals? By comparing these 3 calculations, what you have done? These calculations what you have done, which fault is more severe at the alternator terminals? Which fault? Observe here, LG fault current you calculated, that is coming as magnitude. Magnitude only you take one for comparison sake. LG fault current magnitude 7.317. LL fault current magnitude 5.09. Double line to ground fault current magnitude 8.108. Triple fault current magnitude 5 per unit. But you see, whenever you are comparing, listen please. Whenever you are comparing the severity of the fault, all of you listen here. Whenever you are comparing severity of the fault, what we have to compare exactly speaking? Is it fault current value or current carried by the lines? Whenever we are comparing the severity of the fault from one to the other, what we have to compare exactly speaking? Is it fault current value? Or current carried by the lines? Current carried by the lines, right? Because that is the thing which is going to decide whether your alternator is going to be damaged or not. I think all of you getting my point. So, for example, particularly in case of LG fault, if you think, whatever the fault current you have and phase A current, both are same. Means, whatever fault current you calculated, 7.317 is carried by phase A conductor. Well, in case of LL fault, whatever the fault current you have calculated, magnitude, 5.094 carried by B conductor as well as C conductor. But in case of LLG fault, whatever the fault current you calculated, so-called ground current, is not the currents carried by the phase B and the phase C. Means to decide this double line to ground fault severity, I have to calculate the currents B and C rather than the value of fault current for the comparison. Okay, so immediately in the next step, what I'll do is I will attempt to calculate the B and C currents in case of LNG fault for the severity comparisons. Okay, yeah. Let's take, we have to continue that. For double line to ground fault, we have to do that continuation. Already you calculated the positive sequence current. How much is that positive sequence current in case of double line to ground fault? Done already. It is minus J 4.054. Minus J 4.054. And zero sequence current also we have done already. Zero sequence current also J 2.703. J 2.703. Okay. Now, as you know, IA1 plus IA2 plus IA0 value equals to 0. Right? You want to observe in the symmetrical component model. This is IA1, IA2, IA0. Sum of the three currents is equal to 0. From that, we are capable to get the IA2 current. What is IA2 current now? Negative of IA1 plus IA0. Else you take up the current division also, you will get the current value. So it's minus of IA1 minus J 4.054 plus J 2.703. Okay, you please tell this IA2. J 1.351. J 1.351 per unit. Okay, now you calculate conductor B current and conductor C current. Then we can confirm it. Conductor B current. Conductor B current. I'm going to calculate. Simple. What's the formula for B current? Phase B current. Phase B current. IA0 plus alpha square IA1 plus alpha into IA2. Okay. So IA0 current is J 2.703 alpha square 1 at an angle 240 degrees. IA1 current is minus J 4.054 plus alpha 1 at an angle 120 degrees. IA2 J 1.351. J 1.351. Get this current IB now. Get that current IB. Calculate with your calculator and tell me this number. What is the IB current? So magnitude and angle you are going to get there. Some magnitude and angle. Yeah. You are getting this 6.186. 186 angle of 139 degree. Cross check this one in per unit form. Cross check this 6.186 angle will be 139 degree. Okay, close to this you are going. And how is the IC current now? How is IC current? If you want, you use a similar formula to get the IC current, right? Else, as you know already, fault current IF is nothing but conductor B current plus conductor C current. You can write IC current from this as IF minus IB. This formula can also be entertained. What is this IF in case of LLC fault? J 8.108. Okay, J 8.108 minus conductor B current is 6.186 at an angle of 139. Yeah, you please tell me what is this magnitude angle? Please tell me what is this magnitude angle? It will be again coming same magnitude, I think so. Same magnitude we are going to get. Please kindly cross check this. Same magnitude you are going to get almost. Angle might differ. Angle may be different. Okay, fine. Leave it. You do that one later. Tell me now. In case of LG fault, what is phase A current magnitude we have? In case of LG fault, what is the phase A current magnitude? That's coming as 7.317. In case of LL fault, what is phase B current magnitude you got? 5.09. In case of LLG, what is the phase B current magnitude we got? 6.186. In case of triple fault, what is the phase A current magnitude we got? 5. Which fault is more severe among these three at the alternator terminals? Which fault is more severe at the alternator terminals? That will be definitely LG fault. LG fault is becoming more severe as compared to any other fault at the alternator terminals. Particularly, I'm going to make a comparison between LG and triple L faults right now. LG and triple L faults. Okay. Anyhow, you don't need to write these things. Already we have done, no, just for conclusion's sake, I have written these currents here, comparison sake only. So I can say in the next slide directly. So at alternator terminal, okay, for a solidly grounded neutral alternator, for a solidly grounded neutral alternator, grounded neutral alternator, LG fault is more severe. LG fault is more severe than triple L fault. Triple L fault occurring at its terminals. Occurring at its terminals. At its terminals. Okay. So LG fault at the alternator terminals will become more severe than the. Yeah, that's what I am saying. We are not comparing fault current, right? We are not comparing fault current. I am saying severity of the fault with respect to current flows. Severity of the current flows in the conductors, right? LG fault is more severe than triple L fault occurring at its terminals. In bracket, you write this is with respect to current magnitude. This is with respect to current magnitudes. With respect to current magnitudes. I'll tell you the simple reason why this is happening here. Anyway, we have done some mathematical problem. By that way, we have confirmed it. But still, I want to tell this thing. What is this LG fault current to triple L fault current ratio? In the way of formula. What is LG fault current formula? LG fault current formula is 3 times of pre-fault voltage by what you have? Z1 plus Z2 plus Z0. 3 times of pre-fault voltage by Z1 plus Z2 plus Z0. That's the LG fault current. What is triple L fault current formula? VPF by Z1. Okay, VPF will be cancelled out, and finally what you get this is 3 times of the positive sequence impedance by Z1 plus Z2 plus Z0. You can see 3 times Z1 by Z1 plus Z2 plus Z0. That's the ratio between the LG fault current to triple L fault current. Particularly if you talk about alternator, listen please. Particularly if you talk about the alternator, Z1, Z2 values may be a bit close. Z1, Z2 numbers may be a bit close, but Z0 number is very, very low compared to Z1 and Z2, right? Z0 value will be very, very low compared to Z1 and Z2. In that perspective, definitely this denominator number may be close to 2 times Z1 plus Z0. Okay, this value will be definitely less compared to 3 times of Z1, right? This number will be definitely less than 3 times of Z1. So this ratio will come definitely greater than 1. Greater than 1. Okay? Yeah. So let me write that statement. For alternator, particularly we are saying, for alternator, Z1 may be a bit close to Z2, but you know, Z0 is very, very less compared to Z1 and Z2. In that situation, Z1 plus Z2 plus Z0 number, it will be definitely less compared to 3 times of the positive sequence impedance. Therefore, LG fault current magnitude by triple L fault current magnitude, it will be definitely greater than 1. So, LG fault current magnitude will be greater compared to triple L fault current magnitude at the alternator terminals for solidly grounded neutral alternator. For solidly grounded neutral alternator. All of you getting this one? All of you getting this? LG fault current is more severe. LG fault is more severe than triple L fault with respect to current. See how to reduce the severity now? How to reduce the severity of LG fault now? There is a chance of reducing it. For example, if you provide some neutral impedance for the alternator, if you connect some impedance between that neutral and ground. Then in the denominator, you used to get the 3Zn here. In the denominator, you are capable to get the 3Zn. Then by manipulating the Zn value, we are capable to reduce the LG fault. Okay, but still, at this statement, I want to tell something to you. At this point, I want to tell something to you. Generally, in the earlier classes, maybe at the initiation of fault analysis and all, please tell me, based on what fault we are interested to design the breaker, we said? Based on what type of fault we are interested to design the breaker, we said? Most severe fault. Generally, it is triple L, we said, but not at all places. Generally, triple L is severe, but not at all places. Okay, particularly at the alternator terminals, as LG fault is becoming more severe compared to triple L, we have to design the breaker based on the LG fault. Okay, right. So based on this statement, I am saying that implies the generator circuit breaker shall be designed based on LG fault, which is the most severe fault we are considering, LG fault. Okay, but it is possible to reduce the severity of the LG fault. By providing some neutral grounding reactance or neutral grounding impedance. Okay, so with neutral grounding impedance, it is possible to reduce the LG fault level at alternator terminals. Okay, it is possible to reduce the LG fault level at the alternator terminals. Fine. Next, we'll do one problem on this one. Before moving to that problem, very simple question I am asking you. This is one transformer, and we have some alternator, and we have a transformer here. You assume that it is star ground transformer for time being, and this is one transmission line wire. It is one transmission line wire like this. Else you remove that transformer also to avoid the confusion. Simple, like this. We have a generator, star solidly grounded generator. We didn't connected any reactance. It is star solidly grounded alternator connected to the transmission line wire like this. Tell me. Operating at no load. This is a fault location. Bus 1 is a fault location. Which fault is more severe, you are saying? Which fault is more severe at the bus 1? Anybody? Please tell me that. Anybody? Which fault is more severe? LG. Means I should say LG is more severe than triple L. LG is more severe than triple L. Tell me, this bus 2. At bus 2, if you take fault, which fault is more severe now? In your expectation, at bus 2, which fault may be more severe? Is it LG or triple L? Triple L. Why it is so means, listen here. Why LG is more severe than triple L at the alternator terminals means, for alternator, zero sequence impedance is very, very less compared to positive sequence impedance. But you see, for transmission line wire, zero sequence impedance is very high compared to positive sequence impedance, right? For transmission line wire, zero sequence impedance is very high compared to positive sequence impedance. So if you see with respect to bus 2 terminals, it may be expected to say that overall zero sequence impedance might be larger compared to positive sequence impedance. In that situation, LG fault will become less severe than triple L fault. All of you understanding my words? All of you understanding my words? Please tell me. At this place, LG becomes less severe than triple L. Or else you write triple L will become more severe than LG. Triple L becomes more severe than LG. Triple L becomes more severe than LG. I think all of you getting this point? Clear? Fine. Good. So we used to get one model in the examination. How much amount of neutral impedance we have to connect to reduce the severity of LG fault to the triple L fault level, or to make LG fault current magnitude equals to rated current is 1 per unit. That type of problems we find many in the previous gate questions. One such type of question I want to discuss here, which asked in the recent year examinations. Okay, yeah. So let's see this question. Let's look at this question. One minute, please. See this one. See, a 30 kV, 50 hertz, 50 MVA, 30 kV, 50 hertz, 50 MVA generator has the positive and negative and zero sequence reactances of 0.25 per unit, 0.15 per unit, and 0.05 per unit respectively. Okay. The neutral of the generator is grounded with a reactance, so that the fault current for bolted LG fault means solid LG fault means with zero fault impedance. Bolted LG fault is nothing but solid LG fault means with zero fault impedance. And that of bolted three-phase fault at generator terminals are equal. The value of grounding reactance in ohms is dash. Round off to 1 decimal place. Round off to 1 decimal place. Okay, let's look at this. First of all, this is an alternator. And what's the positive sequence reactance we said? 0.25 per unit. Negative sequence reactance 0.15 per unit. Zero sequence reactance is said as 0.05 per unit. Next, ratings 30 kV, 50 MVA. 30 kV, of course, it is line to line voltage rating. 50 MVA, it is of three-phase apparent power rating. These values itself we should consider as base. And what he said is we have to connect this neutral of alternator to ground with a reactance of Xn. Such that LG fault current level should be matched with the triple L fault current. Okay, the aim is to make LG fault current magnitude equals to triple L fault current magnitude. He didn't say anything about resistances in the network. He didn't say anything about the resistance in the network. So you neglect the resistances. And what is LG fault current formula? 3 times of pre-fault voltage value by what you have? Z1 plus Z2 plus Z0 plus 3 times of Zn. This magnitude value is equals to triple L fault current magnitude is what? VPF by Z1. VPF will be cancelled out. It is 3 by Z1 JX1, right? Z2 JX2, Z0 JX0, and 3 times of Zn means J3XN. J3XN magnitude is equals to 1 by JX1 magnitude. Okay, simple, very simple problem it is. So it is 3 by, x1, x2, x0 summation 0.3, 0.45 plus 3xn is nothing but 1 by x1 number is 0.25. Okay. So from this, you can calculate 3 into 0.25 means 0.75 you can write. 0.75 is equals to 0.45 plus 3xn. 0.45 plus 3 times of xn. And if you calculate xn value from this, I think you get 0.1 per unit. You are going to get that number as 0.1 per unit, but you have to give your answer in terms of ohms. We have to give this answer in terms of ohms. Okay? Give your answer in terms of ohms. And what is Z base value here? Z base. Already voltage base line to line 30 kV and MVA base 50. So 30 kilo square in the numerator, 50 mega in the denominator. Kilo square and mega will be cancelled out. 900 by 50, 0, 0 cancelled. And you may get this like 18 ohms, I think. 18 ohms. So xn value in terms of ohms will be per unit value 0.1, base value 18. So it will come to be 1.8 ohms. 1.8 ohms. So if you connect 1.8 ohms reactance between neutral and ground, it is possible to limit the LG fault current magnitude to be equals to 3-phase fault current magnitude. Okay, this is one model. This is one model in the examination. Sometimes they will ask resistance value. Sometimes they will ask resistance value. There you should put little more effort. In the sense, if he's asking resistance value, in place of 3 Zn, we should keep 3 Rn. 3 Rn. There is a real part as well as there is an imaginary part. Yes or no? Magnitude means what now? Root of real part square plus imaginary part square. Then the calculations will be little more compared to this one. Okay? Yeah, be clear what he is asking. Whether he is grounding that neutral with a reactance or whether he is grounding that neutral with a resistance. That you should be very clear to answer. Fine. So we'll discuss last problem in the fault analysis now. Last problem in the fault analysis. So taking up in the next slide. Last problem I'm taking up. Is it there or not? Go through this. So this is one typical question we used to get sometimes in the exam. Look here. Consider the following single line diagram with points capital A and capital B shown. This is a point A and this is a point B is showing in the figure. If single line to ground fault occurs on point B, means at the point B, we have a single line to ground fault. Single line to ground fault. Then it can be seen as dash type of fault with respect to point A. With respect to point A, if you look, what type of fault it will be? Is it LG or LL? Is it LLG or triplet? That's the question. See, what you have between the point A and point B? Point B, we have LG fault. How it is looked as at A? What you have between them? Transformer. What is the transformer connection? Delta star ground. Delta star ground. Means his interest is to know. His interest is to know this transformer might be modifying the currents from one side to other side according to their flux linkage. Okay, that he is asking us to know here. So let me draw the delta star grounded transformer connection, and we'll take fault on the star grounded side, and we will see winding currents of star winding. Those currents we transfer to the delta winding. Then we will find out the line currents on the delta side, and we'll confirm what type of fault is it. Look my words. First, what I will do? I will draw the delta star grounded transformer connection. I'll take fault on the star side. I'll find out star winding currents. I'll think what are the currents on the star winding. these currents I will transfer onto the delta side. After transferring these currents onto delta winding side, find out the line currents on the delta. That will tell you what is the type of fault. Clear? Okay. So I'm showing the delta star transformer here. This is delta winding. Right? 3 windings I am showing. This type of connection you might have studied maybe in transformers. Again, 3 windings on the secondary side I am showing. This is of star grounded type. This is a star grounded type. Delta. I am doing that connection in this way. Like this you'll have. And these are the outgoing terminals, lines actually. You see, this is a side A and this was a side B actually. Side A, side B. Look, very simple, very simple, very simple. Just listen all of you. Stop writing. Stop writing. Stop writing. We have phase A to ground fault on the B. Phase A to ground fault on the B, LG fault. LG fault. See, already it is operating under no load, right? Already this whole network is operating under no load. No load means before the fault occurs, we don't have current in the first winding, second winding as well as third winding. Line currents are 0, winding currents also 0. But unfortunately, we have phase A to ground fault at this place. Nah? Because of that, this line will carry some fault current. Same current will be carried by this winding also. Same current will be carried by that winding also. Fine. What about second winding current? I need your answer, please. I need your answer. Please tell me. Please tell me kindly. What will be the second winding current? Or second line current, how much? On the star side, 0, because it is open. This current is 0. Third one current, also 0. Means obviously, the second winding will carry 0 current here. Third winding also carry the value of current as 0. Value of current as 0. See, simple. MMF balance technique we are going to apply. MMF balance technique we are going to apply. See, the first winding on the secondary side carrying a current of IF. By that way, definitely, this winding, corresponding first winding in the primary side, corresponding linked winding on the primary side will carry some current as IF. Whatever, it may be having some magnitude variation, right? Maybe in per unit it is equal. Per unit it is equal. So the first winding on star side, whatever the current it is carrying, that we have transferred onto the primary side delta winding. Second winding current on the star side carrying 0 current means what is the respective current in the delta side? 0. Second winding in the star side is carrying 0 current. The respective current on the delta side will be 0. Third winding current on the star side 0. The respective current of the primary will be 0. Yeah, have you clear about this one? I need your response. I don't explain it again. Have you understood this at this point or not? Transferring the currents from secondary windings to primary windings. Right? Simply, first winding in the secondary carrying IF. Transferred to the delta side. So first winding on delta carrying IF. Second winding in star, 0. Second winding in delta, 0. Third winding in star, 0. Third winding in delta, 0. Have you clear about this one? Are you clear? Now, what currents you have to calculate? What currents we need to calculate? Please tell me. What currents we have to calculate now? Line currents we have to calculate. Line currents we have to calculate. What is this line current? What is this line current? What is this line? Tell me, please. Yeah. What are the line currents here? Don't bother about transformation ratios and all right now. Just we are saying currents from one side to other side. Okay. Tell me, please. Apply KCL here. You will get currents, right? If you apply KCL at this place, IF is this winding current. This winding current is IF. And this winding current is 0. 0 is flowing in this line like this. 0 is entering. IF is flowing in the winding. So this line will carry a current of IF. This line will carry a current of IF. I think all of you getting this one. KCL at this node. IF is a current going out. 0 current coming in. So how much current will flow in this line? IF. Apply KCL at this node. 0 is a current going out. IF is a current coming in. Na? IF is a current coming in. Means we can say 0 is leaving out. Means IF will go out on the line, right? IF will go into the line. Right? So I can say this current as IF. IF is going out in this manner. Now, if you apply KCL at this node again, at this node, 0 current is entering and 0 current is leaving. How much current this line will be having? 0. 0. Yeah. Dear anonymous attendee, even if I say I don't explain it again, that does not mean that I won't explain it again. My intention to tell you is you will listen a bit carefully. Kindly understand me, what I am saying. Okay, don't think that in a negative sense. Yeah. Tell me please. We have some currents here. IF 0. Means what is this fault you can experience now? First line is carrying IF current. That current is coming back in the second line as IF. Third line is carrying 0 current. Third line is carrying 0 current. Means it looks to be a double line. It looks to be a double line fault because 2 lines are carrying current and that current is going and coming back, right? Between these two. Following all of you. So what's your answer now from the options given? It will be option B. So it will be looking as line to line. Correct answer will be B, we can say. B, we can say. Okay, fine. So this is the end of fault analysis, right? So in tomorrow class, we will be starting with stability analysis. Tomorrow class, we will be starting with stability analysis. And if you have any doubts, you can ask me. You can raise your hands if anybody having doubts. If anybody is having a doubt, please raise your hands. Pramod. Pramod, are you there, Pramod? Pratik, Pramod. Pratik, Pramod. Yeah, Danvi. Danvi, are you there?
Yes, sir. Sir, my doubt is, sir, in double LG fault, sir, you're telling it is ungrounded, no, sir. Then basically you're telling that zero sequence network is open. There is no zero sequence current flowing. That's why you're calling it as ungrounded fault in double LLG fault. Sir, there is one condition.
In case of double line to ground fault, as a zero sequence circuit is open, we don't have zero sequence current in that.
Yes, sir.
Okay, then what's your doubt?
Sir, there was one statement, sir, like in ungrounded fault, in ungrounded faults, like we considered various conditions, like saying that they are grounded and ungrounded, sir, with their arcing ground phenomenon, etc.
Okay.
They're ungrounded, sir. So I got confused between that LG fault is grounded, and then in double LG fault, we're saying that there's one more ungrounded. We're calling it, sir. So that's why I got confused there, sir.
No, see, if you have an ungrounded neutral system, if you have LG fault, there is a rise in the LG phases voltages. Even in case of double line to ground fault also, you have a rise in the LG phases voltages. That's what we are saying.
Okay, sir. Okay, sir.
Okay, but the possibility of getting arcing grounds for LG fault on ungrounded neutral system will be more as comparing to double line to ground.
Sir, and that ungrounded neutral system, as you just said, sir, it
Ungrounded neutral system is simply with respect to any location, so-called fault location. If you measure zero sequence impedance, if it is infinite, we will say it's an ungrounded neutral system, right?
Oh, yes, sir. This is exactly what I wanted to ask, sir. You cleared it. Thank you.
That's it. Any other doubt you have, Dhanvi?
No, sir. Only that one. Last part I had. That's
Fine. Vaishnavi.
Sir, in 339 page number, sir.
Okay.
Sir, ఇక్కడ circuit breaker rating అంటే default voltage into maximum of
You take rated voltage. In case of breaker rating, we should take rated voltage, right? Not pre-fault.
okay sir, rated voltage into current అనేది maximum of అంటే ఏ
You
phase
see, listen. If you are thinking about this breaker one capacity, if you have taken fault at this place, you know, whatever the current supplied by A is coming through breaker and going into fault.
yes sir, yes.
Whatever the current supplied by the B coming in this manner and going into the breaker only, right?
Yes sir, but
Then why
we
did
have
you
to
take maximum of
sir, you said in formula no sir, that only starting class లో circuit breaker rating formula చెప్పేటప్పుడు
what is the difference between this diagram and that diagram? For example, if you have one breaker at this place, and if you have taken fault at the location of breaker, if you are getting current from both sides of the breaker,
yes sir.
then you should take maximum of these two currents, right?
ఇక్కడ రెండు ఒకే
Here both
డైరెక్షన్
currents are in the same direction.
ఓకే సార్.
Understood?
Understand.
Yeah. Any other doubt you have? Vaishnavi?
No sir. No sir.
Thank you. Tulsi,
Hello, sir.
tell me, Tulsi.
Sir, in 314F, sir.
Okay.
సార్ ఇది మామూలుగా మనం కన్సిడర్ చేసుకునేటప్పుడు ఫస్ట్ ఫార్ములా తీసుకోండి అని చెప్తారు కదండి సార్ మీరు. అప్పుడు డైరెక్ట్లీ షార్ట్
In
సర్క్యూట్
fault current also you have pre-fault voltage, right?
సార్ ప్రీఫాల్ట్ వోల్టేజ్ కి స్క్వేర్ కాకుండా నార్మల్లీ డైరెక్ట్లీ ప్రపోర్షనల్ ఉంటది కదండి సార్.
Sorry, short circuit MVA equals to pre-fault voltage into fault current.
ఎస్ సార్.
In the fault current also you have pre-fault voltage, right?
ఓకే సార్. Got it, sir.
Okay.
Sir. Okay, got it, sir. Sir, in 318F, sir.
Okay.
సార్ ఇక్కడ ఫస్ట్ బ్యాలెన్స్డ్ నుంచి అన్బ్యాలెన్స్డ్ తెచ్చి మళ్ళీ మనం వాటిని కన్వర్ట్ చేస్తున్నామా సార్?
No, we are discussing two different systems.
ఓకే.
Why you are coming to unbalanced from balanced? First we discussed about pre-fault system is balanced, how the things will be.
ఎస్ సార్.
Then we say that pre-fault system may not be balanced in all cases. It may be unbalanced also.
అప్పుడు అన్బ్యాలెన్స్డ్ అన్నప్పుడు ఆ VA1 మనం ఫస్ట్ తీసుకోవాలి కదండి సార్, VA, VB, VC వాల్యూస్ ని.
We have to write it. Tulsi,
సార్.
in the pre-fault condition, we have VA, VB, VC.
ఎస్ సార్.
Those are converted into symmetrical components.
ఓకే.
You got positive sequence pre-fault, negative sequence pre-fault, zero sequence pre-fault.
ప్రీఫాల్ట్.
Okay.
ఓకే సార్.
Then we have taken fault at that place.
ఓకే సార్.
After the fault has been taken, you know, VA equals to VB equals to VC.
ఎస్ సార్.
Post-fault condition.
Ah.
From that VA equals to VB equals to VC, you got VA1 value 0. VA2 value 0. VA0 value VA. That's what we
Okay.
explained in normal triple L fault.
ఓకే సార్.
Those conditions we should implement in the sequence networks.
ఓకే సార్. ఓకే, గాట్ ఇట్.
Yeah.
సార్ అక్కడ ఒకటి చెప్పారు కదండి సార్, ఎల్జీ ఫాల్ట్ ప్రీ ఫాల్ట్ వోల్టేజ్ 1 ఉంటుంది, అది √3 పెరగడం వల్ల 1.732 అవుతుందా సార్ అది?
Yeah, what is that?
ప్రీ ఫాల్ట్ వోల్టేజ్ 1 per యూనిట్ ఉంటుంది. దాని తర్వాత అది √3 టైమ్స్ పెరగడం వల్ల ఎల్జీ ఫాల్ట్ లో 1.732 అవుతది.
At default, for ungrounded neutral system, obviously voltage will become √3 times, right? Healthy phase voltage will become √3 for
ఎస్
a
సార్.
single line to ground fault. That we discussed in yesterday class.
ఎస్ సార్. అది గుర్తుంది సార్. కానీ ఇక్కడ మీరు చెప్పేటప్పుడు ఒక పాయింట్ మిస్ అయినాను సార్. అందుకు డౌట్ వచ్చింది సార్ అది.
Tell me, what is that location where you have missed that point?
ఒక నిమిషం సార్. అదే సార్ ఎల్జీ ఫాల్ట్ అనే అక్కడ రాసేటప్పుడు 1.732 అని రాసాం సార్ డైరెక్ట్ గా.
That open system, right? It is Z0 equivalent is infinite, right? For that system.
ఓకే సార్. అది ఒకసారి చెప్తారా?
Calculate Z0 equivalent of that system with respect to bus 3.
నాకు ఇక్కడ కనపడడం లేదు సార్. ఒక
See this.
ఎస్ సార్.
If you calculate Z0 equivalent with respect to bus 3, this looks to be open, right?
ఎస్ సార్.
Delta Y ungrounded.
ఎస్ సార్.
If that is the case, obviously your Z0 equivalent is infinite.
ఎస్ సార్.
Means your zero sequence circuit is open. If you draw 3 sequence networks connected in series and zero sequence circuit open, we have done in yesterday class arcing grounds.
ఎస్ సార్. ఎస్ సార్.
From that, healthy phases voltage will be 1.732.
ఓకే
√3.
సార్. ఎస్ సార్.
That's it. What's the doubt you have now?
అంటే √3 ఆఫ్ ది ప్రీవియస్ వోల్టేజ్ అండ్ ప్రీ ఫాల్ట్
Default
వోల్టేజ్.
voltage 1 I have taken.
ఓకే సార్. దట్స్
I have given here. Default voltage 1.
ఓకే. 1.732 into 1 అవుతుంది కదండి సార్. అంటే నార్మల్లీ మనం
1.732. Yeah. Default voltage 1 means you will get same value, right?
ఓకే. దట్స్ ఆట్ ఓన్లీ సార్. థ్యాంక్ యూ.
Any other doubt here, Tulsi?
నో సార్.
Pratyush.
Hello, sir.
Tell me, Pratyush.
Sir, in case of LG fault, if the alternate is isolated, then we applied KVL, no sir, in A and B to say that terminal voltage of VB is √3 times of line √3 times in case, no sir.
Which one?
VB is √3 times of phase voltage, no sir. In case of
Fault
isolated, no
voltage.
sir. Yes, sir.
Okay.
Sir, by applying KVL, we said no sir simply, but not
Yes.
by symmetrical components, sir.
Yes.
Sir, why that can't be applied in LLG, sir, by taking same with
If you
respect
are
to A, sir?
capable to apply KVL, you can apply it. Pratyush.
Yes, sir. Sir,
If you are
then
capable to solve with a KVL application, you can do it, right?
yes, sir. Then it should be also 1.732, no sir. We will get line to line only, no sir. VB is equal to VC, sir.
VB equals to,
VC.
and it is grounded.
Yes, sir.
Between A and ground, you have to calculate the voltage.
Yes, sir. We can calculate with respect to B only, no sir.
Okay. A to B you can do. A to C also I can do, right?
Yes, sir.
Then you will get two different numbers. Means angles will be different.
Okay, yes, sir.
Okay.
Yes, sir.
In that case, it is better to find that neutral to ground voltage. And then you take A to ground means A to neutral and then neutral to ground.
Okay, sir.
Okay. Getting
Yes,
that
sir.
ambiguity, what is it?
Means that neutral to ground potential will be shifting, sir.
It will be changing continuously.
Okay, sir. Okay, sir.
Okay.
Okay, sir. Then it is better to go by symmetrical components only.
Symmetrical components. Yes.
Okay, sir. Thank you, sir. That's it.
Yeah. Gautami.
హలో సార్.
Tell me, Gautami.
సార్ లాస్ట్ లో డెల్టా టు స్టార్ కనెక్ట్ చేసుకున్నప్పుడు ఇక్కడ ట్రాన్స్ఫార్మర్ కి మ్యాగ్నెటిక్ అంటే కోర్ అనేది 2 ends కి ఒకేలాగా జాయిన్ చేస్తారు కదా సార్.
Yes. You assume those are 3 single phase transformers. If you have that type of doubt, you assume 3 single phase transformers separately.
యా సార్ అదే సార్ డౌట్ ఉంటే అట్లా. ఓకే సార్, థ్యాంక్ యూ సార్. అంతే సార్.
Then Matthew. Alan Matthew. Alan Matthew. Do you have any doubt, Alan Matthew? Okay, if anybody have doubts, you can raise your hands.
Hello, sir.
Tell me. Alan.
Hello, sir.
Tell me, please, Alan.
Sir, but you are not audible. 1 minute, sir.
Are you hearing me, Alan?
Hello.
Alan. Alan, are you there? Are you listening to me?
Sir, just answer me. You are not audible to me. But anyway, I will ask my question and I will see it in the recorded lecture.
Okay.
I will ask my question. So, in that CB rating formula, in that we are writing CB rating is equal to 3 into, means if we take per unit value, we face into IB, no, sir? In that we face means we always write we face, but in numerical which you have solved, we have always used V pre-fault.
No,
So-
V phase we have to use in case of breaker rating. In the fault level calculation, we should go for the pre-fault voltage.
So you are not audible. Just answer me. I will see it in the recorded lecture.
Yeah, okay.
My doubt is that we always while writing formula we write V per phase, and while solving we never use that. So where is the situation when we use that V phase formula? Means V phase value.
No. I'm unable to get you exactly what you're asking.
Okay, okay, sir. Okay, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. In my doubt, the formula of CB rating, we find. Yes, sir. Yes, sir. Yes, sir. So that we face, we always means in the numerical or later in this sum, we are always use we face as V pre-fault. In that situation, it may be correct. No. We have to use. With rated phase
Okay.
voltage. Okay. Okay, sir. For that line we have to use that rated phase voltage, no, sir? For S.
Yeah.
For CB rating, right?
CB rating.
Yes, sir. I got you. Thank you, sir.
Kumar.
Hello, sir.
Tell me, Kumar.
Sir, for every fault calculations like LGLL, we take pre-fault as balanced.
Yeah, yes.
But in practically, it is not happening. Then how do we proceed for unbalanced?
See, we may not get a great change actually, because your practical system is unbalanced only, but not again heavily unbalanced.
Sure.
Getting Kumar?
Yes, sir.
Your practical system is unbalanced, surely, but it's not heavily unbalanced as we think.
Yeah.
Okay, so in that view, even though you consider that the original system is balanced and you are doing fault analysis, it is okay with the numbers what we do. Okay.
Okay. Only negative sequence and zero sequences లో వాటి యొక్క voltages వస్తాయి. Remaining అంతా సేమ్ ఉంటుంది.
Yes.
Like sequence networks లో.
Yes, correct. Only negative sequence network and zero sequence network, you get a minor component of voltage, very small voltage you will get.
Okay.
Unless otherwise, the values what we get will be close to the what we call practical values.
Sir, one more doubt. In triple L and triple LC fault లో only positive sequence currents వచ్చాయి కాబట్టి they are balanced we call. But terminal voltage like VA, VB, VC are equal to 0. So they are not satisfy the property of balance condition. It's not like that.
VA, VB, VC are 0 in the sense we can't confirm that the system is balanced, right?
So generally what we say that when the system is balanced or not, voltage magnitude should be like we say that, or currents also. Here currents, okay, it satisfied the current. Both sir. So here current satisfy the condition, but voltages are equal. Means phase A voltage, phase B are all are equal and equals to 0.
Means I can write VA equals to 0 at an angle 0 degree. VB equal to 0 at an angle minus 120 degree. VC equal to 0 at an angle plus 120 degree.
Okay.
Balanced only, right?
Sure. So, which means no voltages are induced in generator.
What are these voltages? Terminal, not internal, right?
Okay.
You have your internal EMFs as it is.
Okay, the internal EMs are taken as the drops in their respective impedances.
Yes.
Okay, sir.
That's it. Any other doubt you have, Kumar?
No, sir.
Yeah. Bhaskar.
హలో గుడ్ ఈవినింగ్ సార్.
Tell me, Bhaskar.
సార్ ఇది సివియారిటీ అనేది కంపేర్ చేసేటప్పుడు ఓన్లీ ఫేజ్ కరెంట్ ఎందుకు మనం తీసుకుంటాం సార్? ఫాల్ట్ కరెంట్.
So what is the current flowing in your alternator winding?
వైండింగ్
Fault current or phase currents?
ఫేజ్ కరెంట్ సార్.
Then phase currents will decide whether your winding is going to be damaged or safe.
ఓకే సార్, బట్ మనం ఫాల్ట్ లెవెల్ షార్ట్ సర్క్యూట్ ఏమి కనుక్కునేటప్పుడు ఫాల్ట్ కరెంటే తీసుకున్నాం కదా సార్.
That calculation is only in the view of examination. That fault level calculation and all.
ఓకే సార్.
I don't do anything with that fault level, strictly speaking.
మీన్స్ అవి అంటే రేటింగ్, బ్రేకర్ రేటింగ్ అవి.
No, again breaker rating formula is different and fault level formula is different, right?
బ్రేకర్ రేటింగ్ మీన్స్ ఫేజ్ కరెంట్.
Some cases both fault level and breaker ratings might be equal in some
Okay.
cases.
ఓకే సార్.
Okay, otherwise we don't have any practical significance to take up with fault level.
ఓకే సార్.
Okay.
ఓకే సార్.
Yeah. Any more doubt you have, Bhaskar?
మీన్స్ మనం ఇప్పుడు అంటే ప్రతి అంటే ఏ ప్రాబ్లం చేసినా ఫాల్ట్ కరెంట్ కనుక్కుంటాం కదా సార్.
But strictly speaking, it's not required to find fault current value. During that disturbance, so-called fault, it is required to know what are the currents carried by your windings.
Yes, sir.
Okay, that is a main intention or main motto of fault analysis, strictly saying.
Okay.
Based on that only, we are going to design your breaker and all, right?
Yes, sir.
Yeah.
Okay, thank you, sir.
That's it.
Okay.
Yeah. Ram Pawan.
Hello, sir. Good evening, sir. Sir, in page number 286, sir.
Okay.
Sir, here in double LG fault, how could we be getting 1.5 per unit, sir? It should be like we have taken pre-fault voltage as 1 per unit, no, sir. Each VA0, VA1 and VA2 will be getting VA by 3, no, sir.
VA by 3.
Yes, sir. But VA is if we take V as default voltage, it should be like a 0.33, no sir, 1/3 each.
Why VA you are saying pre-fault voltage here?
So isn't it pre-fault voltage we have taken?
All these things we have written are post-fault conditions, right? During the fault,
sir.
how much is the voltage?
So, but why do you take 0.5 each, sir? Is
You have
there
to
a
do
reason
analysis
for
for it.
taking 0.5 each?
You draw positive, negative, zero sequence networks and connect them in parallel.
Sir,
Take the pre-fault voltage one, calculate VA1, VA2.
then do we get them, sir?
Yeah,
0.5.
you get 0.5 per unit. Yes.
Okay, sir. Okay, sir. I had the same doubt. That's
You
thanks.
do that. Do that first. Okay.
Okay, sir. Okay, sir. I'll try, sir. Thank you, sir.
Yeah. So any other doubts you have? Can raise your hands. Nitish Reddy.
In three-phase unbalanced system, can we say negative sequence component magnitude is less than positive sequence?
Didn't get you, Nitish Reddy. What you are asking me? Please kindly repeat, Nitish Reddy. What's your doubt?
In three-phase unbalanced system, magnitude of negative sequence components cannot be greater than positive sequence components.
In three-phase?
Unbalanced system.
Okay, unbalanced system.
Negative sequence component magnitude
Hmm.
cannot be greater than positive sequence component magnitude.
Okay.
Is it true or false?
Where you have found that question?
In textbook, sir.
Which textbook? Can you tell? Can you know?
I don't know, sir. It is on the not there. It is in some PDF, sir. Not. It is taken from textbook, but there is.
Which textbook? If it is from textbook, I will try to answer it.
I don't know the name, sir.
Can't be greater than negative sequence. Sorry, positive sequence. It's not a proper statement to say exactly.
Okay, sir.
What that statement should be is, in general, for a practical power system network, the negative sequence component value may not be greater than or will not be greater than the positive sequence component. You should not say can't be greater than. Yes or no?
Okay, sir.
So you can, if for your answer, if you want, you can say that statement as true. That's your wish. If you want, you can consider it. But strictly speaking, I don't accept with the wording of that statement exactly. Practically in a power system network, positive sequence components are dominant ones compared to negative and zero sequence components. Yeah, I am unable to get you. Are you listening to me, Nitish?
Yes, sir.
Okay, understood what I said?
Okay, sir.
So you can say practically negative sequence component will not be greater than the positive sequence component. That's a correct one to say. But you should not say can't be greater than positive sequence component. We should not force that statement.
Okay, sir.
Yeah. Any other doubt you have, Nitish?
No, sir.
Yeah, fine. Any other doubts you have? Please tell me.
Hello, sir.
Tell me, Tulsi.
Sir, in 332, sir.
Okay.
Sir, a question ఒకసారి explain చేస్తారా sir?
What doubt you have in this question?
ఫస్ట్ లో ఎలా ప్రొసీడ్ అవ్వాలో చెప్పారు కదండి సార్, ఆ ప్రొసీజర్ సార్.
No, have you listened this one?
ఎస్ సార్. ఇప్పుడు సొల్యూషన్ విన్నాను.
At what point you have a doubt?
ఇంటర్ కనెక్షన్ అది నాకు అర్థం అవ్వలేదు సార్. ఏ న్యూట్రల్ నుంచి అది తీసుకున్నామో అక్కడ సార్.
న్యూట్రల్
సార్ పర్ ఫేజ్ నెట్వర్క్ ఇస్తాం కదా, స్టేషన్ ఏ స్టేషన్ బి ప్రాబ్లం.
Okay, this one.
ఎస్ సార్, దిస్ వన్ సార్.
Okay. Okay.
ఇక్కడ పర్ ఫేజ్ నెట్వర్క్ దగ్గర ఎక్స్ ఈక్వలెంట్ తీసుకుంటున్నాం కదండి సార్, అది ఎందుకు
Yes.
తీసుకుంటున్నాం?
We have to calculate the short circuit MVA with respect to station A.
ఓకే సార్.
So to find out that short circuit MVA, we should take base MVA by X equivalent.
ఓకే సార్.
What is X equivalent with respect to A? X equivalent means you have to measure with respect to, sorry, from A to reference. Between A and reference, you should find out equivalent reactance, right?
ఎస్ సార్.
Between A and reference, I am attempting to get. Reference is neutral here.
ఓకే సార్.
Now you know XA here, and XR and XB will come in series in this other side.
ఎస్ సార్.
So XB plus XR in parallel with XA is a value of X equivalent A.
ఓకే సార్.
That's what we have done here.
రెఫరెన్స్ తో ఓకే సార్, అర్థమైంది సార్.
Whenever he is asking to find Thevenin impedance with respect to one point, means that between that point and reference, we have to do the calculation, right?
ఓకే సార్.
Okay.
ఓకే సార్, గాట్. థ్యాంక్ యూ.
Yeah. Fine. So any other doubts? You can raise your hands, else we can leave. Abdul Rahman. Abdul Rahman, do you have any doubt, Abdul Rahman? Abdul Rahman, do you have any doubt?
हेलो सर.
Tell me.
सर मेरे को डाउट क्या है, तो आप लास्ट प्रॉब्लम बोले था ना सर, एलजी फॉल्ट का.
हाँ.
पॉइंट बी विच इज सीन विथ रिस्पेक्ट टू पॉइंट ए.
क्या?
उसमें क्या है तो सर, अगर ट्रांसफार्मर कनेक्शन स्टार टू डेल्टा है समझ लो सर, उस टाइम पे भी सेम ऐसा ही प्रोसीजर फॉलो करना सर?
नहीं नहीं.
हाँ.
पहले ये एलजी फॉल्ट सर्कुलेट करता नहीं चेक करना.
अच्छा.
ये डेल्टा स्टार ग्राउंड ट्रांसफार्मर है ना
जी,
डेफिनेटली एलजी फॉल्ट करंट सर्कुलेट करता.
अच्छा अच्छा, टाइप ऑफ कनेक्शन के ऊपर डिपेंड होता सर.
हाँ या.
अच्छा, पहले वो कनेक्शन देख के वो हिसाब से क्या बोलते हैं, एलजी फॉल्ट एग्जिस्ट होता नहीं होता?
हाँ, नहीं होता वो चेक करना पहले.
अच्छा.
हाँ, बाद में वो करंट्स we have to take and we should transfer.
अच्छा सर. सर और एक क्या है तो सर, हाँ, विद रिफर्स टू प्राइमरी है तो भी, विद रिफर्स टू सेकेंडरी है तो भी ऐसा ही. फॉर एग्जांपल अपन क्वेश्चन में ऐसा बोले था ना सर, क्या बोलते हैं, बी में फॉल्ट आया ए के टुवर्ड्स सी एंड टू ए का, तो हम रिफर्स टू प्राइमरी ले लिए.
प्राइमरी लाइंस.
हाँ. फॉर एग्जांपल हमें रिफर्स टू सेकेंडरी का तो फ्रॉम ए टू बी देखना है.
ए टू बी देखना बोले तो ये डेल्टा है ना प्राइमरी
जी.
ये करंट नहीं कैरी करता, ये डेल्टा वाइंडिंग.
सर कनेक्शन चेंज हो तो बोल रहा हूँ सर मैं, अगर ये डेल्टा नहीं हो सका दूसरा.
LG faulted A,
जी,
LG faulted A, then this delta star ground transformer will not carry any current, right?
हाँ.
Then the transformer will not carry any zero sequence current at all.
अच्छा 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 अच्छा. हाँ सर, और एक है, अपन या एक इस क्वेश्चन में सिंगल लाइन टू ग्राउंड एलजी फॉल्ट बोलने के वजह से हमें ऐसा करे, क्या बोलते हैं, डेल्टा टू कनेक्शन एग्जिस्ट होता नहीं होता वो सोच के अपन ऐसा ले लिए. अगर फॉर एग्जांपल दूसरा एक नेटवर्क दिया सर, दूसरा एक नेटवर्क दिया, उस टाइम पे ट्रिपल एल फॉल्ट हो, एलएलजी फॉल्ट हो, कौन सा भी अगर चेक करना का तो पहले आप कनेक्शन देख के वो हिसाब से एग्जिस्ट होता नहीं होता देखना, राइट?
ठीक है. यस
सर. ओके सर. सर और एक है, मैं इधर डेल्टा वाइंडिंग, सर मैं प्राइमरी डेल्टा वाइंडिंग के बारे में बात कर रहा हूँ मैं. इधर फर्स्ट नोड है ना सर, वहाँ ओके सर, आई एफ इक्वल टू सम वैल्यू आया. इधर मेरे को कितना आएगा तो सर, सेकंड नोड के पास आई एफ इक्वल टू माइनस वैल्यू आया, माइनस आई भी कुछ आया था. सर मैं बोलने का मतलब क्या है सर, फर्स्ट नोड में आई एफ इक्वल टू आई ए ले लिया सर मैं,
ठीक है,
केसीएल अप्लाई करके. सेकंड नोड के पास आई एफ इक्वल टू माइनस आई भी आया. थर्ड नोड के पास आई सी इक्वल टू 0 आया.
ठीक है.
हाँ, आप ये डायरेक्शन कैसे
वो
ले रहे
LL
हो?
फॉल्ट होता है ना.
LL फॉल्ट होता, लेकिन इधर टू भी सेम वैल्यूज नहीं है ना सर. एक इसमें IA वैल्यू है, एक इसमें अगर मैग्नीट्यूड प्रिफर करें तो सेकंड में IB
मैग्नीट्यूड एक ही है, वो करंट सर्कुलेट कर रहे हैं ना, वो बोथ लाइंस में
सर्कुलेट कर रहे हैं, लेकिन सेम नहीं है ना सर.
सेम करंट मैग्नीट्यूड से ना. Notation changed, IA, IB, but currents will be same, right?
नोटेशन चेंज, हाँ नोटेशन चेंज हुई है.
Notations change हुआ,
हाँ
but
जी.
numerical value same है ना.
अच्छा अच्छा अच्छा. तो इसलिए हमें दो भी सिमिलर ले लेके LL फॉल्ट का बोले.
Yeah.
ओके ओके, थैंक यू.
Yeah. Any other doubt you have, Abdul?
नहीं सर, ओके, थैंक यू.
Any more doubts? You can raise your hands. Murali Krishna. Tell me, Murali Krishna, do you have any doubt?
సార్ గుడ్ ఈవినింగ్ సార్.
Good evening.
సార్ అదే సార్, ఈ స్లైడ్ ఉంది కదా సార్,
Hmm.
ఇప్పుడు ఇన్ కేస్ ఏమన్నా మనం ఇక్కడ బి పాయింట్ దగ్గర LL ఫాల్ట్ అనుకుంటే
Hmm.
ఇక్కడ ఏ పాయింట్ దగ్గర అంటే ఐ మీన్ ఏ ఫాల్ట్ వచ్చే ఛాన్స్ ఉంటుంది సార్? ఏమన్నా ఇదే ఫాల్ట్ వస్తుందా, LG ఫాల్ట్ వస్తుందా?
Then all the three wires will carry currents, right? For example, if you take LL fault here,
ఎస్ సార్, అటు బి పాయింట్
it
దగ్గర.
is carrying some current. This winding also carries some current.
ఎస్ సార్, సెకండ్
Those
వైండింగ్.
currents transfer to this side. Means in the
Okay.
primary, this winding will carry current. This winding also will carry some current.
ఎస్ సార్.
And you have to find out these line points.
ఓకే
Based on that, it will be decided. For example,
సార్.
is delta. Star. We have LL fault here between
Yes, sir.
AB like this. It will carry some IF and
Okay,
it
sir.
will carry some IF in the opposite direction.
ఓకే సార్.
This current is 0.
0. ఎస్ సార్.
When this IF of first winding transferred to this place, it is IF.
ఓకే సార్.
IF of this second winding transferred to this place, this is IF.
ఓకే
Okay.
సార్. ఓకే
And
సార్.
this current is 0.
ఎస్ సార్.
KCL at this node. IF is going out
ఎస్ సార్.
in the winding. And the other wire current is 0 coming in. This wire
ఓకే
current.
సార్. ఎస్
Zero.
సార్.
And this
Okay.
IF going out. So IF will enter into that point node.
ఓకే.
At this node, you see, IF is entering.
ఎంటరింగ్.
Again, IF is entering here.
ఎస్ సార్.
So 2 IF should go out.
ఓకే సార్.
And this node, you see, IF is leaving in this direction. 0 is going in this direction. IF should enter in this direction.
ఓకే సార్.
What is the type of fault? We can't say.
ఎస్ సార్.
Exactly, we can't say what is the type of fault.
అంటే సపోజ్ ఇన్ కేసు ఇలాంటి మోడల్లోనే ఇంకొక క్వశ్చన్ అడిగినాను సార్ ఎగ్జామ్లో.
Hmm.
అంటే మేము వేటిని బేస్ చేసుకుని అంటే ఐడెంటిఫై చేయాలి సార్? అంటే ఈ జీరో సీక్వెన్స్, పాజిటివ్ నెగిటివ్ అవి ఉన్నాయి సీక్వెన్స్ కరెంట్స్ ఉన్నాయి కదా సార్, వాటిని బేస్ చేసుకుని.
Analysis will be there, but it's not a proper analysis. Strictly saying,
ఓకే సార్.
it's not a proper analysis. For
అదే సార్.
example, if you have a double line fault here,
ఓకే సార్.
we'll say we have positive and negative sequence currents are existing on this side.
ఎస్ సార్.
On the other side also, we will have positive and negative sequence currents.
ఎస్ సార్.
Okay, based on that, I can't confirm that the fault has a LL fault, right?
ఎస్ సార్.
For example, if you have double line to ground fault on this side,
ఎస్ సార్.
we have positive, negative, and zero sequence currents, all the three.
ఎస్ సార్.
And if, but on the other side, you say it's a delta star ground, means on this side you don't have zero sequence current.
ఎస్ సార్.
Means I should not confirm that as LL fault, right?
ఎస్ సార్.
So if you have different types of faults, whether all the three wires are carrying current or only 2 wires are carrying current? That depends.
Yes, sir.
Okay.
Okay, sir. Okay.
Can't say it exactly what type of fault it will be.
ఓకే సార్. అదే సార్ ఇది వరకు చెప్పింది అది గేట్ క్వశ్చనే కదా సార్, ఇంతకుముందు మీరు చెప్పింది మీరు
Gate
ఎగ్జాంపుల్ గా
question or
చెప్పిన.
some previous exam question, I think. Gate or IES.
ఓహో, ఓకే సార్. ఓకే సార్. ఓకే, దట్స్ ఆల్ అండి సార్.
Okay.
ఓకే సార్, థ్యాంక్ యూ సార్.
Any other doubts you have? Please raise your hands.
హలో సార్, వన్ లాస్ట్ డౌట్ సార్.
Tell me those.
సార్ డ్యూరింగ్ ఫాల్ట్ అన్న ప్రీ పోస్ట్ ఫాల్ట్ అన్న ఒకటేనా సార్?
ఈ ఫాల్ట్ అనాలిసిస్ లో
ఒకటి. అదే సార్ SSSG లో డ్యూరింగ్ ఫాల్ట్ అని రాశారు సార్. తర్వాత
డ్యూరింగ్ ఫాల్ట్ అన్నా పోస్ట్ ఫాల్ట్ అన్నా ఫాల్ట్ అనాలిసిస్ లో మాత్రం ఒకటి.
ఓకే సార్. ఆఫ్టర్ ఫాల్ట్ అక్కర్డ్ అన్నా సేమ్ వస్తాయి కదా?
సేమ్. బట్ ఇన్ స్టెబిలిటీ వి హావ్ సమ్ అదర్ నోటేషన్.
ఓకే సార్.
ఇన్ స్టెబిలిటీ పోస్ట్ ఫాల్ట్ మీన్స్ ఆఫ్టర్ క్లియరింగ్ ఫాల్ట్.
ఆఫ్టర్ క్లియరింగ్. ఓకే సార్.
That notation problem is there. Even in one of the standard textbook, they have written it clearly.
Okay, sir.
In fault analysis, if there is a term called as post fault, you should consider this as during fault. In stability analysis, if it is a post fault, you should consider it as after clearing fault.
Okay, sir.
That statement is there in very old standard textbook, one of the standard textbook.
Okay, sir.
Okay, that confusion we have to carry. We have to be clear.
That's why only, sir, I got doubt, sir. Here, during the fault, especially you mentioned in SSSG.
During fault, post fault, after the occurrence of short circuit fault will be same terms in the fault analysis.
Okay, sir.
Okay.
Got it. Thank you, sir.
Any other doubts you have? You can raise your hands. Can we leave? Thank you. If you don't have doubt, you can leave. If you don't have doubt, you can leave. Okay. I'm closing the session. Okay.